All right, I guess we can get started. Okay, good morning, everyone. Welcome to the 2020 Singapore Symposium on Natural Language Processing. Um, I'm very happy to see many people here today, and thank you for your presence. I am the general chair for this year's event. So on behalf of all the committee members of this event, we thank you for being here today. First of all, we would really like to express our special thanks to the Chinese and Oriental Languages Information Processing Society, which generously provided sponsorship for this event. Without their support, we would not be able to host the event entirely online with so many of you joining us. So thank you. Now, for those of you who are attending the SSNLP for the first time, let me just give a very quick introduction of the Singapore Symposium on Natural Language Processing. So SSNLP it started in 2018. It was initially initiated by Professor Ming Yan Kan from the National University of Singapore. And in 2018, it was held in the beautiful campus of SUTD and successfully attracted, if I remember correctly, more than 500 participants that year. And subsequently, in 2019, we had the second Singapore Symposium on Natural Language Processing, and this time was hosted by A-Star at Fusionopolis. And again, I think registration was full last year. Now, this year, things, of course, are different because of the ongoing pandemic. Unfortunately, we will have to move this event entirely online. We are very lucky to have two very energetic and enthusiastic junior researchers as our program chairs. So we have Ganeshwar Krishna Murthy from IHPC and Wenqiang Lei from NUS as the program chairs this year. The two of them have done a lot of work in the past few months to put together the program for this year's event. So I really like to thank them for their hard work. As you can see from our website, they have put together a wonderful program for today. So in total, we have 7 invited speakers from overseas. We also have a panel discussion in the afternoon to talk about low resource NLP. So here, I would really like to thank all the invited speakers for spending their precious time with us today. So later on, I hope that you all will enjoy all these talks, and please feel free to ask questions to our invited speakers. I'm sure they will all be very happy to answer your questions. And we are also very lucky to have 5 people who all have experience from leading industry research labs, right, to join us for the panel discussion in the afternoon. So again, make sure you join the panel discussion to hear about their thoughts on low resource NLP. Now, I would just like to hand over to one of the program chairs to give you some, just to tell you more about the logistics for today.
Hello, everyone. Good morning and good afternoon for people joining from other time zones. Thank you for joining us today. So we have a fantastic lineup of speakers, and in case you have any questions during the session, you can find the Q&A section below on your Zoom, right? And after the session, in case you have you need to discuss with them about anything, you can again come back to our Slack channel, and you can scan this QR code in order to access the Slack channel. and you can ask them questions there. We have a special section, a special channel for this called Q&A. You can start asking questions there, and the speakers can respond to your questions there. That's it for today. I think I will hand over to Saujanya and Mohit. Let me invite them. So Saujanya is a professor, assistant professor at SUTD. So he's going to welcome our next speaker. Saujanya, to you, please.
Yeah. Thank you, Ganga sir. I think Mohit is here, right?
Yes, he is here.
Okay, awesome. Okay, great. Hello. Okay. Thank you, Mohit, for accepting our invitation. It's an honor to host you, virtually. I mean, due to the pandemic, but it's an honor to host you here. Uh, Mohit is going to present a talk on knowledge robust and multimodally grounded NLP. So Mohit is the Parker Associate Professor in the Computer Science Department at UNC Chapel Hill. Prior to this, he was a research assistant professor at TTI Chicago. He received his PhD from UC Berkeley and BTech from IIT Kanpur. His research expertise is in statistical natural language processing and machine learning with a focus on multimodal grounded semantics. And he also works on QA, dialogue understanding, human-like language generations. So there are various prestigious awards that Mohit has received. To name a few, and they are 2020 IGCAI Early Career Spotlight, 2019 DARPA Directors Fellowship, 2019 Google Focused Research Award, and 2019 NSF Career Award. Mohit also served as a program co-chair for Cornell 2019, a senior area chair for several ACL, MNLP, and AAAI conferences. I wholeheartedly welcome Mohit to deliver his talk. Looking forward to it. Stage is yours, Mohit. Thank you.
Great. Thanks a lot, Jiang, Saujanya, Gangeshwar, everyone. And thanks for attending, everyone. Like everyone else said, I'm hoping that we'll meet in person soon, but we'll do it virtually for now and hope everyone's staying safe and healthy. Especially, it's been like 9 months. So I'm sure, yeah, everyone's tired of COVID by now. So I'll share my screen and share screen, view full screen mode. So Saujanya, can you see the full screen?
Yes, I can see your screen. Yes.
Okay, great. Okay, so yeah, so today I have around 30 minutes. So this will be more like half a version of the usual, maybe 45 to 1 hour talks. But I'll try to do my best to cover two aspects today. One is how to make current state-of-the-art NLP, and when I say NLP, I mean both understanding and generation models, how to make them more robust towards knowledge, and I'll explain more what I mean by that, and also how to ground them into other modalities and in the environment surrounding us. So by knowledge robust NLP, what I mean is that we need to be able to have systems around us, whether they are doing natural language understanding or generation or both. We need to have systems that can satisfy certain properties in terms of being knowledgeable, consistent, and robust. So here are some bullets that I'll try to cover briefly in some of the work we are doing in my lab. So some of the things are towards auxiliary skills, which means that, as you might know, some of these end-to-end neural models are pretty notorious for hallucinating random, unrelated information or contradicting themselves and not being consistent, and also other related aspects such as being able to find salient information and so on. Then we'll also look at two aspects of robustness through adversaries, where they need to be both sort of stable to small perturbations that would not confuse humans, but also be sensitive to things that should change the meaning. And then we look at a little bit of how we can do this maybe automatically and also as human in the loop. And then finally, I'll touch a little bit briefly on more open-ended pieces like external common sense, reasoning graphs, proofs, touching into interpretability. So that will be the first part, and the second part will be shorter, maybe 30-40% of the talk on the multimodality side. But let's see how we go with time. So this is, like I mentioned, the first bullet that I was talking about is if we look at end-to-end neural language generation models, there's a big issue there, which is sometimes known as hallucination, or also you can call it as factuality, consistency, faithfulness. Obviously, all these terms have slightly different meanings, but for the purpose of this slide, what I mean here is that if you are, for example, doing the task of, say, document summarization, like on the screen, there'll be a lot of issues where the models would try to hallucinate things, which means that there might be things, as you can see on the screen, the red parts like John Hartson, Hampton Injustice, additional assistant Alan Muir. These are actually names and entities that are not even present in the input document at all. So this is obviously a short version of the input document, but if you look at the full input document that you need to summarize there, none of these names are mentioned there. And some of the sort of end-to-end deep learning models will still hallucinate these. And this is where the thing which we are calling as knowledge control or entailment comes in for tasks like document summarization, video captioning, sentence simplification, and so on. So since the last 4 or 5 years, around 2016, we started looking at some of these controlled elements back when end-to-end language generation models had become recently popular. So this was something we did in 2016, where we looked at the task of video captioning, which is given a sequence of video frames, you have to generate a caption describing the events in the video. And here what we said was that, okay, let's try to use the pretty old paradigm of multitask learning, where the main primary model shares parts of its architecture with different auxiliary tasks. And this shared knowledge, hopefully during training, helps the primary task learn some aspects of the auxiliary task. So in this case, the diagonal task is the main task, right? The video encoder going to the language decoder, video captioning. And what we did was, on the left side, we shared the video encoder across two decoders. So video would go to caption, but also the future part of the video. So it would try to generate the next maybe 20% of the video. And this was more from the visual robustness side, where this would make the system more robust to missing actions or being able to predict action completion at different frame rates and so on. Whereas on the right side, if you look at my pointer here, what we did was the decoder also shared two encoders. So this is known as a many-to-one multitask learning system, whereas the left side would be one-to-many. And then overall, this becomes many-to-many. And the idea here was that you are also sharing the decoder of the video captioning system with an entailment generation system. So we took things like SNLI and entailment classification data sets and tasks and converted them to an entailment classification task, where the idea would be that the decoder will then learn how to generate a logical subset of information in the encoder. So this was one example of multitask learning. And then we also looked at this from the reinforcement learning perspective. So in this case, as you can see on the screen, metrics like CIDR. So there's also a big issue with the metrics, right, for natural language generation. So CIDR is already one of the best consensus-based phrase matching metrics for something like captioning. But you can see here that if the ground truth caption was something on the left, the generated captions can be pretty absurd, right? Man is spreading some butter in a pan versus puppies is melting butter on the pan. The CIDR metrics will still be very happy. 140 is a very high above average score for CIDR. And the problem is that because 90% of the sentence matches the ground truth, so CIDR is happy. But one important word that changes or is wrong or hallucinated or contradictory could make a lot of difference. So what we realized, this was also 2016, and maybe sort of back then the idea that we used was that, okay, we need to make these metrics more directed and more controlled as opposed to undirected bidirectional match. And what we saw here is that something like an entailment classifier could come in to be more controlled and add a sort of element of factual consistency. And in this case, you can see that most of these scenarios, even though the CIDR will be very high, we can get a very low score from an entailment classifier, which is good because you do want something that can flag these issues with a low score. And so the simple thing that we did back then was that we modified CIDR with the entailment scorer and called it SIDENT, where CIDR, the CIDR score would get penalized based on how low the entailment classifier, how unhappy the entailment classifier was. And in this way, instead of using CIDR as a reward in a reinforcement learning system for a policy gradient system for NLG, you would use SIDENT as a reward. And hence it would not encourage these kinds of 90% correct generations. So I'll not show the result tables and so on because there's many of those, but the papers will have a lot of data sets, 3-4 video captioning data sets, human evaluation and everything as cited at the bottom of the slide. And I'm also citing previous related work and models that some of our work built upon. And so this sort of continued. So we addressed document summarization also through both multitask learning and reinforcement learning, where on the left side, you're seeing a model where it's a 3-way multitask learning system, where the middle model is a summary generation system. And then the left side, so the right side is again an entailment generation model, which is being shared with the summary generator. But on the left side, we brought in the idea of saliency, which is also another important aspect of summarization. And the idea here was that a system that knows what are the important questions to generate given a document will also be useful for summary generation, because a good summary should answer important questions about the document. And another sort of small innovation here was that you should have multi-layered maybe encoders where the layers closer to away from the input and output and closer to the center and the attention should be more shared, whereas the layers closer to the input or closer to the output are more low-level information and should be unshared across the tasks. So that sort of was one thing that helped. And then on the right side is more the RL version of this, where we were looking into how can you have multiple rewards in a policy gradient NLG system. So in this case, again, entailment was being captured by the SIDENT style idea that I mentioned, whereas saliency was being captured by another question answering system, where we could take something like SQUAD, like a span-based question answering system, and you would basically treat the answer phrases in a question answering data set as surrogates for something salient, because these are things that people are asking questions about. So we could train a saliency classifier based on these answer spans, and these could be run on the document summarization data to get surrogates for salient information. And then you would take CIDR and upweight it, or Rouge, sorry. So if you are having Rouge as a metric for summarization, you would do something called Rouge Sal, where not every word is being treated equally in the reward, but the more salient words get more credit for being correct in the output summary. And then the last thing we looked at, the third thing, was sentence simplification, which is another language generation task. And this time the middle task is sentence simplification. The right side is again entailment generation, because you do want, again, the output here to be a logical subset of the input. And then on the left side, instead of saliency, here we are introducing something like paraphrase generation, because sentence simplification takes a complex sentence and then it needs to both simplify it through some paraphrases while maintaining overall global logical entailment and meaning. And so here the idea, another idea we showed, was that different levels of layer sharing are important given the type of the task, auxiliary task that you're bringing in. So something of a low level task like paraphrase generation, which is more at the word and phrase level, seems better if you share it at the outer layers, whereas something that's more semantic and capturing global meaning of the sentence seems better to be shared among the lower layers. And then the last piece we brought in here was, let's also not try to have manual decisions here or human inductive bias in trying to decide the importance of these tasks. So in multitask learning, you are training these models alternately, with different mini batches. So instead of trying to tune these mixing ratios very expensively, we tried to build a multi-arm bandit setup here where each task was an arm, and then you would pull an arm, you would get a reward, and then you would try to maximize expected future payoffs based on the current training trajectory. So this could automatically learn the importance of each task as the training trajectory continues forward. So this converged into something called AutoSem in 2019, where we sort of expanded this not just for 2 or 3 auxiliary tasks, but this was a framework where you could have, say, 20, 30, 40 tasks, maybe glue, super glue, and you are trying to decide that for a given primary task, what are the best auxiliary tasks that would help your current primary task, right? So you can't really do all these manual sort of hand-picked decisions for across these 30, 40 tasks. So what you could do is a multi-arm bandit could be the first stage, which basically decides the 2 or 3 most obvious or most helpful auxiliary tasks to help the primary task. And then you could use a Gaussian process on the next step to be taking these 2 or 3 tasks and then learning their mixing ratio when doing multitask learning. So this actually ended up being very true to the intuition that we had, that we want to avoid inductive sort of manual bias. And one example, as you can see in the paper, is that suppose you're trying to improve a paraphrasing task, like MRPC in glue. If you had to make a educated guess with inductive, like with manual decisions, you would choose something like QQP, which is another paraphrasing task, and you would imagine that they might help each other. But in fact, if we let the model, the bandit, choose the auxiliary task on its own, it doesn't choose QQP, it chooses RTE. So this basically shows that given the dataset distribution differences and the vocabulary overlap, it's much easier for the model to decide this on its own using some sort of controller or bandit model, as opposed to us making hand-picked decisions. And the bonus that comes with this kind of bandit approach is that you could actually have some sort of interpretability that comes in here, because if you visualize the arms of the bandit, then you can get this dynamically changing task utility function, and you can visualize that, right? Because it's telling you that as you move over time, which auxiliary tasks become less versus more important during the training curriculum. And then the last example that I'll give in terms of sort of encouraging or forcing consistency or faithfulness in language generation was another work from last year where we looked at the task of question generation. So the idea here is that there's an issue called semantic drift in question generation, where the question that you're generating for a given answer in a context document may actually drift away, in the sense that it may not even answer the same answer that it was generated from. So that was the basic intuition. And this is why we brought in sort of a consistency reward or a back translation reward, or you can call it a round trip consistency, where you generate the question. So this is you can first ignore this top reward, but the second reward is basically you take a context, you have an answer that's marked in it, you generate the question for that context and answer. And then what you could do is the generated question could be fed back into a question answering system with the same context, and you can see how high the probability is of generating the original answer that the question was generated from. So this becomes sort of a reward. This probability will become a reward for the QG system in the policy gradient RL setup, where it will say, okay, I want you to encourage generating questions that get high probability for the original answer that it was generated from. And then the second reward was more a question paraphrasing based reward, which basically expands the space of the question generation system to be able to do some perturbations and match the correct question better. So that was more of a helper reward. And then you basically mix these rewards in different methods to be able to operate for better question generation. And another sort of important idea here was that when you're doing question generation, you can also use, when you're trying to do natural language generation, and we know that metrics are a big issue here. One idea that we discussed in this QG paper is that you could in fact evaluate QG using a downstream question answering system. So you could have a fixed question answering system and only the training data keeps changing. So you basically have a QG system that generates a synthetic QA data based on the generated questions. You can train your fixed QA system using that data, and then you can test it on a human-labeled QA dev set. So the higher that performance, hopefully it means the quality of the generated questions is getting better. So this is one way sort of to use a more consistency and downstream check to be able to evaluate your generated outputs. And then another way we evaluated it was obviously the more real use case, which is semi-supervised question answering, where you could bring in new documents, generate new questions, and create extra data for your QA system to be able to do better on real QA tasks. So this was sort of the first piece of how to do knowledge robust NLP. The other thing, as I mentioned on the first slide, is something that's very important, is what we know, what we call as adversarial robustness, right? So the idea here is that you want to be able to have systems that are stable to small perturbations that would not fool humans. And you also want your models to be sensitive to small but important changes that might look sort of unimportant, right? So this was a Connell 2018 paper for dialogue systems that we did, where the basic idea is that if you take some sort of strong state-of-the-art dialogue model and you say something like, I think I'm having a heart attack, and suppose the model is good at saying a good response, maybe it will start generating a definition of symptoms for heart attacks. But if you do small perturbations like paraphrases or even grammar errors, and if you just add something like, I'm afraid I'm having a heart attack, the agent basically can get confused very easily and say, my apologies, I don't understand. And then you could hopefully get a lot of this adversarial data, retrain the model, and then it should be able to go back to the correct answers. So this is 3 years ago, where we had the Connell system on being able to look at both oversensitivity strategies and overstability strategies. So like I said, oversensitivity means that these are changes that should not change the response of the system. So something like randomly swapping two words, or dropping a stop word, or some data level or model level paraphrasing, some grammar errors, right? So these are things that should not change the response. And overstability is an issue where the response should change, but the model doesn't realize that the response should change. Like, for example, if I'm adding a negation or the opposite of what I was saying. So this is what we did for this work, where we basically generated a lot of data, both with oversensitivity strategies and overstability strategies. So for adversarial training on oversensitivity, it's easy. You just add back this data with the perturbed context and the same response. Whereas for overstability, you do max margin, where you add back the, say, negation-based context or conversation history, but the response should be anything but the original response. So you add it as a max margin setup. And so with the simple adversarial training, you can do much more robustness, both in terms of automated metrics like activity F1, entity F1, but also human evaluation on different domains of dialogue corpora. And we showed this across 3 or 4 model types. And then the year after, we were interested in how do we not have to manually decide what kinds of adversaries are good for making your system robust. So one thing we've been looking at is how to do this automatically. So how do we automatically generate the best adversaries? So this is something known as an auto-augment model from Kubuk et al., which was more on the vision side. And the idea here for NLP would be that you could have, basically what you're trying to do is you want to learn sequences of adversarial perturbations or policies that could lead to much more advanced and complex adversaries overall. So maybe you say that, okay, one policy is that I'll apply 2 paraphrases, then 1 grammar error, and then 1 more paraphrase, right? So that can create a much richer perturbed sentence as opposed to just 1 paraphrase or 1 operation. So that's what this side is showing, that this is sort of like a RNN encoder decoder model, which will decide what's the operation type, grammar error versus paraphrase versus drop a stop word, and then how many times do we apply that operation and with what probability. And so basically this is what the controller does. It samples a policy based on these sequences of smaller operations. And then you can take the original data, transform that data with this policy, and then you can use this augmented data to retrain the model. And then the performance improvement on a held out validation set becomes the reward for this controller. So the controller basically gets encouraged to generate policies that lead to improvements on the validation sets after augmenting the data based on that policy. So Sojan, I'm not able to see the Q&A from my screen. So is it okay? Like, I'm assuming you'll let me know and I can continue.
Yes, so I guess 30 minutes for the talk, right?
Yeah.
So we still have few minutes, I
I
guess.
think we have 10 minutes. Yeah.
Yeah,
9 minutes.
sure.
Okay, yeah. So I'll continue and then I can take questions and then also on Slack. Um Yeah, so this is a more recent version of this auto augment setup where we did this for question answering, where many of you might be aware of the Jia and Liang style adversarial setup, where they showed that you can add a distractor sentence into your context of the QA model, and this will force the model to generate the wrong answer. So we created many more sorts of adversaries based on that, including our follow-up from 2018. And then also doing this for multiple sentences, and then also positive perturbations where the model should not change the answer, but it's just a paraphrase of a certain sentence that contains the answer. So this is another setup where you could use auto augment versus Bayes augment. So Bayes augment is a faster version we presented in the paper, which overcomes a lot of issues of speed and memory for auto augment. And the idea here was that we can also use this setup for cross-domain or cross-lingual generalization, where you can also try to, say, improve things like German or Turkish or Russian question answering models by being able to generate perturb data for them, even when you don't assume there's any training data. So you just need maybe a small validation set for this language to get a reward from, but the perturbations are being learned on the training data for English. So it gets pretty reasonably good improvements based on cross-domain and cross-lingual results also. And just to take this one step further, ideally, you could also imagine that in addition to learning these adversaries automatically, one other approach would be having a human and model in the loop interacting with each other, right? So this was the adversarial NLI paper last year with collaborators at Facebook, where the idea was that you don't want maybe the human annotator or mturker is interacting with the model to try to fool the model, and basically you would get very complex data that can fool, say, a BERT model, and then you would retrain BERT with that additional data. Then it becomes a more advanced model, and then another more advanced set of Turkers will write more complex examples that would fool this advanced model. And you can keep iterating this process till both the models become more stronger against adversaries, and also you collect data that challenges models more in terms of not being able to not just having a static benchmark, but a more dynamic benchmark. Okay, so this was mostly about the robustness part. The very last piece that I'll end with here is that there's also other open-ended challenges here that we haven't covered. So there's obviously a lot of things to think about in terms of common sense. So we've done just a little bit of work on this in the past, where if you have a document question answering system, can the model decide when, if it's doing multi-hop question answering, there's some missing reasoning gap, and it needs to go outside and bring external knowledge to be able to fill the gap. And we've recently at EMNLP this year had a proof generation paper where it's not just using common sense, but it also is structurally showing you the path or the reasoning graph of the common sense pieces being used. So basically it has facts and rules, and it can generate a graph along with the question answering system jointly to be able to show you what facts and rules in what graph order did it use to reach the answer. Okay, so let's, since time is a bit tight, I'll move on to the part 2 here, which is now so the first part we talked about was all text-based, right? So how do we do knowledge robustness and adversaries and common sense, where you're assuming that this is being discussed from the given documents at hand or knowledge bases or ontologies. Now let's look at what can we do if we can ground our models and have multimodality where they can also interact with things like images, videos, and the environment around them, right? So this is the idea here is that this will help them condition or ground, right? And be more consistent, be able to resolve ambiguities if they have the additional context of the visual environment around them. So again, I'll be able to only give a few examples here just to get everyone thinking about it, and then we can have more conversations. But many of you might already be working on these topics, so you might already be aware of all these issues. But the idea here is that, for example, if you're doing question answering, there are many scenarios, right? Even on something as obvious as Wikipedia, there are many scenarios where the question that you're asking will not just be answerable by the text, right? So on the top example, there might be something where some of the information comes from a map, right? The capital or the location, and then you have to go and use that information to go into a table and get the average precipitation. Or on the bottom side, you might need to know the family type of alkaloids and then go to the table to find the year in which they were introduced. So this was one initial attempt in AAAI 2020, where we released a many modal QA dataset, where given the question, the model has to first decide which modalities does the answer come from, and then it will decide to use maybe a text QA model versus a table QA model or an image QA model. We've gone to the video side of these things also with a lot of effort on the data collection side. So this is one of the largest video question answering data sets, which has 6 different categories and genres. And the interesting part here is that it's compositional, which means that we created questions in a way that the crowdsourcing, the crowd workers were forced to create questions that would need both information from the video and the dialogue subtitles. So it would be something like, what is X holding when he's talking to Y about swords? So first you need to go to the dialogue and figure out where is the talking about swords happening. And then in that timestamp, you need to go to the video clip of that start and end span and be able to then get bounding boxes and be able to figure out that this was talking about a computer or a laptop. And it can be vice versa, right? I mean, the first part could be based on video, and then you have to go and find the answer on the dialogue. Sometimes you have 2 pieces that are both based on the video or the dialogue, but it forces you to have joint models and fewer biases. And then we've extended this to retrieval and also future prediction, next event prediction data sets that you can look at offline, which have also been extended to other languages and more free-form videos like food bloggers on YouTube. And then the last 2 pieces, there are 2 slides that I'll talk about are some of the, not from the dataset side, but from the model side. So basically taking things like large scale pre-trained BERT models, but being able to make them more grounded in vision. So the cross-modal version of this, which we call LexMERT, and there were other, a lot of systems are there now. But the idea is that if you're trying to do vision and language pre-training, you would want to have something where, unlike BERT, which is just doing masking in the surrounding words and also sometimes next sentence prediction or sentence ordering, here you want to have 3 types of encoders. So there'll be a language encoder, an object relation encoder, and a cross-modal encoder that talks between the 2. And then the pre-training tasks will be much more diverse. They'll always be the masked language model, but there'll also be a masked object prediction model, both at the feature level and the label level. And then you'll also have things that do cross-matching. Given an image and a text, like the model has to predict whether they belong to each other or not. So this got a very strong improvement in several multimodal tasks, and also VQA, NLVR2, but things like VizViz, which is a very important use case of visual question answering, where people with visual disability take photos of things maybe in their refrigerator or in their pantry with their phone, and it's shifted and out of focus and out of frame kind of images, and they want to ask questions about what they are looking at. And so to scale this at an automated or human in the loop level, some of these models could be pretty useful. And then the last piece is from a different angle. So this is the vocanization work that was at EMNLP this year, where the idea is that how do we use mapping to vision for language or text-only tasks? So if you're trying to improve something like SQUAD, question answering, or MNLI, entailment, or SST2 sentiment, instead of using BERT, what we could do is we could try to make BERT map to visual information that the words in context would map to. So we call these vocans. And the 2 biggest challenges here were that we want to do distant supervision and contextualization. So the problem is that if you do want to learn this information, you need like the cross-modal data sets like MS COCO are very small, and they have much smaller vocabularies and smaller lengths of sentences. And it's very different from the text-only tasks that BERT would be trained on. So the first thing we need to do is be able to go from MS COCO to something like Wikipedia and get these vocans, the image mappings for all of Wikipedia. So that's the first step that this work does. And the second step that it does is that Wikipedia has less visual words. So how can you get vocans or image mappings for more and more words in Wikipedia? And that you would do through contextualization, which means that you would use information about surrounding words to be able to also guess what would be the image mapping for this other word. And then once you have these image mappings, you could basically retrain BERT, where BERT is not just doing a masking prediction of surrounding words, but it's also classifying which vocan or image does this word map to. So that becomes a vocanized BERT. And then these are the sort of improvements on text-only tasks that I'm showing on the screen. So maybe I'll stop here. I had one last example on an end-to-end robotics grounding task, where if you are given an incomplete instruction like pour me some water, this goes all the way from speech recognition and connect 3D image recognition to completing this incomplete verb frame from the surrounding environment objects that it finds, and then doing a sentence generation based on that to decide that, okay, pour me some water from the vase to the mug is more common than pour me some water from the plate to the spoon. And so it basically does common sense reasoning based on that, and then ends at the full motion planning setup. So this is some videos you can check later. And then just to sort of briefly conclude in half a minute, this was sort of some of the summaries of things that I discussed, but also what we need to look forward to. I think factuality and consistency control, hopefully I got the point across of how we made some good progress as a community, but there's still much more challenges to resolve, but also a very important challenge. We do need more transparency in our models so that we are not just using them as accuracies, but we also understand where they are going wrong, even if we think they are correct. This would avoid very important biases and unintended outcomes. The third point mentions that you don't just want interpretability, you also want to make sure that your interpretability methods are in fact doing the thing that they are intended to do. So we need to evaluate our interpretability methods themselves. So we have some new work on this at ACL this year. Like I mentioned for NLG metrics, I think human in the loop is obviously very promising. But another thing that could be promising is the QG example that I showed, where QG could be evaluated with both consistency or downstream QA performance. Instability is extremely important to look at, where we've been basically seeing a lot of reproducibility issues where the models, especially on stress tests, the smaller data sets, the models can be pretty unstable. And then the last two things would be low resource generalizability. So one of our recent benchmarks on the indigenous Cherokee language, which is endangered, only 2,000 speakers remaining, sort of is one example where it could cover both low resource generalizability challenges through multilinguality. And then the very last bullet is that grounding also needs to be broadened. So we are currently looking mostly at images and maybe a little bit of videos, but there's a lot of other things like haptics, touch, sound. Even sound is very sort of underused, and hopefully there'll be more and more of it and more of collaborations from the other communities. And also things like interactive haptics, where it's not just a static benchmark. Thanks. And then obviously thanks to the students who do all the great work. And there's some links for you to ping me at later on. And if you're looking for postdocs, definitely ping me.
Okay, great. Thank you, Mohit. I think, yeah, it was a great talk. I learned a lot of things. Thank you. Since the time is short, and so we just take maybe one question from the chat, and the rest of the questions.
And I'll answer the rest on Slack.
Yeah, thanks. That would be great. So Saili's question is the most upvoted ones I can see on Zoom. So what she is asking is like in this kind of system, whether it is always true that the systems agrees one example as a difficult example and whether the human agrees the same thing, okay? Or one example which human finds difficult to answer, but the system finds it very easy to answer. So I think her question is on that. So she is also adding, did something like this happen in the human in loop system? How was it dealt with? So what's your take on that?
Yeah, so I think defining what humans found hard is sort of a very interesting direction. So right now it was mostly focused on what models find hard. We did have a whole setup where the humans were allowed multiple turns to try to fool the model. So it would be, we were discussing like it would be interesting to use that information because we have it recorded, right? How many turns did they have to take to be able to sort of fool the model? So that could so like roughly estimate the complexity from the human side. So yeah, so I'm happy to take it offline with Shally, but it's a longer answer. But hopefully that answers part of what she means.
Great. I mean, do we have one more minute to just take one more questions? Like
Yeah,
the next
definitely.
question is also very interesting, which is also I wanted to ask. Like, so the question is, I noticed that for most multimodal approaches, the inputs are vectorized before being fed as inputs to the model. Is there more sophisticated way to encode context and other kinds of information? Yeah, that's the question.
So what would this, what would it mean by vectorized here?
So it means that I think pre-trained features for the inputs, like if you have 3 channels of information, visual, audio, and text,
Mhm.
you
Yeah, no,
pre-train.
definitely. I think, for example, if you're looking at something like charts and graphs and plots, right? I mean, that's another sort of modality that's becoming very interested in structured documents. So there you can bring in something more direct where it's more 3D coordinates and also information about the shapes and the edge detector systems, right? So we don't need to have everything as just vectorized. It could be more traditional features and also more structured features. And then also, in some sense, you could think of like even on the language side, right? I mean, if we bring in additional features, not just from charts and plots, but also more structured and other features from the language side, we don't need to look at these as vectorized.
Okay.
But if I misunderstood the question, then I can just keep continuing it on Slack.
Yeah, that would be great. Okay, fantastic. Yeah, thanks once again, Mohit. I mean, it was a great talk.
Yeah, thank you. Thanks for having me, and I'll stick around for a bit.
Thank you. Okay, Ganges sir, I think we should welcome our next speaker and start the next session. So yeah,
Yes. Thank you, Sojanya. Thank you. Thank you, Mohit.
Thanks, Gangeshwar.
See you here. Okay.
Okay, wonderful.
There we go. Can you hear me?
Oh yeah, so
Yes,
yeah.
you can.
All right.
So let me introduce the next speaker. Good morning, everyone, and good evening to Eric. It looks like the morning or so on your side. It's my great pleasure to introduce next speaker, Professor Eric Fossler-Lucier. He's from University at the Ohio State University, and actually Eric was in Singapore last year about this time as a chair of ASRU conference, and welcome back to Singapore in a year. So let me briefly introduce. I don't want to take too much time. It's only 35 minutes for the session. Professor Fossler-Lucier received a PhD in 1999 from UC Berkeley, and he has worked in Bell Labs, Luxent, and also Columbia University. He's also a technical leader in our field in speech and language processing. He's currently the chair of IEEE Speech and Language Processing Technical Committee. And he has also served in the editorial board of ACM Transaction of Speech and Language Processing, the Journal of Experimental Linguistics, and he was also the program chair for NACO 2012. Eric has done research, it's particularly interested in integrating linguistic insights into machine learning systems. So today he's going to share with us his recent study on low-resourced but long-tailed spoken dialogue system building. Okay, Eric, please.
Okay, thank you. All right, let me remember to share my computer sound because I have a little video clip here. There we go. Can you see that?
Yes, wonderful.
Excellent. Yeah. Okay. All right. Well, thank you for having me back. I really wish I were there in person because I had such a lovely time last year. Yeah, so today I want to talk a little bit about, I want to give you guys a story. And it's a story about partnerships. It's a story about Doug Danforth, who is at the University College of Medicine. And his job, in part, is to teach 200 medical students per year, or actually per class, there's actually multiple classes, how to do things like take medical histories. So students are evaluated in taking these medical histories and doing a differential diagnosis, basically asking a series of questions to the point where they get this differential diagnosis. They say, oh, well, I think you have this kind of thing going on with you, right? And the way that these students are evaluated is using standardized patients. So the idea is they hire an actor who has the same malady for every student, and they go through student after student after student. And you can imagine that this can get to be a little bit boring. And sometimes you get inconsistent things going on with the actors because, you know, they kind of want to hint a little bit at like, okay, you should be asking this question and stuff like that. But the main thing is it's expensive, right? You have to hire the actors and it takes a lot of time. And the question is, how do we actually make students better at doing this task, right? Well, practice obviously is the right answer. And so Doug came up with this idea of, hey, can I actually create a virtual standardized patient and then students can practice that medical history taking. We'll still use the actors to do the end evaluation. And what he did was he basically looked around and said, hey, look, there's this chat script by a guy named Bruce Wilcox, who is producing these Loebner Prize chatbot type things. And he says, we can use this. It's an open source system. So he worked a little bit with Bruce and also with ACAD, which is the Advanced Computing Center for Arts and Design, to develop an avatar. And they put together a system where Doug provided both the knowledge and also learned to write rule patterns himself, where Bruce gave the dialogue engine, and then the avatar came from ACAD. And Doug was able to put all this stuff together with a research programmer, and became sort of a little bit of a dialogue expert. So here's somebody who's trained in medicine, becomes a dialogue expert, right? So he's looking and he's saying, as I start to build out more and more patients that are like this, it gets a little bit more brittle. And he said, so he approaches us and Mike White and William Schuler and me over in CSE and linguistics, and says, hey, you guys do NLP, right? So how do I make this stuff more robust? How do I use this really cool, like neural NLP that I hear you guys talking about, right? And he says, oh, and by the way, I want to put a speech front end on this thing, right? And I know that you guys do speech too, so we're gonna have you do that. And I said, sure, we can do that, right? And I have to say that we thought, okay, we have this experience. I spent some time at Bell Labs building dialogue systems that did travel reservations. We can do this, right? No problem. And I think one of the things that I want to bring home in this thing is about what having that kind of partner who is not an expert in NLP can actually do for your research. And that's the story I want to tell today, is how that perspective of NLP folks is very different from the domain researchers who want to build systems for that task. Okay, the key thing is that we both really want to make systems work really well. And we spend all these times and, and we all do it where we're measuring like the performance of this thing, and we're going to do this incremental or this new technique, and we're going to see how much better it works on this task, right? Doug doesn't really care about the numbers. I mean, he cares at some level, but what he really cares about is that when he gets a bug, the students are knocking on his door and saying, hey, this doesn't work for me, right? And so he is very much in the, I'm going to fix it now because I can write a new rule pattern, right? And that kind of changed the course of research a little bit, right? And so in that particular case, that led us to building this hybrid approach where we still kept that rule-based system where the medicine team kind of improved that rule-based system, but at the same time, the NLP improved the machine learning-based system. And then we developed something to kind of switch off between the two. So a little chooser. And this kind of cropped up over and over again. So when we started putting the speech front end on this, right? One of my pieces of background is that I work in speech recognition, right? And so I thought, oh, we'll build our own speech recognition system. And actually I had this idea about how we can do some discriminative language modeling. And Doug comes along and says, I'm gonna hook up the cloud ASR system here and see how that works. And of course, the minute that happened, right, that was anything that we could build, that was better than anything we could build in the lab. So it's like, okay, what do we do with that? And so that actually changed our research direction a little bit too, in thinking about how to be the glue between the cloud ASR and the NLP system. So another interesting difference here is that when you think about building a dialogue system, you think about building a natural language generator as well. And that was actually explicitly mixed as part of our thing. The doctors need to have that quality control over the answers. They have a specific answer that they want to give for a virtual patient. And so when they're authoring these things, there's a specific answer. So, in some ways that made it easier because, we didn't have to do the natural language generations. Sorry, we didn't have to do any NLG, but it changed that perspective a little bit, and it was interesting. So the design of our system ended up being actually pretty much like a QA system. It's a very shallow QA system. In fact, we didn't really even have to go deeply into this. So I'll get into that in just a bit here. Okay, so here's the core problem. Here's how we're going to set up this problem. We have these students over here, and the student says to the avatar, "How can I help you?" The avatar then does a query and says, what's the most similar question to that, right? So there's about 350 question types. And yes, I do mean 350 question types that it knows how to answer, okay? And this is actually, this is a sort of, comes from the fact that we're using this chat script, and this is how this is kind of set up, right? So we're kind of working in tandem with the chat script and saying, okay, how do you do this? Now let's think about those 350 questions, right? There's a lot of examples for some of these questions, like, how can I help you, right? But there's some other questions like, are you nervous, right? For which the student, maybe it said once, right? So, there's this long tail, it turns out, of questions, like a number of questions that we do really well on and a long tail that we don't, okay? So once we have that figured out which answer is the correct one, we send back a canned response, and that comes back and says, oh, I was hoping you could help me with my back. And then, are you feeling pain? Yes, it's been hurting for a while. And eventually, after you ask all these questions, you come out with a report and says, oh, you've covered these 4 out of 23 categories or something like that. So let me give you a quick, before I do that, the main point of the technical part of this is that in building up this system and thinking about it, we ended up with this really long tail and low resource situation. And it's really odd because you have to decide between 350 different classes, but you don't have a lot of data, right? And to make it worse, they said, okay, we're going to put a speech thing in. Now we know the speech recognition is likely to make some errors, right? So, how do we adapt to that when we actually have never observed any speech data for this and we only have text data? So we kind of worked on some technical solutions to that. All right, so let me give you a quick demo. This was actually recorded this morning. So this is the current version, and this is Mr. Rodriguez.
Hello, doctor.
Hello, Mr. Rodriguez. How are you today?
Generally pretty good, except for this back pain.
Where does it hurt?
It is mostly in my lower back.
How long has it been hurting?
I want to point out at this point, just to stop for a second, and one of the interesting little user interface tricks that we ended up doing, we played around as moving from a chatbot to a speech bot. We actually originally had the speech transcript coming out here, along here, and we found that students found that much too distracting when there were speech recognition errors. So we found, but if we didn't put anything, it didn't know if we were listening or not. So we have this little ... thing going on there, which I thought was kind of an interesting solution to this problem.
Almost a week, I think.
Have you been taking anything for the pain?
I have been taking ibuprofen for a few days, but that is not helping much.
So sometimes the avatar looks a little freaky here. So so you get this little answer, like, here's what you filled out at the end. I'm going to zoom in on one little bit of it. This is the end of this. And you can see that I didn't ask any of the social history questions. So it knows how to categorize questions, and it says, you know, you did ask this question, right? And the idea is that this gives the feedback to the student to say, oh, okay, you next time remember to ask about the person's physical activity, right? That kind of thing. So the other thing is you can actually see what the actual speech, the actual speech recognition output was there. Okay, so let's now, how did we get involved when we built the system? Basically, when Doug came to us, the chat script system was basically built on an iPad. The avatar sits on the iPad. Text questions came in and canned replies came back. And so the first thing that we did is to say, hey, what we were kind of looking for is sort of like little n-grammy type things. So we said, okay, let's build a convolutional neural network, and we'll use that to kind of do a prediction of the response. And I'll show you a picture of that later on in the thing. And then this chooser that I talked about says, oh, do we use ChatScript or CNN? And actually, interestingly, in order to get ChatScript to kind of keep its context up to date, what happens is if it chooses the CNN, it actually feeds the sentence from the CNN into ChatScript and then gets the response back that way. So, okay, so the next bit is then said, okay, we want spoken questions now. So we're going to feed this to a cloud speech recognition system. We've used a couple over the course of the years. The problem is that these are going to generate errors, but we don't have any speech data to know how to adapt to that. So what we did was basically say, how can we collect a set of errors that can actually allow us to take text and create effectively pseudo transcripts, fake speech recognition errors, right? And use that to augment our training data. Meanwhile, and work I won't talk about today, we're also looking at augmenting our training data by doing paraphrases to help. So that's actually Mike White's group is focused more on that part of it. Some of the same ideas that Moet just presented in his talk sort of apply it there. So, okay. And then we turned our attention to handling rare classes a little bit better. And so two models that we've looked at that I'll talk about today are an RNN with attention and also some pairwise models, pairwise training models. Okay. Now we've put that into place, and maybe someday with enough data, we can actually just get examples from our collaborators in medicine, and generate these things if we can use just sparse data. Okay, we're not to that point, but that's maybe someday, right? Okay, so just to give you an overview of what the convolutional network is, the input is originally a typed text sentence. And the output decision is one of 59 classes, and that classifier basically looks at unigrams, bigrams, and trigrams over a sliding window, and then does basically a max pooling operation on top of that. It's a very simple classifier, okay? And it turns out to be not as good as the rule-based system, but it works differently. The rule-based is better actually on rare classes. So when we started talking to people about this, they predicted, oh, the CNN is going to be good because it's general, and the rule-based system is going to be very, focused on particular sentences. And it turned out that no, it was exactly the opposite. The rule base is actually pretty good generally. The CNN is actually good when you've got enough data to train it. So in fact, one of the things is we've gotten more and more data over the years because we get another 200 students coming through the system every year. So we get more and more data every year. One thing I want to point out is why is this a tricky problem, right? The differences in these classes can be very subtle. So one question might be, are you taking any pain medications? And the answer to that is not right now, okay? Did you take any pain medications, which is an aspect difference, right? Or a tense difference, right? I took some ibuprofen, but it doesn't seem to help, okay? So even though, both of these are talking about pain medications, these questions are very subtly different, but they're important in, in their differences, okay? So I want to talk a little bit now about speech because I am a speech guy. So I want to talk to you about hello Oreo, right? This was an actual input that went to our system and we kind of went, what the heck? And it turned out that when we went back and listened to it, what was really being said was, hello, how are you? Right? But the thing is that these two things are pretty close phonetically, hello Oreo versus hello, how are you? But you wouldn't actually predict that they were gonna, come out, right? So the question is, how can we do this kind of prediction to do data augmentation? And the idea is we're gonna use the idea of phonetics to help us out here, right? First of all, let's try and figure out how bad is this problem, right? So we didn't have any existing speech data, but we just had the text chat as our training data, right? So what we did is we read a subset of those transcripts. Now this is read speech, so this is not as difficult as when you're doing conversational speech, but should have some problems. And it turns out that you get 4% absolute more semantic errors. You go from 69% down to 65%, okay? So the question is, how can we actually try and recover those errors, right? So we had two basic ideas. One is if we can imitate how a speech recognizer would behave on that text data, maybe we can generate those pseudo transcripts. So that's the idea that I talked about before. Okay, so just formally, you're given a text transcript and a recognizer with some arbitrary speech data predicts speech recognition transcripts from those text transcripts. Okay. Second problem or second idea is to say, we've got a system that knows how to deal with typos because sometimes the people type in things incorrectly, so we put a character-based system. But if we can basically make the system understand how words sound like each other, maybe it can do that disambiguation. Okay. So, how do you train a system how to predict likely speech recognition errors? And this goes back to some work that I and a number of other people have kind of looked at over the years. Our original idea back in 2002 was basically in the service of trying to get more data for a speech, for a language model, a discriminative language model, okay, which we needed speech recognition errors for. And the idea is that you're going to take pairs of transcripts. Correct transcript was the average rate, and errors-full transcript is disaster trade. This was something that one of our noise robustness experiments and for Wall Street Journal actually produced. And it turns out that the reason why is because that V is very low energy, and when you get noise, it masks it, and then all of a sudden everything goes to heck, right? So you get disaster trade instead of the average rate just because that one sound is not present, okay? So, but maybe we can collect enough of these examples of these kinds of misrecognitions, we can get enough data to generalize. So that's the idea, okay? So what we do is we collect data from a speech recognizer and we say, oh, okay, what are the sounds, the sound-to-sound transformations that we have. And the original models that we had were very sort of smooth in the sense of that we learned essentially a confusion matrix and basically just used that to project what are the likely sounds. And this worked really well back when all of our ASR systems were very much in the Gaussian sort of way, because the Gaussians also kind of have smooth overlap models that in acoustic space. But it turns out that as we've now moved to deep learning, right, to produce posteriors of phones, for example, right? Those when it makes a mistake, it is making a mistake that's very spiky, that it is very sure that it is this sound that it is very wrong about, right? So it turns out that we learned that it was better to sample these types of errors instead of actually predicting this smooth kind of thing, okay? So we now use the sampling technique over and over again in a number of different things. We also, one of the cute things about this is that we actually took something, we figured out errors that are happening with our switchboard recognizer, which is just telephone conversations. It turns out that even if you just use that as a model and you then apply it over here to a completely different recognizer, a completely different domain, right? Cloud ASR, virtual patient domain, we're still predicting half of the errors if you give us 100 guesses, which is pretty good. Actually, it was very surprising that it actually worked at all. But it means that there's something general about the way that people, that machines and probably people misrecognize words, right? And that has to do with the phonetics of the situation. Our best performing system to date basically takes that plus a word-based transformation system where you transform the sky into this guy, and you can actually predict speech recognition errors pretty well. So what happens if you actually try and put this into a system? Okay, so two things. One is that the second half of the story that I was telling you is that to deal with this sort of typo, but the phonetic typo system, we actually introduced a phone CNN in parallel with the word CNN. And that actually gets us a good chunk of so remember, we went from 69% on text to 65% on speech. When you add in the phone-based system, you get some of that back, and then you get a little bit more when you add these pseudo transcripts in. So it turns out that you can actually recover about 60% of the errors. That was pretty good. We were pretty happy about that. So, and we've seen other results that kind of confirm this in later versions of the system. All right. In the little bit of time remaining, I want to talk about the long tail. So as I said, you've got 350 classes, right? Some of those are frequent, some of those are infrequent. That rule-based system is very good at answering rare classes. The CNN is better at but the question is, how can we improve that? Well, one of the things that we noticed is that going back to that example that we were talking about before about, are you taking medicine or, did you take medicine, right? So there are overlapping pieces of those that maybe we can reuse to build up knowledge about rare classes. So we built an attention model that was actually focused on extracting parts of rare classes to help with classification. And then we introduced some a little bit of few shot learning, what I'll call, with pairwise training. So let me talk about both of those. So one thing is we built an RNN model that basically says, oh, okay, we're going to take an RNN style. This is a GRU that says, how are you? And attend over the outputs of these things. Okay. And then there's weighted summing all the way up, right? And predicting, right? What was interesting about this is that by doing this attending, we did actually find that we were getting better on rare classes. What we end up here is these are the quintiles of the question classes essentially, and you can see that our accuracy goes up quite a bit here. 10% on the lowest class. We get a little bit of degradation on the most frequent class, not enough to really make a difference, and a little bit of gain here. So that F1 score actually goes up quite a bit. The accuracy is about the same. F1 goes up quite a bit when we do these kinds of things. But the things for me that was really kind of cool is that we can take a look now and look at those, what are those attention heads doing? And this was one example that came out of Adam Stiff's thesis, where he's looking at three classes that are pretty close. Do you drink caffeine? Do you drink? And do you drink water, right? When you say, do you drink? The implicit thing is that you're drinking alcohol, okay? Right, so interestingly, when you start looking at the patterns of activation of the attention head, right, there seems to be a pattern that is around drinking and there's a pattern around caffeine. And when you've got, or what it is you're drinking, right, And what we're noticing is that these things are attending to, when you just have drink with no argument, all the heads attend to that drink, okay? And the patterns turn out to be, of that activation, turn out to be very similar here as with alcohol, right? Whereas you get very different patterns for water and caffeine. Okay, so that was kind of nice. You can inspect these kind of things. And I know there's a long running argument about, attention is not an explanation, but I think what we're seeing is that we're seeing some ability to do some inference of argument structure, which is kind of nice. That's not something we coded in. That's just what fell out of the model. So the other thing that we did was to change how we trained things, so that can also help. So one of the things, so the previous model was pretty much monolithic. You took in a sentence and you produce a classification. Here we're actually saying, okay, look, I'm going to produce some sort of representation, right, that I'm going to use, and then I will mix them up and then try and detangle them using a classifier saying, oh, you have these two classes going on. So this is called mix-up training, pairwise mix-up training. And it turns out that if you do two things, one is to basically make those representations of the same class closer together than the ones that are further apart, at the same time as requiring the system to create representations that can be classified and disentangled. That turns out to be much more effective in particularly for rare classes. And we did this actually with our original CNN classifier, the self-attentive RNN, and BERT, which we had never been able to get to work for this because there's never been enough data to get BERT to work on this task. And it turns out that if you look here on the virtual patient data, which is the relevant bit here, that you actually get that same sort of nice performance that the pairwise F1, and this is a slightly different data set if you're wondering why the numbers are not quite the same. On the bottom quintiles, you get quite a bit of gain, and in fact, again, you get just a little bit, basically the same performance here. So these are the F1 scores as opposed to accuracy, but same idea here. And so it turned out that our BERT system now gets about 81% with F1 at 67, and our original CNN way back when, got 76% and 51% F1. So we're getting large gains now in F1 and nice accurate classification accuracy, but that's in part because of change of model and whatnot. So, okay. That is all I really wanted to tell you, but I wanted to sort of say, bring us back to like, how did we get here? So we got here because we started this partnership with a partner who really, was coming from outside the academic tradition of oh, we're going to measure the differences and whatnot, and basically had this sort of like, I need to fix this problem attitude. And that's great, and so that allowed us to build these hybrid models that allow teams to work independently, and it gives us new ways of thinking about those problems that incorporate these end constraints that they have, right? So it has to work with speech recognition. It has to produce these particular outputs, right? So that evolution itself created an interesting set of problems that were a combination of both being low resource and long tailed. Usually if you have low resource, there's not a lot of classes of the thing that you're trying to do. But we're actually, there's a wide space in here and we don't have a lot of data examples of each one of these. So it forces us to think about new ways to augment the data that we're doing and to train models. So that's all I wanted to say. And a big thank you to all the grad students who were really the people who do all the work when you come right down to it. So thank you very much.
Okay, thanks, Eric. Wonderful talk. Let me see whether there's a question. Any of you have questions, you can post on the Q&A panel. I don't see yet. Maybe let me ask a couple of questions. So Eric, I was very impressed by the speech error correction network. I think there's interesting way of overcoming the problems. But I would like to know if in your study you have seen, well, some make good corrections and some make bad corrections. They turn correct results into errors. What was your observation on that?
Yeah, okay. So in fact, we explicitly didn't do error correction, although this is something the model that we presented could be done that way. Like we could have, but we in fact did the other way around, which was we took correct things and we generated errors. And then we fed those into our training set to create robustness.
Okay.
And I think
that augmentation.
Yeah, right, exactly. So we're doing a data augmentation approach. But your point still holds, okay? Because the thing is that if you just dump a large number of examples into the set, you turn out to skew the data in various ways, okay? Because you change if let's say instead of having, for every example, I generate 5 errorful examples, right? All of a sudden now, instead of having this long tail, I've now raised everything by quite a bit, right? And it changes the dynamics of those of the classifier. And so what we ended up doing was this interesting sampling technique where we basically said every so often, instead of training on the true thing, we'll actually just grab the errorful one, and we'll do that basically based on how likely it was to be errorful. And it turns out that was the best strategy that we've found so far for incorporating this. We're using that for paraphrases. So
Q&A panel for some questions from the audience. So one question is on how the rule-based system is integrated with the NLP system. I think
the
rule-based system works well. Yeah.
Yeah, the machine learning problem, the system. Yeah, so actually we let them run independently and each give their own answer. And then the chooser goes and basically looks at the question and says which question and which category, and it takes into account the answers that come back. Which system am I more likely to believe? And one of the chicken and egg problems that you get in that is that as you improve one of the systems, then all of a sudden you have to retrain the chooser, and then it gets into this big question mark. But basically, we're only doing the combination on the answer level, which that's a nice thing that we are allowed to do because we basically are doing a classification problem. So
another question is on why didn't BERT work?
Yeah. Okay. So we have a couple of insights on that. First of all, there is a big domain mismatch between what BERT was trained on and asking questions of a virtual patient, right? But fine tuning should help with that, right? But it turns out that, this is the low resource problem. It turns out that BERT to fine tune BERT, at least in its full form, right? There are distilled versions that maybe might work a little bit better, but in its full form, to fine tune BERT, you actually need quite a few sentences. And we basically had like a couple thousand, right? Which was not enough to really move the needle for BERT. It didn't work horribly, but the RNN still beat the heck out of it. So, but once we actually started this pairwise focus, this seemed to help. And we're still trying to understand the why of that. So,
yeah.
So that's a to be determined.
Right. Good. So, well, in the interest of time, I think we have to conclude the session. Thanks, Eric, for sharing with us interesting experience in developing real-world systems. Yes, I would like to pass the floor to the chair of the next speaker. Thank you, Eric.
Thank you.
Thank you, Eric. Thank you.
And I will be on Slack if people want to ask questions.
Okay, that's great. Thank you. Okay, I'm going to invite Professor Alessandro and Professor Weigao. All right, they're here.
Hello. I cannot
Hi.
hear. Wait.
Hi. Hello. Hi, Alexandra. Can you hear me?
Hi. How are you?
Cool. I'm good. Thank you very much for accepting our invitation. Okay, so good morning, ladies and gentlemen. I'm the chair of this session. My name is Wei Gao from Singapore Management University. Today, we are very happy to have Dr. Alessandro Moschetti from Amazon to give us a talk. Let me first briefly introduce Alessandro to the audiences. Alessandro is the principal scientist of Amazon Alexa, leading the research on QA systems since 2018, and professor of the computer science department of University of Trento, Italy, since 2007. He was a principal scientist in the Qatar Computing Research Institute, QCRI, for 5 years. He was a visiting professor in the University of Columbia, Colorado, Johns Hopkins, and MIT, and a visiting researcher for the IBM Watson Research Center, participating at the Jeopardy Challenge. Alessandro is a top expert on theoretical and applied machine learning in the area of NLP and IR and data mining. He has been working on the innovative structured kernels and neural networks for syntactic and semantic processing and inference over the text. He has received many awards, including 4 IBM faculty awards, on 1 Google faculty award, and 5 best paper awards. He has led about 25 projects, including MIT, CISO, QCRI joint projects and European projects. He was the general chair of EMLP 2014 and chaired more than 50 conferences and workshops. He has been an acting editor of TACL, and currently he's the acting associate editor of the ACM Computing Survey and JIR, and in the editorial board of the Machine Learning Journal and Journal of Natural Language Engineering. All right, without further ado, let's welcome Alessandro to deliver his talk, and the topic is advances in question answering research for personal assistance. All right, Alessandro, please go ahead.
Thank you very much for your warm and detailed presentation. So I'm sharing with you my screen, right? Okay. So today I'm going to, first of all, thank you very much for inviting me to this workshop. It's very nice. I would have liked to be there with you, but for the moment, this is what we can have, and we should enjoy it. So for today, I have prepared this presentation on some recent advancement in personal assistant. This, of course, is connected to my research in Amazon Alexa. Yes. Okay. So basically, we know that the personal assistant nowadays have a renewed interest for question answering. There are powerful virtual assistants like Google Home, Alexa, Siri, and so on. So the question is how they can exploit QA. What are the challenges? How can we build a question answering system that can be optimal for personal assistant? So in this talk, I will give you a background on QA. We introduce, in particular, retrieval-based question answering system. And I will focus on basically the most important task, that is answer sentence selection. And I will show you some advancement that also with my team we performed using transformer-based model. And in particular, I also will show some improvement in accuracy, but also in efficiency to make a transformer technology suitable for a real-world application. Finally, I will derive conclusions. So let me start with a light and modern question-answer architecture. I have only 30 minutes, so I cannot show you much about the past and the challenge with IBM. That was a quite complicated system that required, if you use only one machine, it required 15 minutes to answer a question. So we don't have the luxury to serve millions of users with systems that have this cost requirement. So we need to have something lighter. A light and modern architecture can be something like that. So suppose that a user asks a question, what is Mark Twain's real name? You can use a search engine to search your local database or maybe also the web. So your search engine retrieve a set of documents, then you have some processing of the documents. You want to segment them in a paragraph or, as in this case, in sentences. And then you will have a rank of the sentences returned by the search engine that will be something like this. So we can have a couple of sentences which are relevant to the question, but the first one is actually, it's another question, so you don't want to answer a question with another question. The second is basically roll over Mark Twain because Mark McGuire is on the scene, so it's lexical similar to the question, but is incorrect. And then let's suppose that the real question is lower in the rank, for example, in position 16, Simon Logor Clemens, better known as Mark Twain. So what you would like to do now is, given this set of candidates, select the right candidate. For this, you need a passage ranker. Passage ranker is a model that can reweight, or based on the probability of each answer, the rank of the candidates. So such that hopefully in the first position you will get a correct answer, and then you can use it to provide it to the customer. This task of re-ranking sentences, sentence candidate, let's say answers candidate, is called answer sentence selection. And formally, basically, you have a set of sentences. You want to define a function that give a question, and a subset of sentences return your target answer. This function basically can be implemented with an argmax of a probability of the answer sentence candidate. So at the end of the day, to make it short, what you need is to estimate the probability of correctness of a sentence given the target answer. So how can we estimate this probability? Modern systems use neural networks. So what is the basic approach? There are several ways to estimate the probability of an answer to be correct, given a rank. One of the simplest one is the point-wise approach. And this is basically a binary classifier. So very simple and very efficient. The binary classifier can be trained with question-answer pair. You will have a correct question-answer pair we saw before once, like what is Mark Twain's real name? Someone Logor Clemens better known as Mark Twain. And then we saw also other incorrect pairs. If you provide binary classifier with this kind of training data, then you will have as a side effect the probability of each pair. And the probability of each pair means the probability of each answer. So this is the main idea. Let's see what is the state of the art that we have had until now. So I could present also something regarding track competition, but let's speak about something a little bit more recent. So this is a task that was quietly contributed since 2005, 2007. So here we could see traditional old machine learning model, quasi-synchronous grammar, three-edit distance, probabilistic model, CRF, SVM, and other lexical semantic model. Since 2015, neural network started to appear in NLP, at least massively in NLP, so in all, even in question answering. So we have the first model based on convolutional neural networks and also on some forms of attention. So here I report some of the papers that have been developed since 2015 to 2019. So this slide misses a lot of previous work. This is just to make you understand that the answer sentence selection is a task contributed by hundreds of researchers. So as an example of early neural model, I can talk about our neural network because it was one of the first. The idea was pretty much simpler. So you build a sentence model using a convolutional neural network, for example, and similar convolutional neural network can be used to build the question representation. Then you have these embeddings. You may use another matrix to compute another feature. But the end of the day is that then you join the embeddings in a fully connected layer, and then you will have your binary classification task. So this was one of the first methods. What is interesting to stress here that even if our early model was quite simple, we already introduced something that was interesting. So we added to the representation of the question, or it also to representation of the answer, these additional embeddings for each, for example, question word. And the embedding was used to signal the network that there is a match between the answer and the question. For example, here there is a match with the word cat, so we signal this with 1. This was actually very interesting. It improves our performance of several points, and was very interesting because after that, attention mechanism started to appear, even in answer sentence selection and question answering. And so, for example, was proposed the compare aggregate model. The compare aggregate model is something like you build a classical attention matrix. This basically tell you what is the best match between the question word and the answer words, so that you build the matrix H, which is the best representation of the question words, given the weight that you have computed before with respect to the answer. So after you have the best representation of the question, what you can do is to build the representation of the pair, so both answer and question. So you can compute the component-wise product between words representation of the answer and this attended representation of the word representation attended by the answer. And as a result, so then you have this representation of the pair T1 TA, so all these individual vector, on top of which you can apply a convolutional neural network to create many more combination and features between the pair embeddings. Okay, this was the state of the art in 2017. Then in 2018, something interesting started to appear. I would say that in machine translation appeared already in 2017 and was the transformer model. The transformer model was basically used to encode and decode the text. But after, so in 2018, it started to be used just as an encoder, mainly. And the main idea of the transformer is that you have several blocks like this, are simple blocks constituted basically by a multi-head attention a layer normalization, a feed-forward layer, another normalization. So in 2010, BERT came out. We had an architecture with 12 blocks like this one that I'm showing, or in the large version, 24 blocks. So this is a huge neural network and need to be trained. Fortunately, the author came out with an interesting approach to train the transformer, and this is called the pre-training language model. So basically, you can give an input, a text to the transformer network, and this text can even be separated in sentences. But the main idea is that you can mask some of these words, and then you try to reconstruct the word, so to classify, to predict the words at the output of the network. Basically, in this way, you build an artificial task, and you can be, let's say, you can train the network with a huge amount of text because the label is obtained for free. Roberta is an improvement of BERT in terms of parameterization. Instead of static masking of the input words, you can apply dynamic masking. It always uses full sentences. They removed the sentence prediction task, and then they are using large mini batches. So once you learn this huge language model, basically you have a network like this, so a block repeated many times. Now you can just select the representation of one of the tokens, for example, the CLS, which is the starting token, and then you just need to apply your classifier. In case of answer sentence selection, we just need to add a binary classifier, so a linear layer will be more than enough. So for ranking sentences or answer sentences with transformer, the idea is the following. Suppose to have a contextual language model. So I show you the transformer, but there are other alternatives. You provide a question answer pair, and you see that you can provide it separated by a separator, an input to the transformer. And then what you get, you will have for each of the pair representation a score in the produced by the fully connected layer. So you see that the intermediate candidate got the highest score, so this will be the answer that you can give to your user. Until here was basically the baseline. Our first contribution to improve this approach was exactly the same observation that in the previous talk Eric pointed out, that BERT was pretty much stable. Imagine this was we tested at the beginning of 2019, half year 2019, and it was not much clear how to get stable models, especially if you have small training data. So our idea was that, okay, but why if we divide the fine-tuning of BERT into steps? One, we call it a transfer, and this is mainly supposed to transfer to the task, because you start from a raw language model, and then you want to transfer to a task, for example, question answering task, answer sentence selection. So after you transfer this, and you can use any data set for the task, which is enough large, then you can adapt the task to your specific domain, and we call this the adaptation step. We published this paper in AAAI this year. So let's see what is the effect of this simple first transfer and then adaptation. And I will show you some experiments. So for the experiment, we use the traditional data set, VQA and TrackQA, that I show you are used in all other papers. And as you can see immediately from this slide, I don't want to go deeper, but basically the data sets are very small. So fine-tuning directly on them doesn't produce the top results. Here, another interesting idea that we had is to build a data set that was possible to use as the transfer step, so a large intermediate data set. For this, we use a data set from machine reading. And the main idea is that machine reading as a question, document, long answer, short answer. We mapped this directly in a question answer sentence. I give you the intuition very quickly because otherwise I believe I will not have time for the rest. So suppose that this is a piece of text of Wikipedia with the Google NQ annotation. Google NQ annotated the target answer, short answer. For example, what is the highest mountain in France called? Mont Blanc. Okay, this is the right answer in the right sentence, in the right long answer, which is the entire piece of text here. And since the sentence contained the right short answer, we labeled as a positive answer sentence. All the other answers here either don't contain the short answer, that is Mont Blanc, or the short answer here is not exactly annotated by the annotator because, for example, this sentence, the Mont Blanc massif is popular for biking, skiing, and snowboarding, doesn't answer the question. So the annotator did a good job. We are exploiting the good job of the annotator. We are annotating all these other cases. For example, here you don't even find, this is not again, is not the right sentence as annotated by annotator. This doesn't contain not even Mont Blanc. So we could exploit machine reading data set to build an answer sentence selection just for using as a transfer step. What are the results? Well, first of all, we take as a baseline the best model of 2019. This is compare aggregated I showed you before, plus Elmo embeddings and other pre-training. So this is a strong model. But then if we use our approach, especially with Roberta Large and with a step of adaptation and then a step of transfer and then a step of adaptation, as you can see, our improvement is massive. This is correspond to 50% of reduction of the state of the art. To give you an idea in perspective of the research, this are the system performance during this year from 2015 until now. Our contribution is this one for the WikiQA dataset, or for Trek dataset. You can see there were several improvements during the year. We had another massive improvement. So basically, this transfer and adapt technique works quite well, and I can give you some real cases of the question answering. So, for example, an easy question would be, who is the character Don Quixote? Any system, good system, could answer this using maybe also knowledge graph. But then it starts to be a little bit more difficult, the following question. What is that Spanish character had a problem with windmills? And our model can pretty much interpreting this question like the fictional character Don Quixote is famous for thieving at the windmills. Another interesting observation that we can also answer non-factoid questions. For example, why did the Don Quixote attack windmills? The hero attacked windmills, believing them to be giant, making his name a big word for attacking imaginary enemies. So basically, the transformer model is working quite nicely in matching the semantic of the question with the one of the answer sentences. Okay, there are also other examples, but I better move on the next topic. We proved that transformers are great. Everybody's using them. So this proof is supported by many other teams. The problem is that the efficiency is low. Transformers are heavy. So for example, if you want to process 100 sentences, you may require 200 milliseconds with a GPU, an entire GPU. So imagine if you want to apply transformer to millions of questions, the cost will be too much. There are indeed some effort to distill transformer such that you use a smaller architecture, and there was some effort also with Albert to reduce the parameters. What we propose is something orthogonal to this approach, meaning that you can still use distillation, but this is a little bit more rooted on the IR research. So basically, the transformer model needs to process a large set of candidates to come out with one candidate. You can split the problem into subtasks. First, you have a re-ranker, which can be pretty much fast and cheap, although not much accurate. And then you still keep using the transformer. But now the transformer will be used on a reduced number of candidates. So we published this paper in SIG-IR. The model can be generalized using n re-rankers with different accuracy and different efficiency. I don't insist too much here because I want to go in the last part of the experiment and then the last topic. So we consider several re-rankers, also the Jacquard similarity, which is a standard unsupervised way to rank text. We used also, we extended also the data set that we proposed with more candidates, because on average, we had only, let's say, still large, but 354, we extended to adding more noisy candidates until 1,300 candidates. So here is exactly what I was telling before. The line is the performance of transformer model applied to all candidates, and this is the upper bound. Then if you use a re-ranker and feed the transformer just with 100, 200, 300, 400 candidates, you see that the performance little by little increase if you use Jacquard similarity. But then if you use a powerful model, like for example, compare aggregate, which is very fast, but also powerful, you just need less than 100 candidates to reach the same performance of the transformer using 500 candidates. So basically, the idea of using sequential re-ranking is very appealing. To quantify in terms of numbers, BERT may take more than 5 seconds. The sequential re-ranker take only 1 second. So you improve almost 5 times. Finally, using these different networks is interesting, but actually, since we are applying transformer, there is another possibility to build sequential re-ranking. You can build sequential re-ranking directly inside the transformer. So basically, this is the monolithic model. Sequential re-ranker allow you to cut some part of the computation. Our idea is to go linearly, block by block, and reduce the computation. I will show you in the next 2 slides the idea. So basically, this is the cascade transformer, classical, for example, BERT base with 12 blocks. What we do is to add a partial classifier after a certain number of blocks. We start with the first 4 blocks because here we need enough power to do a good job at the re-ranking with the re-ranking task. But then you can just put another classifier each 2 blocks. And the way in which you train this architecture is basically you select one of the classifier randomly, and then you back propagate with respect to the classifier that you have selected. So basically, it's a kind of round robin training of the transformer. So very quickly, what is the advantage? If this is the monolithic transformer, you have 100 candidates, you pass through the blocks all the way down until the last blocks. So you have 1,200 computations, let's say, block computation. Instead, with the cascade transformer, you pass the first 100 for the first 4 blocks, but then you reduce, for example, 30%, and then you reduce again 30%, and you reduce 30%. So at the end, you have only 25, and the total reduction will be 37%. So basically, you integrate a sequential reranker within the transformer. So how much time I still have?
You still have maybe around 5 minutes more.
Perfect. So, okay, so let me briefly discuss the results, and then we can go to the QA. So for the setup, we use more or less the same data set of before: VQA, TrackQA, SNQ, also an internal data set, and standard precision at 1, MIP, MRR, and DCG. So we compared the standard transformer, which is 12 layers, and we call it monolithic to stress the difference with the cascade. So we compare against that, and also against a sequential reranker, this time built with the transformer technology only. So no compare aggregated that can be very fast, but just transformer of 4 blocks, 6 block, 8, 10, and 12. So first of all, we want to see if the cascade reranker is losing some performance because it's different from the original transformer. Surprisingly, what we can see here, this is a 12 blocks cascade transformer achieve even better performance of the state of the art that is a standard Tanda approach. And also, if you see with respect to the other layer, it behaves basically quite well. The 4 layer is not so good, but the other are pretty much okay. The other research question is that, okay, how much we can filter with respect to the cascade transformer. And these are the results. Basically, if we don't filter anything, again, we have I'm repeating the performance because this is another data set. So if we don't filter anything, again, we are better than the state of the art. So 66 versus 65. Then if we apply some filtering, for example, 30% of the candidates, we have an overall 37% of saving with respect to the standard transformer. If we use the sequential reranker, actually done by different transformer model, actually you have an increase of 53% because each of the reranker will classify a portion of the candidates. So in order to have an advantage with the sequential reranker of transformer, you need to have a harsher selection. And in any case, our saving is much better. Okay, in conclusion, I briefly mentioned that traditional QA architecture can hardly scale for efficiency problem and also for accuracy problem. So we have proposed an efficient retrieval-based QA system. We have a focus on answer sentence selection because it's the most important semantic task. We have presented a way to optimize answer sentence selection. Tanda approach is stable, easy to fine-tune, modular, because you can do the transfer step one time and then you could adapt step many times, so you don't need to redo the transfer step. Sequential reranker is very good for getting the right efficiency. And then we have presented also the cascade transformer, which is a more elegant solution which embeds re-ranking and transformer in just one neural architecture. We produce also some resources. So if you go to our GitHub, you can get data, models, papers, anything you can need to implement your basic QA system. Thank you very much.
All right. Okay. Thank you very much, Alessandro, for giving us this very nice talk. So we do not have much time left. So maybe we can just answer one short question, and then after that you can answer other questions on the Slack.
Sure.
Okay. So there's a question on the panel is that if the maximum token length of the QA pair exceeds the maximum length of BERT, besides cutting down the the original text, what else can we do? I think these are some very common issues that people face when the QA practitioners is usually facing. So do you have any thoughts on that?
Yes. So basically, I would like to tell that people may have seen. I didn't mention machine reading, but just because this is a 30 minutes, it's really small for what I wanted to present. So most of the research now is focusing on machine reading, and machine reading takes in input a large piece of text, and this can well exceed, as I was the questionnaire point out, the size of the BERT model. So the first part that is not really answering the question is that the answer sentence selection technology allow you to avoid this problem. It's more efficient avoid this problem because you have typical sentences, so you are well within the BERT size. But let's try to answer the question anyway. So it doesn't affect, the question doesn't affect this technology that I presented, but still it's a problem, it's a general problem for maybe inference and for sure for machine reading. So in machine reading, they want to process the entire document. So what they do, typically, they do something basic, like you can have a kind of sliding window. And since especially in machine reading, what you target is a shorter text with respect to the input. You will never classify an entire text you will not provide an entire text as an answer. So what you will do is to try to find a subsequence in the piece of text. If the piece of text exceeds the size of BERT, what you do is to apply a kind of sliding window. So you fit the maximum from the top until the maximum side of BERT. Try to look for the candidate answer there, which will be short. Then you move on one sentence, two sentences, three sentences. It depends on how much accurate you want to be. And then you see if you can find another candidate. At the end of the day, you may have several windows, so several computations, several answers, and you may have a joint model or just selecting the maximum score between the answer that you have found in the different windows. Of course, this is not much efficient, and but in general, machine reading is not much efficient. This is why when I presented an efficient real-world technology, I focus on answer sentence selection. Try to merge the two worlds, one very efficient, practical, the other very interesting, is surely also something that is interesting for us and for many researchers.
All right, so is Alessandro still online?
Yeah, did you miss me? I'm still here.
Yeah, okay. Yeah. All right, so yeah, thank you very much for answering these questions. So let's take the other questions offline. It's okay. And thank you very much.
I will check.
Yeah,
thank you again for inviting me. Have a nice continuation of the workshop. I will try to answer some question now. Then probably I need to go to eat. Here is evening, as you can see, late evening. Yeah. So good luck for the rest of the workshop. Enjoy.
All right. Okay. Thank you very much. Let's pass on to the chair of the next session. Thank you very much, everybody.
Hello, I hope people can hear me, and I hope that my chair is coming in too. Meanwhile, I'll share my screen.
Hi, Emily. Yes, I can hear you. Let me just add Kokil.
Thank you, Gangeshwar. And hi, Emily.
Hello.
All right. Thank you, everyone. And thank you for being here. And thanks to all our speakers so far. I'm very excited to introduce our next speaker, Professor Emily M. Bender. Professor Bender is a professor of linguistics at the University of Washington, where she is the faculty director of the Professional Master's Program in Computational Linguistics. Her research interests include the interaction of linguistics and NLP, and the societal impact of language technology, and how transparent documentation can help mitigate the effects of bias and the potential for trained systems to perpetuate systems of oppression. She's also actively working on how to best incorporate training on ethics and societal impact into the NLP curricula. Today's talk by Professor Bender is going to be about some of these issues, about a typology of ethical risks in language technology, with an eye to where transparent documentation can help. So without further ado, I invite Professor Bender.
Thank you so much. Thank you for having me. And it's evening here in Seattle yesterday from your perspective, and it's the end of a long day, so bear with me, but I will try to bring the energy here. I have put my slides up on, there's a bit.ly link there. It's also in the Slack, and I'm going to have it on my next slide too if you want to jot that down. So all the references and stuff are available to you. My goals in this talk are to present a typology, and I'll say what I mean by typology on the next slide, of the risks of adverse impacts of voice technology, to prevent data statements, which is one positive step that we can take to position ourselves to mitigate these risks, and then reflect on which types of risks the data statements help with, and also describe some emerging best practices, and I'll see how much of that I can do in a half an hour. I want to point out that my typology is still preliminary. This is work in progress. This is non-exhaustive. Data statements are not going to fix everything. They're just one tool. And the answer will be that they can help with some of the risks, but not all of them. So what is a typology? A typology, and I'm taking this term from linguistic typology, refers to a systematic classification of phenomena along one or more dimensions. And the purpose of making a typology is to help explore the space of possibilities. If we have a whole bunch of different things, and we want to get a sense of what might we have missed, it helps to categorize them in a typology so we can get a sense of where to look. And also to help understand the relationships across categories. Now, I'm not the only person working on trying to understand the range of possibilities here. I want to point you to previous work by Hovey and Spruitt and Barocas et al., and also Meg Mitchell in her Coling keynote for Friday, which it isn't Friday yet here, also is working on sort of a taxonomy of different kinds of harms. And the difference between a taxonomy and a typology is that I'm really trying to put these categories in conversation with each other. All right. In building my typology, I am drawing on two schools of thought. The first is value-sensitive design, which is a school of thought around how to design technology in a way that supports people's values rather than being in tension with them. And it goes back about 25 years, but there's some nice recent summaries there in the citations. And what value-sensitive design teaches us that's, I think, highly relevant here is to identify the stakeholders. That is to find out who the people are who are likely to be affected by the technology, either in the building of it, by directly using it, or because somebody else has used it. And then the next step is to go figure out, okay, what do those people value? And then how can we design the technology to support their values? So I'm drawing on that on the one hand. And on the other hand, I'm looking to sociolinguistics, because sociolinguistics surfaces a lot of important information about how language works in society that we need to be aware of as we are designing language technology. And sociolinguistics, of course, is a whole field in its own right, but in 4 bullet points, here we go. First major headline is that variation is the natural state of language. In any language, you're going to have multiple ways of saying something, and that is going to get associated with social information in the communities in which the language is spoken. The second thing is we tend to find particular language varieties being anointed as the standard, but that is merely a question of power and nothing inherent to the variety itself. That is, the way the language is spoken by the people who have power becomes the standard, becomes the prestige, but it's not that they speak a better language. Conversely, the language varieties and language features that are associated with marginalized groups tend to get stigmatized, and people tend to have language attitudes that say that way of speaking is bad or uneducated or rough, or all of these negative attitudes. And again, nothing inherent to the language, just a reflection of the marginalization that's happening in society. And then the fourth point, which is somewhat orthogonal but still connected, is that our social world is largely constructed through linguistic behavior. For example, when we are doing this activity we're doing right now, participating in a symposium, we are doing it in language. We're doing it about natural language processing, and we are conceiving of ourselves as doing science, but we are doing it by speaking to each other. And so language holds a lot of our social world, both in terms of things like science and in terms of things like constructing social categories of who is a good person, who is a powerful person, and so on. All right, so here's my current draft of my stakeholder-centered typology of the kinds of harms that can come about from language technology. And what I've done is I've divided the harms, and I'm going to show you a bunch of examples in the next slides, according to who is being affected and how they relate to the technology, but also whether it is a community or an individual being harmed. So the first top-level distinction is between direct stakeholders. Those are people who directly touch the technology in one way or another, and indirect stakeholders. These are other people who are affected, even though they might not even know the technology is being used. And then I have this distinction between harms that come about during the use of the technology versus harms that come about during the development of the technology. And I'm going to have less to say about the development part, so I'll start there. So direct stakeholders involved in technology development are people like annotators or crowd workers, and indirect stakeholders are unwitting data contributors. So people whose Reddit posts are scraped in the process of creating a Reddit-based data set, for example. And I don't have specific examples of that in the coming slides, but you can imagine that someone who is employed to do annotation of toxicity in online content is going to suffer some psychological distress from looking at very offensive posts, for example. So that's kind of the space that's going on there. I've got more to say about the use of the technology. There, the direct stakeholders are people who actually use the technology, but they might be using it by their choice or not by their choice. And so I've got those two different categories, and we'll see examples. Indirect stakeholders are people who are not directly using the technology, but still affected by it. And there I've got my case studies divided into whether the harm applies to the community or to the individual. And that's not a really sharp distinction. Oftentimes, harm to a community is harm to the individuals in the community, but it's still, I think, a useful way to think about it. The final thing that I want to say is that any given individual might fill multiple ones of these roles, right? You might sometimes be using the technology, sometimes be affected by somebody else's use of it, and so on. Okay, so here are some examples. Cases where someone is using the technology by choice, but they run into trouble. So for example, I might choose to use a voice assistant or some dictation software or a machine translation system and find that it doesn't work for my language or my language variety. And that can lead to harms like the suggestion to me that my language is inadequate or I speak it inadequately. Or I might just find that the product is unusable for me. Alternatively, I might be using the system by choice, but the system isn't indicating to me how reliable it is. And if I am reliant on, for example, machine translation or auto captioning for important information, and I don't know how well it's working, then I can be left in the dark about what I might be missing. The direct stakeholders not by choice example, I've got 3 of these. 2 of them are real. The third one is a nightmare scenario that, as far as I know, does not happen yet, and I hope it never will. So the real things are, there's companies out there marketing AIs that can do screening interviews, either by actually being the virtual agent that the interviewee talks to or by listening in on an interview. There's certainly cases where you might be trying to access a bank account, for example, and you have to deal with a virtual agent first. The nightmare scenario that I hope will never, ever happen is access to emergency services requiring interacting with a virtual agent. And in the US, I'm sorry, my slide says 911, that's what it's called here, but emergency services. Now, in all 3 of these scenarios, if I'm trying to use this because I have to, I don't want to be talking to a virtual agent, but it's in my way, and it doesn't work for my language variety or doesn't work well from my language variety, there's some real problems that could come about. So I might score poorly on the interview, even though I said good things content-wise, but the agent couldn't understand me, and so it just gave me zeros, right? Or I might be unable to access my bank account or, heaven forfend, emergency services. Another way in which we can be direct stakeholders is if we are consuming the output of large language models, which can now generate very real sounding text in English at least, but that text is not grounded in any actual relationship to facts. So I might mistake that text for statements that were made by a human who actually was taking responsibility for their truth. Or I might be aware of that and then just become more distrustful of all texts that I see. Also, thinking from the point of view of sociolinguistics, we should keep in mind that a language model that is trained on standard or official sounding documents or prompted in its few-shot learning with standard or official sounding language will sound standard or official and therefore might sound more authoritative. All right, all of that was cases where people were directly interacting with the system or its output. Now I've got the indirect stakeholders, community harm. So if someone is searching for me online, and in this case, I am taking on the identity of Dr. Latanya Sweeney, who did a very excellent study of this after seeing this happen, where she was sitting with a colleague in their office. They wanted to find one of her papers. They typed in her name, and up popped an ad that says, "Has Latanya Sweeney ever been arrested?" Why is that? It's because the system behind serving those ads, it had two options. It was the had ever been arrested option or find more information about option. And it had gotten trained probably through its interaction by what people were clicking on to show the ever been arrested option if the name sounded like an African-American name. And you can imagine if somebody is applying for a job and someone else is looking up for information about them and they're getting this subliminal message that maybe they're criminal, that would harm their job prospects, even though they're not even aware that the system is being used. Another kind of indirect stakeholder is the people who are affected as everyone in the community at large gets used to bossing around virtual assistants that are gendered as female. So I don't even have to be using those. If people around me are using them and getting used to barking orders at female sounding agents, that might affect the way they behave towards me. So these are examples of community harm. I think I'm going to skip over this one. You can look at it briefly. You have my slides. There's more examples. Another one that I want to highlight, though, is the way in which we are using general web text as a proxy for word meaning or world knowledge can mean that the biases in the general web text, otherwise known as general web garbage, can seep into our systems in ways that we don't want them to be there. So one example is nicely documented by Sophia Noble in her book, Algorithms of Oppression, where the auto-completion of search queries repeats and reinforces harmful stereotypes. So the image on the cover of her book has a case where she typed in, "Why are Black women so?" And the autocomplete gives angry, loud, mean, attractive, lazy, annoying, confident, sassy, and insecure. And she says, why is the world being told this about my community when they're just trying to type in probably some other question, or one would hope some other question. All right. That same problem of using general web garbage to train up word vectors that are a proxy for word meaning or world knowledge can also lead to individual harm of indirect stakeholders. So Robin Spear did this wonderful study looking at what happens when you take word vectors as an input into a sentiment analysis system where the supervised training data was just Yelp reviews of restaurants, and the task was predicting the stars of the review based on the text. And Spear built a system doing this using word vectors instead of the lemmas or whatever, so that the system had, in general, that leads to stronger performance, as we've seen over and over again, but it also leads to bringing in these biases. And what she documents is that a system built in that way systematically underpredicts the stars for Mexican restaurants. So you can have this glowingly positive review of a Mexican restaurant, and it gets a lower score than a similarly positive review for, say, an Italian restaurant. And this is all in English. And what's going on here is that general web garbage in English includes a lot of discourse in the US about immigration and lots of terrible things that are said about people who immigrate from and through Mexico. And so because of that discourse, the word Mexican itself was recognized as a negative sentiment word and then affected the performance of this system. So I think that's a really compelling example of how this practice that we use that seems well motivated because word vectors are really powerful, lets this bias come in and then can have direct consequences in an actual application. And further examples on the slide that I'm going to skip over in the interest of getting to more examples. There's recent documentation with GPT-3 now, this McGuffey and Newhouse paper, that finds that it would be very straightforward for an extremist group to use GPT-3 to generate very real sounding posts for a message board used to radicalize people. And that's a context where the direct user, the person who's creating this content, wants text that is not grounded in the actual relationship to the facts, just to make real people who come to that message board feel like there's a community around them. And so they document a very real risk about that. And I've classified this as individual harm because those radicalized people can then go and cause harm to specific individuals, but there's clearly also a community level harm there. All right. There's more. And I guess all I want you to take away from this slide is I have found a home for every example that I know about so far in my typology. So to review, this typology looks at who the people are who are being affected, how they're relating to the system, and then the ways in which they're being harmed. So are they using the system, and if so, by choice or not by choice? Are they being affected by somebody else's use of the system? And in that case, is it harm to a community or harm to an individual? And on the development side, are they knowingly contributing to the development of the system or the data set, or unknowingly doing so? All right, so that was very quick, but my point here was to basically highlight the ways in which the technology we build can actually have real repercussions in the world that are not ones that we should want. So now I want to step back and say, well, what does this mean for us? And I think what it means is that we have a responsibility to broaden our lens and to conceive of our jobs as not just about framing and solving technical problems, but also about understanding how the tech we build, or in some cases possibly choose not to build, fits into society. And doing that, taking that step back, does require a slower pace of quote unquote progress, but I think that that's healthier, and I think that that leads to better science overall. Than trying to be, the next person out to get the next state-of-the-art numbers before someone else beats us to it. And I would like to say that as we're working on broadening our lens, being systematic about documentation of the data we're using is a good strategy towards that. So talking a little bit about what I mean further about broadening the lens, here is a cartoon of machine learning taken from a machine learning textbook by Mitchell. That talks about precisely categorizing machine learning problems in terms of the task definition, the learning approach, the training and test data, and the evaluation metric. And Mitchell says, once these things have been specified fully, the learning problem is well defined. And Mitchell's talking about three things, but I have actually pulled out learning approach and training data as two separate things instead of just training experience. So that's the narrow view of machine learning. That's zoomed in. But if we want to broaden our lens and zoom out, then we start asking questions like, why do we care about this task? And there's sort of two broad classes of that. One is we might be trying to build something useful, or we might be trying to learn about computers, about people, or about the modeling domain. So these are basically the engineering and science answers to why do we care about this task. Once we have in mind why we care about the task, then we can ask, okay, how does this particular data set model the task that we care about, given the reasons that we care about it? And we can ask, how does the task relate to the world? Right? There's this task that I'm interested in, and I'm motivated by some scenario in the world. How does the task actually fit in? If someone were going to use the system, what would they be trying to do? How do we go about collecting the data, or how were the data collected? And finally, what happens when we deploy this? So these are the contextual questions that I think it's important to be in the habit of asking. All right, so what do I mean by transparent documentation? Friedman and I proposed something called Data Statements for NLP in 2018. That's a tackle paper. At the same time, there was similar proposals coming from other groups. So Gebru et al. Proposed data sheets for data sets. Mitchell et al. Proposed model cards for model reporting. I forget the name of the AI Now Institute one, but basically in 2018, something was in the air and a whole bunch of groups sort of independently said, hey, guess what? If we're going to get a handle on the way these pattern matching machines are causing harm in the world, we should know something about the training data they're learning their patterns from. And data statements for NLP is a version of this that looks specifically at language data sets. And we're asking for things like making it clear which populations and linguistic styles are represented in the data set, and conversely, therefore, which ones are not represented. And that allows people to reason about the possible effects of mismatches. So if I'm a hypothetical procurer for a municipal government thinking about putting in a voice assistant in my emergency response system, and the system I'm looking at is well documented in terms of whose language it can actually handle, then I'm positioned to ask the question of, oh, is this actually going to work in my community for everybody in my community? Contrary, if someone says, here's a speech recognition system, we've solved speech recognition, without saying whose speech and in what context, then that person doing that procurement is not in as good of a position to ask those questions. Documenting the data also allows us to recognize limitations of both training data and test data. If you think about limitations of the training data, those are effects on how systems can be appropriately deployed. And that's exactly the same example I'm talking about. If my training data only reflects a certain population, and then I try to use the system with other populations, that is not an appropriate deployment of the system. Limitations of the test data are really limitations in what we can measure and claim about system performance. So we can't say we've solved speech recognition. We can say we have done X% well on speech recognition on American English from adult speakers from California who are in a meeting, or whatever the actual specific context of that data set is. And this is a place where the goals of ethical practice and good science are actually very much aligned. We are doing better science when we're being more precise about our claims about how far things generalize, and we are better setting up people who are using the systems to know how they can deploy them. All right, so what are we asking for in particular? This is the schema for data statements as in that 2018 paper. We're actually currently in the process of extending that because we had some people make data statements and we learned a lot. But this is where it stands as a starting point. We asked for things like curation rationale. What data is in the data set and why is it there? How did you choose what to include? The language variety, whose language, right? Is this English? Well, whose English? Is it Singaporean English? That's much more specific than just English, right? As is American English, much more specific than just English. What is demographic information about the speakers, the annotators, the speech situation and the text characteristics, what kind of language behavior is going on here, and so on. So it's information about this that really gives you a much better sense of what's in the data set. So what does this help? The way I'm thinking about how we can use this is by thinking about the various roles which people have with respect to language technology, crossed with the kinds of things that can go wrong. So if we think about the situations where direct stakeholders are experiencing harm because their language varieties are not well represented in the data and therefore not well handled by the systems that have been trained on that data, and we would like to prevent those harms, well, as speech and language technology researchers and developers, we can, using data statements, map out underrepresented language varieties and direct effort appropriately, right? If we had data statements for all of the data sets available and we knew which languages were represented and we could say, hey, look, there's hardly anything here for Singaporean English, for Singlish, let's fix that, right? That would surface that information. And it would allow us to test approaches more broadly. So if somebody said, all right, I am working on a sentiment analysis system and I want to make sure that my system works across a wide range of contexts, let me go see what kinds of data sets are out there. I would be better positioned to do that if I had this kind of information about each data set. The procurer role is the person who's deciding which system or whether or not to buy a system and use it in some context. And if you have good documentation about the languages that the system was trained on, or the language varieties, then you can ask the question of, okay, is this likely to work for our clientele or our users, the people who are going to encounter this system? Conversely, a consumer can say, all right, is this going to work for me, right? Am I well represented here? And if not, I can point to that data statement and I have something to base my advocacy on, to get something in place that will work for me, if it's not a question of me buying something, but me like trying to talk to my bank. A fourth role is as members of the public, where I think it makes sense to advocate that models the models that are deployed in public-facing contexts be trained on data sets that are responsive to the community of users. And then finally, policymakers might require automated systems to be accessible to speakers of all language varieties in the community. And having that information documented would help policymakers to do that. So similar reasoning here about indirect stakeholders, but I think I'm going to skip over that one in the interest of time as well. And point out that data statements are not a panacea. Right? Mitigating the negative impacts of speech and language technology is going to require ongoing work and engagement and cost-benefit analysis. So this is a bigger conversation that we should be having. It's not enough to one and done make a data statement. The idea here is that data statements are one practice among others that position us in various roles to anticipate and mitigate some of the negative impacts. And arguably, if we don't have this information about what's in the data, then we are cutting ourselves off from the possibility of mitigating those negative impacts. Like it's not going to help, it's not going to solve the problem just to have this information, but if we don't even have this information, then our hands are really tied. That said, there's some things that I think are completely independent kinds of problems. So the impacts of gendering virtual agents, that's not a data statement related type of harm. Similarly, privacy concerns around classification of identity characteristics, where you've got, if someone makes a classifier that it can out people for various characteristics, I think data statements aren't particularly going to help with that kind of harm either. One thing they can help with is problems stemming from lack of representative data sets, as I've been saying, and also the problems of automation bias. So automation bias is this tendency that people have to look at the output of a computer as reliable because it must be objective because a computer said so. And if we can foreground for the public that these pattern matching machines are doing pattern matching on the basis of some particular data set, then I think that will push back against this notion of, well, we have to take the answer because the computer said so. All right, so what else can we do? I encourage everyone to make time to consider early and often questions like, what are the use cases of the technology being developed? How does this specific machine learning task, that is the inputs and outputs, actually relate to the intended use case? What are the failure modes and who might be harmed in each of them? And what kinds of bias are likely included in the training data? And when I say early and often, I want you to think of your research time as a really valuable resource that you don't want to invest poorly. And so the time to ask these questions are at the beginning of a project, not after you've done lots and lots of work, only to find out, oh, this was a bad choice. So it is worthwhile to ask this early and then keep checking in with it. I also want to encourage us all to broaden our notion of scaling up. There's lots of excitement right now about building models that can take in bigger and bigger data sets, around building models that have lots and lots of parameters. There's a certain amount of excitement around models that can deal with lots and lots of languages. But also let's think about scaling up around diverse communities and experiences with the software and apply some of that excitement to, is this research that helps us as a field consider more kinds of users and more kinds of experiences? And that's an important dimension of scale that should be valued. Even if any individual research project is actually going to be very specific to one particular user community that's being engaged with, we are still increasing our scale as a research community as we support that. All right, GPT-3 is really in the news right now, and I would like to ask the question, if something is too big to document, is it too big to deploy? GPT-3 and other ginormous language models, I propose ginormous as the technical term here, pose a dilemma. That is, if we're pursuing an approach to language technology that rests on gathering data sets that are too large to feasibly thoroughly document, how could that possibly be used safely? And I want to point again to the McGuffey and Newhouse article that showed that GPT-3 can be led through few-shot learning to produce text in the persona of a conspiracy theorist. I've got a screen cap from their paper here. I don't want to spend time on this because it is obnoxious conspiracy theory stuff. But my questions are, could GPT-3 have produced this without having similar conspiracy theory text in its training data? I strongly doubt it. If not, how much is required? And the worst case is actually only a little is required. And that's the worst case because it is much harder to design data collection and data cleaning processes that remove every last trace of this kind of thing. So I think that we can't just all jump on the enormous, ginormous language models bandwagon and abandon other approaches to language technology that are much more manageable in their data practices. All right, on the flip side, very large language models are giving us improvements in things like speech recognition, and that's very valuable in many ways, and including increasing accessibility. So what do we do? How do we get those benefits without opening up or while mitigating the above mentioned risks? Well, one thing is to ask, are very large language models actually the only way to get those benefits? Maybe there's other research we can be doing that would get us there without the ginormous data sets. Or are there ways to prevent or reduce the dispersal of synthetic text? So could we think about watermarking the output of language models, for example? All right, that was a lot. I hope that you are inspired nonetheless to see more. So I want to close this talk with a reading list. These are all great places to start. They are very much centered in the US context. But as you're reading about systems of oppression and the particular ones in the US, I think it's worthwhile thinking about in your own communities, what does that map to? Because I'm not aware of any utopias anywhere that are free of systems of oppression. I also really enjoy this podcast, radicalai.org, so I want to put in a plug for that. And finally, to conclude, Tyler Schnoebelen put it really well in 2017 in his blog post summarizing the EACL workshop on ethics in natural language processing. The L in NLP means language, and language means people. When we are working on tech that will be deployed in the world, we need to keep an eye on how it fits into the world and how it affects the people in the world. And it's easy to get bogged down once you start thinking about these things and this is too terrible or this is too hard, and then just decide I'm not going to do it. I'm either going to turn away from NLP or turn away from its societal impacts, but we don't have to get stuck there. And so I think I want you to walk away with the idea of transparency is a good starting point, and documentation of data sets and models and clear discussion of the application world relationship are positive steps that we can take to actually address these things rather than getting stuck in the this is too terrible, this is too hard, local minimum. So I'm happy to take some questions if I saved enough time. Thank you.
Thank you so much. That was fantastic. We do have a lot of questions. I'm going to start with the one that's the most upvoted. It's by a fellow speaker. It's by Dr. Eric Fosler-Lucier, who asks, I agree with the idea of data statements, but how do we balance the right of non-identification in data statements? If we have low number percentage of people in a certain demographic, for example, that may leak information about who is on the data set in some circumstances.
Yeah, that's a really important point. One of the concepts that comes, at least that I learned from anyway, in thinking about value-sensitive design is this notion of a value tension. So here we have the value of clear documentation and representation in tension with the value of privacy. And so it's, in some cases, it's not going to matter if you can show that it is privacy preserving still to say these many people from this demographic are in this data set. And if it's not, then you have to basically back off and say either not give the specific number or lump categories together and say, we collected this data in California and we sampled this many people, this number of them were from the majority population, and then not have anything further to say about the minorities of whatever category would be one way to go about doing that.
Got it. Thank you. The next question with the highest upvotes is, we'll take a couple more, all right? I know you'd have to get, do you have other appointments? We cannot always, this is from Ankurani, we cannot always train the model on all sample of the population. When you talk about appropriate deployment, what do you think can work best with a sample of population and testing it on all of the population?
So I think the answer might actually vary depending on what the application is. And sometimes the answer might be, we should just not do this. And so my current version of that is, we should not put speech recognition in between the person calling and access to emergency services, because I don't think that it's possible to make something that's going to be robust to all of the people calling. And that's the kind of very time sensitive thing where even having a failover to a person just wouldn't work. If it is something lower stakes, like imagine it's speech recognition as you're accessing food delivery, like I'm calling for a pizza and I have to deal with the speech recognition system, then it becomes a question of, all right, who are we failing to accommodate and how much harm is that doing, right? And it's still non-trivial, right? If the people who speak marginalized varieties are the ones whose language is not going to be recognized, and they're already getting the short end of the stick over and over again, and then they can't even deal with the pizza delivery place easily, then that's maybe not worth doing. I think my answer is to really think about the deployment case and then start with the people who are being harmed and most likely to already be experiencing harm in society at large, and think about what it means for them before continuing.
All right. Thank you so much for your time. We do have other questions, which if you don't mind, we'll put in Slack and maybe you can get to them later.
Yeah, I will try after dinner.
Yes, sure. All right. We'll let you get to your dinner. So thank you very much for being with us. And I'd like to pass over to our next host and speaker. Thank you.
Thank you. Bye.
Bye. All right, Gangeshwar. We have a next speaker.
Thank you, Gokul.
Awesome. See ya.
Yes, I think Wenxiang is here. Yep.
Yes, I'm here.
Hey, yes, it's all yours.
Yeah, Prof. Huang is also here. Okay, so yeah, let me take this session. Hello, everyone. I'm Wenchang Lei from National University of Singapore. I'm the chair of this session. We're glad to have Prof. Nie Huang from Tsinghua University to give us a talk about pre-training language models. Dr. Nie Huang is an associate professor at Tsinghua University. His research interests include natural language processing, particularly on dialogue system and natural language generation. He authored a Chinese book, Modern Natural Language Generation, and has published more than 80 papers in premier conferences. He won Wu Wenjun AI Award in 2019, Alibaba Innovation Research Award in 2019, and Han Wang Yu's Innovation Award in 2018. He won SIGDIAL 2020 Best Paper, NLPCC Best Student Paper, IJCI Distinguished Paper, and nominee of ACL Best Demo Paper. He also served as has a lot of public services like ACL 2021 Diversity and Inclusion Co-Chair, EMNLP 2021 Workshop Co-Chair, and area chairs for premier conferences like ACL, EMNLP, AACL, and senior PC members of IJCAI and AAAI. He is also an associate editor for TNNLS and action editor for TACL. He was supported by several NSFC projects and one key NSFC projects. So let's welcome Prof. Huang's talk.
Okay, thank you very much, Wenqiang. So can you hear me?
Yes, yes.
Okay, let me share my screen. So can you see my screen?
Yes.
Okay, and it's okay for switch?
Yeah.
Okay, thank you very much. So thank you for the nice introduction and also the invitation. Today I will talk about a pre-training language model. So the title would be, do pre-training language model really understand the language? So today I will talk about the following three problems. The first one is what is the understanding and the meaning? The second one is, can pre-training language model understand language? And the third one is how can we do better with knowledge? So let me first talk about meaning and understanding. So in the history of linguistics and computational linguistics, meaning is used is quite a popular philosophy since the 1950s. But the word used here is defined as a distribution in a text corpus. So so this idea is well known as a distribution hypothesis, which was proposed by American linguist Harris in 1954. He said, words are similar if they appear in a similar context. So, so suppose we have a corpus like this. We have many different sentences, and then we can obtain a word context matrix based on the core occurrence statistic. In that way, each word can be represented as a vector of its context word. For example, for bank, we have a crowd, located, and a downtown, and wet. And for apple, we have different context words. So in this manner, we can compute the semantic similarity between bank and apple. So in that way, we can define the distribution and meaning of the words. However, we also know the words is also context. The meaning of the word is a context dependent. For example, we have two sentences here. I go to the bank to deposit some money, and the second one, the little girl fell off the bank. So these two banks have different senses and a different meaning. In 1935, John, the England linguist John First says, the complete meaning of a word is always contextual, and no study of the meaning apart from context can be taken seriously. And after almost 20 years later, in 1957, he said a very popularized sentence like this: "You shall know a word by the company it keeps." So it's actually the meaning is context dependent. It's a very fundamental idea, and this idea is actually the origin of today's contextualized language representation models. So these models follow this kind of architecture. So we have a sequence of word as input, and we have a word vectors for each word, and then in the context encoder, we can represent all the context information in each vector. So each vector encodes all the context information, and then we can use these vectors to learn the downstream task-specific models. So this can be seen, for example, in Elmo, and in the GPT, and in BERT, in XLNet. So this is a very popular pre-training model today. And there's another good statement about meanings use in this year's ACL-based theme paper here. And they said language is used in the real world to convey communicative intent to real people. So what is a communicative intent? It should be grounded in the real world. The speaker and the listener inhabit together. So meaning is to be the relation M. It is a subset of E product I, which contains a pairs expression. E is a language expression, and I is communicative intent. So understanding is defined as the process of retrieving communicative intent from giving language expression E. I think this is a very good, very beautiful definition. Let me show another sentence in this paper. So there's a sentence: the photographer asked me to do a Napoleon for the camera. So for this sentence, if you don't have, if you are not a native speaker, or you have no history knowledge about Napoleon, you cannot understand. But you can guess it's a pose, kind of a pose. Let me say this is the pose of the Napoleon pose. So he put his hand in his coat, And let me show another example about knowledge-grounded dialogue generation. This work is by my team. And if we have a user input post like this, I have asthma since 3 years old. But if I don't know the word asthma, we don't know the meaning of the sentence. So if you try to generate a response to this post, it will not get meaningful responses. But if we can ground this word to the knowledge graph, for example, asthma is a non-disease, and it is caused by air pollution, and it can cause chest tightness. So even you don't know the word, you can guess the meaning of the word. So this is the idea. So if we have this kind of grounding to real words, we can generate more meaningful responses like this. I'm sorry to hear that. Maybe avoiding triggers can prevent asthma attacks. So that means we can use knowledge to facilitate the language understanding and the language generation. So what is understanding? This is my definition. So understanding is grounding to the shared knowledge between people. And the knowledge can be referred to the theoretical or practical understanding of a subject. The philosophy Plato has defined 3 features for knowledge. It must be justified, and then it must be true, and it must be well believed by people. So I think this definition is a good definition one. It's a good definition. And in the following talk, I will talk about, I will try to answer the following questions. What knowledge has been learned in the pre-training language models? And how can we do better with pre-training models? So, before we proceed, let me give a brief overview about the pre-training models. The pre-training models has different architecture. For example, we can have only encoder models. So this is about using the masked language modeling. For example, for BERT, Roberta, and SpanBERT and Ernie. Also, we have a permuted language language modeling. For example, for that used in XLNet. And also, we have adversary training for Electra. And another typical one is we only have decoded structure in the model. For example, we have general language generation models for GPT, GPT-2, and GPT-3, and also control. And also we have applications for a particular domain, for example, for dialogue system, which I was working on. For example, Mina and the Blender and the Dialog GPT and the CDAR GPT. And also in other models, we have both the encode structure and the decode structure. And they could be joint structure and the joint trained. For example, in Uni language model, the T5. And also they can share different. They can have different structure and different parameters. For example, in the math and in the bar. So this is a typical models for pre-training models. And in the following, I will try to answer the question: what is learned and not learned in pre-training language model? Okay. So first, let's look at the BERT. How the pathology models were good at mastering linguistic knowledge. So pre-training language model can do well in many linguistic problem tasks. For example, they have been known to have good knowledge about part of speech tagging, and they are good at grammatical error detection, and they are good at recognized named entities. And also, a sentence structure are encoded in model parameters. For example, in this one, we can see the header word plan is modified by financing, by complex, and by the. So this kind of sentence structure can be encoded in this model structures. The second one is about how its BERT is good at simple word knowledge. So we can see pre-training language models can memorize simple word knowledge. They can do well in simple fill in the blank tasks, and they can understand the taxonomy similarity between entities. For example, we can have this kind of a test. So you can see, for instance, in the first sentence, this guy was born in the right answer is at the second rank. So this is a pretty good result. And for this one, Adolphe Adam died in Paris. So the answer is at the first position. So you can see they are good at answering very simple questions. And also we can use BERT2 large to generate some common sense knowledge. For example, if we have input X holds out X hand to Y, and if we specify a relation attribute, that means what's the purpose of this action, and the answer will be helpful. So this is a very meaningful and incoherent to the common sense knowledge. So this is a very good one. And also we want to study how about complicated word knowledge mastered by the BERT models. So we can test the pre-training language model may fail in a complicated scenario. For example, they are not good at processing negation words, and also they are not good at dealing with frequency-related facts, and or if there are some misleading tokens, they will maybe wrong. This is some examples. For example, here bird can fly. This is right, but if we change the word can, it is still output fly. And if we add some misleading tokens, talk, and birds can talk. So this is also wrong, and this is a wrong, and this is a wrong. So they can deal with a complicated word knowledge very well. And then let's check another problem of BERT. How about they deal with numbers? So pre-training language models can understand normal numbers that frequently occur in a context, but they are only based on numbers, not the language. And also they are sensitive to the absolute values. So we have different sentence patterns like this. And also the meaning of the sentence is almost the same. However, the accuracy, when you're feeling towards older or younger, the accuracy will be changed dramatically from a 96% accuracy to just 12% accuracy. So that means BERT did not understand the sentence. Instead, it only deals with the numbers in a very shallow form. So today, GPT-3 is very hot. Let's look at the ability of the GPT-3. So first, we check the open domain question answering. So it can perform the task surprisingly well. So if we ask a question like this, the answer is correct, and this answer correct. And also, GPT-3 is very good at answering simple common sense knowledge problem. For example, if we ask how many legs does a frog have, the answer is right and correct. And also, you can ask this kind of a question: why are there any animals with 3 legs? There's no, but it's not a surprise because because GPT-3 is very large, and then also some conversation talking about this kind of knowledge. So the model may memorize this kind of knowledge. However, this kind of question will not be talked about in conversation in the web. So because they are too obvious and too stupid. However, in this kind of a question, GPT-3 is very good. They have already 80% accuracy. So this is a good performance. And so let's look at the number in the GPT-3 papers. So in this one, and you can see the fine-tuned SOTA, the comparison between the fine-tuned SOTA and the GPT-3 performance. You can see here Vinogran, and this is almost very close. And for Vinogran D, so this is a more challenging, that is a version of the Vinogran. You can see the SOTA is almost 85%. However, for the GPT-3, it's much lower. And for a reading comprehension task on the easy version and either on the more challenging version, and the performance actually is far lower than the fine-tuned SOTA. And for the job and the quark, this is about the common sense multi-hop reasoning task. It is much lower than the fine-tuned SOTA. So that means GPT-3 still have a long way for common sense reasoning. And if we input the nonsense input to the GPT-3, for example, if we this is a normal question, so the answer of course is right. But if we tap this kind of a nonsense input, the answer is totally wrong. And here, this question is very interesting. So who was the president of the United States in the 19th century, right? So the answer is also wrong, because at that moment the United States has not been established. However, this guy is the major political person in that time. So GPT-3 can do some correlation, can do some probabilistic correlation, but the answer is wrong. And for this one and this one, the answer is also wrong. So GPT-3 doesn't know when to say I don't know. Okay, so Gary Marcus, the NYT professor, has summarized this phenomenon and this problem very well. He said models like GPT-3 are approximations to language use rather than language understanding. So the models learns about how people use language, but has no real understanding about what they're talking about. So this is very accurate, I think. So in the following, I will talk about how can we do better with pre-training models. I will talk about how can we inject more knowledge into pre-training language models, and how can we design a domain-specific pre-training task, and how can we use knowledge-enhanced post-training to train the models, and how can we do explicit control of knowledge use. Okay, so the first one is about injecting more knowledge into pre-training models. So the simplest way is try to increase the masking probability of entities. For example, if we can use a tool to recognize entity, and then we can increase the probability of the masking probability of entities. So this is the simplest way. The second one is we can do word entity alignment. So we can, for example, we can either entity input embeddings in the input layer. So this is a very similar like positional embedding. And also we can align the vectors in the text, and also align the vector in the text with the vectors in the knowledge graph. So we can do a different alignment. For example, we can append, we can fuse, and then we can just say a different kind of techniques. And also we can do a cross validation, a cross prediction. For example, we can use the representation from the text to predict the entity in the knowledge graph, or we can use the representation from the knowledge graph to predict the information from the text. So this is a cross prediction. And in this work, they did a very good idea about this. For example, this is a test to the transformer models, and then they can do a noise linking to the knowledge base. So they have different kinds of linked entities and dimensions. But this could be wrong. Nevertheless, the non-soft attention over the linked entities, and then the computer representation, and then they append the vector from the transformer and also the vector from the knowledge base, and then they do the next layer computation over the model. So this is the idea, to align the vector from the text and also the vector from the knowledge graph. Okay, so we also did the second method to use a domain-specific training task. For example, in this year's EMLP, we published work, sentiment layer. So this work is to try to learn sentiment-aware representations. So we design a label-aware masked language model like this. So if we already know the label of the sentence, so this is a sentence level sentiment embedding. So we have additional embedding in the input layer, and then when a word is masked, for example, a good, the word good is masked. So the task needs to recover the word, but also we want to predict the part of speech tag of the word. For example, this is the adjective word. And also we want to predict the polarity of the masked word. For example, this one should be positive. So this is the first training task. The second one is we have a later supervision. That means if we have a word level priority embedding, that means each word has a word level priority embedding. So this is a neutral, neutral, negative, neutral, neutral, and neutral, and neutral, right? And then we want to predict whether the sentence the sentence is negative or positive. So this is the second subtask. However, to do this, we need unsupervised and scalable way to decide the word level polarity of in a sentence. For example, in this one, it is not a good movie. We want to decide whether this word is positive or negative. We design a context-aware sentiment attention. So in this dictionary, we have different part of speech tag for good, and even for the same part of speech tag, we have different sense numbers. And for each sense number, we have a positive score and a negative score. So we use the sentence. We first compute the similarity score between the sentence, it is not a good movie, and each glossary in the sense. So this one and this one. And then we normalize the similarity score into a soft attention distribution. And then we can compute polarity score for this word. And then we can decide the polarity of the word. So this is an unsupervised way, and it could be scalable to very large very large corpus. So we did this work, and we did the experiment on the aspect level sentiment classification and also sentence level sentiment classification. And this is we have got a remarkable significant improvements over the state of the other baseline. So this is the first work. And the second I want to talk about is when you use the GPT-like generation model for language generation, repetition is a serious problem. For example, if we use the pre-trained GPT-2 and we want to generate a story on common sense story on the RC stories, it will generate many repetitive sentences. For example, she was trying to get home, the brown yellowed one, the brown colored one, and this is a repetition. And you can see green and green is repetitive. And also we have a common sense conflict. And so this is not good. And also if we fine tune the GPT-2 model on the RC story, so we still have many repetition. So how can we deal with this problem? And so we proposed a very simple idea, try to make the GPT model have more knowledge. Because as we have talked about before, pre-training models have already some knowledge. However, they still have a lack of low frequency knowledge. However, knowledge base has many structured knowledge here. For example, we have this kind of a graph, and then we have many triples. So we use template-based method. For example, basketball player has property tall, then we can transfer the triple into a sentence. The basketball player has property tall, and then we can use this sentence to train the language model. So this is the same. So we have common sense knowledge triple, and then we can use template-based method to transfer into sentence, and then we can use the sentence. We can use the language sentence to train the language model. So this is the first one. And also we design a multitask learning objective. This is like this. So we use the idea of self-supervised learning. We have one human written story here. So this is a true story. And then we can do some perturbation over the true story. For example, we just random shuffle the sentence order like this. So this is the second type. And the third type is we just randomly sampled another sentence from another story. So this sentence is replaced by a negative one. And also we can just repeat one sentence we just repeat one sentence in the original story. So we have one true story and we have 3 negative ones. And then we try to make the model to make a classification of the input stories. So this is a multitask learning. We can see by this simple way, we do automatic evaluation and also manual evaluation of the generation quality. We can see the logic and the grammar has been enhanced significantly over the strong baseline. Okay, the last work I want to talk about is about a story common sense generation. So for example, if I have a story context like this, I have a 4-sentence story context like this. And we want to generate a reasonable story ending, for example, like this. So for this task, we need to have good knowledge about, we have a good knowledge about the common sense knowledge. For example, power is related to water and sin is a substance like this kind of. And another application is if I give you a statement like this, the school was open for summer. How can we generate an explanation for this kind of a statement? So here we have 2 versions of the generation. The first one is just either a negation word. For example, the school was not open for summer. Of course, this explanation does not contain too much information, right? This is not what we wanted. However, for this one, summertime is typically vacation time for school, so this is a good one. And also, if we give you a task like this, tell a story about I wanted a simple bag for commuting, so I bought a cheap one on sale. If you don't have this kind of knowledge, for example, this is a common sense knowledge graph, you will not generate a very reasonable continuation of the story. So this is a task. So we try to do explicit control on the generation. So we explicitly construct the common sense knowledge graph associated with the input text. That means if we have input x here, right, x1 to xn, then we can extract a knowledge graph for this kind of input, and then we can input the information, the text information, with a transformer model, for example, GPT-2, right? And here we use the graph neural network. For example, this is the graph we extracted, and then we do multi-hop reasoning over the graph. So at each position, at each decoding step, we have a gate. So the gate decide which word I should generate from graph. So this is from graph, or I should generate a word from the context. And then we can combine the 2 distribution with this gate. So this is the final generation distribution of our model. So you can see at each decoding step, we decide whether we can generate from graph or we can generate from the context. And if we want to generate from the graph, so we have a multi-hop reasoning over the graph. So we will propagate the score over the graph structure, and then we can compute a distribution over all the graph distributions, over the graph entities. Okay, so let's see the result. So we have a story ending generation. So that means we're giving you a 4-sentence story context, and then you need to generate a reasonable endings, story endings. We can see this is our model. So we can have a better BRUTE score, and then we have a better distinct scores. That means for measuring diversity, and this measuring for relevance. And also we can generate an explanation and so giving you a statement, how can we generate a meaningful explanation for the statement? And also we have abductive and NLG. So that means if I give you a start, and if I also give you a result, how can we generate the intermediate process of the given input? And let me show some examples here. So this is some example. So this example for the explanation generation, I have a statement 1. I buy a popcorn and a knife when I go to the cinema. So this is our model, generated by our model. So knives are not sold at the cinema. So we can have top 3 reasoning paths. So buy to sell, and popcorn related to food, and the cinema related to movie. So this is a reasoning path. And also we have second statement. He eats his chips with toothpaste. And this is our generated result. Toothpaste is used to clean teeth. And also the corresponding reasoning path. And this is the abductive natural language generation. So giving you O1 is the start of the story. And O2 can be viewed as the result of the story or the ending of the story. We need to generate the intermediate process. So in that way, we can say O1, and then the Simon's puppy like to play with me. And then he decided, I think I might want a puppy. So this is the result. Also, we can use the attention weight to see during the reasoning process how the score of the node change over the process. And this is the one half pass, and this is the second half pass. And also you can see the generation, the gate probability in the generation. So that means we will choose a word from the graph. So we have a larger probability of the gate. Okay, so let me summarize my representation. So we already know pre-training model learns to use knowledge, not to understand the knowledge. So for understanding, we need to ground into the shared knowledge. However, for this purpose, we need to have scalable and unsupervised grounding. About this is a very difficult. And nevertheless, we can still do better if we can design a knowledge-aware pre-training task, like I introduced in the Sentinel. And also, we can do knowledge-enhanced post-training. And also, we can do explicit control of knowledge use, just like the last work I introduced. And thank you for attention. So this is my talk, and this is a related paper I talked about in the representation. Thank you very much.
Thanks, Prof. Huang's nice talk. So I learned a lot. Okay, we could have some time for QAs, but yeah, but the time is tight. So we do have some questions on the QA panel. So I suggest you to answer the questions by text instead of the live QA, right? So we need to reserve the time for the next speakers.
Okay. No problem.
Hi, Wenxiang.
Sorry?
I think we have some 5 minutes to speak.
5 minutes. 5 minutes.
Yeah. Let's answer 2 questions.
Okay.
And then the rest we can take offline. Yes.
Okay. So let's pick some questions. So yeah. Here one audience asked a question. Yeah, his question is on the significance on the result obtained in the semi-eval, semi-eval 16 and 14 data sets, as these 2 data sets are very small. So do you have any response about it?
Oh, The question is about, I think it's about the Sentinel, right?
Yeah, semi-well data set. The data set is very small, but
the data set is small, and actually the result is significant. We performed a significant test for that, and you can check the details in our paper. And also we do some sentence level sentiment classifications. I did not present the slides here, but all the results are significant. Yes.
Okay, another question is how to measure how much knowledge is needed and how to evaluate what and when knowledge is utilized. So you know the pre-training model.
Model, right? Yeah. This is a very good question. Actually, I don't have answer to this question, but selective knowledge injection is very I think it's very important, and this year has a paper about that. So you can think about how to selective inject knowledge into pre-training models. So for here we just put all kinds of information into the pre-training models. So we translated the triples into natural sentence, and then we can treat the sentence as additional corpus to train the language model. However, if you want to do better, so you can design some sampling methodology. For example, we can sample repetitively the low frequency knowledge that could be get additional benefit for the model. So this is a very interesting research topic. Yeah.
Okay. So the follow-up question would be, so given the pre-training model has a capability of knowledge, right? So will be the knowledge graph invalid or less helpful in the future?
I think the pre-training model has some knowledge, particularly for the high frequency knowledge. And also, however, for example, for the common sense knowledge, has less frequently be mentioned in the corpus, right? And for this kind of knowledge, pre-training model is very bad. It works very poor. So I think in the future, this kind of knowledge should be embedded into the pre-training model very well. And today, I think University of Washington has a paper about this. So that means if you talk about the people murder is more frequently than people breath. So this is actually counter intuition, right? So that means the pre-training model can capture the co-occurrence information. If the knowledge is not presented in the text corpus, there's no way for the model to get it. So that is the answer.
Okay. So another question is that what do you think about the concept net? Someone use concept net, but find it is not very helpful. So what do you think about knowledge concept net as a knowledge graph?
Yes, concept net is very noisy. Yes, so it has many high quality triples, but also has low quality triples. But the problem is we don't have a very high quality the knowledge graph. So if you want to do language generation research, maybe you can use the Wikidata and or Wikitest. So they have a very good linkage between the test and the knowledge graph. And the knowledge graph is is of high quality. So but for common sense, we don't have a good resource for that yet.
Okay, so there is I think this is the last question. How to inject knowledge into pre-training model? So this is a general question actually. So do you have any suggestions, ideas?
Yes. So this is the answer. So we can inject more knowledge into pre-training model by, for example, increasing the masking probability of entities. And also we can do some entity and mention and entity alignment. So for example, here, Prince Sun, Purple Rain. So Purple Rain could be linked to the knowledge graph in an unsupervised way. This could be noisy. Anyway, we can use attention distribution to compute the software representation of the linked result. So this is one possible solution. And another one is you can for example, in the K-bird. K-bird means they just add additional information. For example, they can add another triple here, the link another triple here, and then they took this as input with this text, and then they can put a mask matrix over the on the input, and then they can say I have additional knowledge information. Maybe you can do beta. I didn't show the slide, but you can check. You can check the paper. It's a K-bird. Yeah.
Okay. Thank you very much. So yeah, everything is clear. I think I learned a lot. Okay.
Okay. Thank you very much.
Okay.
Bye-bye.
So let's pass to the next speaker.
All right. Thank you. Thank you, Professor.
Thank you.
So I'm going to add others now. Hi, Saujanya.
Hello. Hi.
Hello. Hi.
Hi.
Hello, Professor Pushpak. Nice
Hello.
meeting
Good
you
morning.
again.
Good morning.
Good morning, Prof. Hi. Yeah. So thank you very much for accepting our invitation. It's an honor to have you here. Let me introduce Professor Pushpak. So Professor Pushpak Bhattacharya is a professor of Computer Science and Engineering Department at IIT Mumbai. His research areas are natural language processing, machine learning, and in general AI. He has published more than 350 research papers in various areas of NLP. He also is the author of the book Missing Translations that discusses the abundant examples from Indian languages. Two recent monographs he co-authored called Investigations in Computational Sarcasm and Cognitively Inspired Natural Language Processing. He is also a fellow of Indian National Academy of Engineering and Abdul Kalam National Fellow. And he also recently received an award from the Ministry of IT and Patwardhan Award of IIT Bombay. He is also a distinguished alumnus of IIT Kharagpur. Let's welcome Professor Pushpak Bhattacharya. Yeah, thank you. We're looking forward to your talk.
Thank you. Thank you very much. Okay, I'll share my screen. So is my screen visible?
Yeah, definitely. Yeah.
Yeah. Okay. Okay. So first of all, thanks a lot to Saujanya, Gangeshwar, and others who are organizing this conference for giving me this opportunity to talk to you about our research. And the topic I've chosen is low resource machine translation. I am in the Faculty of Computer Science and Engineering, IIT Bombay. And what I'm describing to you is the result of many years of work by a lot of PhD, masters, undergraduate students, and many other research staff who have been with us. Now, some perspective-based comments. So we all know that natural language processing is a layered processing of text, going from morphology where the words are processed, going up to discourse and co-reference where connected sentences are processed, large pieces of text are processed. NLP is also a multidimensional problem involving multiple languages like Marathi, Hindi, French, and so on. And we try to solve a particular problem for a language with a particular algorithm. So it is multi-layered and multi-dimensional task, NLPs. Now, machine translation is a branch of natural language processing. And this is a perspective slide which says that the machine translation approaches can be divided into knowledge-based and data-driven approaches. So under knowledge-based approach, we have rule-based machine translation. And that again can be interlingua-based and transfer-based. In data-driven machine translation, we have similarity-based, which is example-based machine translation, probability-based, which is statistical machine translation, and distributed representation-based, which is neural machine translation. Now, we know that today's ruling paradigm is neural machine translation. But neural machine translation is very data intensive and also has the additional problem of explainability. We do not know what is going on inside the neural framework for solving a task. And this graph, which was contributed by Philip Cohen and Noels in 2017, shows that initially the rule-based statistical systems and statistical-based systems have much better accuracy compared to neural machine translation. But as the data size increases, neural machine translation quickly overtakes both the paradigms, both knowledge-based and statistical paradigms. But the fact remains that neural machine translation is very data intensive, requires lots of resources. And this can be said in general about whole of neural NLP, where resource and data play a very important role. And ingenuity lies in finding out methods of ameliorating this kind of huge data requirement. Now, an interesting fact about different machine translation paradigms is that all of them are controlled by 4 A words. Each of them is controlled by a word. So in rule-based machine translation, analysis plays the central role. In statistical machine translation, alignment. In example-based machine translation, analogy. And neural machine translation, most probably it is attention, which is the crux of the matter. I'm audible, right, Saujanya?
Yeah.
And my screen is also visible.
Yes,
right?
yes.
Yeah, good. Now, the main challenge of machine translation is what is called language divergence. Languages have different ways of expressing meaning, and they can be grouped into 2 categories: lexico-semantic divergence and structural divergence. Back in 2002, we undertook an extensive study of English-Hindi machine translation with focus on language divergence. Okay, and the goal of machine translation is really to close this language divergence gap, build a bridge between 2 languages. I'll exemplify this by means of this sentence, English sentence. This blanket is very soft. The corresponding Hindi sentence is "Yah kambal bahut naram hai." Bengali is "Ei kombolti khub naram." Marathi is "Ha kambal khub naram ahe." Manipuri is "Kampar asi mon mon loi." So the language divergence is illustrated by many interesting observations with respect to this sentence. For example, the auxiliary verb is in the middle of the English sentence, subject, verb, object. The verb goes to the end for Indian languages. So for Hindi, we see is has become hai and has moved to the end of the sentence. Bengali, interestingly, doesn't have any copula verb. So, ei kombolti khub naram, then null. There is no copula verb. In Marathi, ha kambal khub naram ahe. So, is has again traveled to the end of the sentence. And notice that Marathi and Hindi has almost 1-to-1 correspondence for the words. Ya, ha, kambal, kambal, bahut khub, naram, naram, hai, ahe. So, there is a lot of shared vocabulary between Hindi and Marathi and almost complete structural isomorphism between the 2 languages. Bengali, on the other hand, has a difference from Hindi. There is no copula, this is null, and there is this classifier T, which comes after kambal or blanket. And Manipuri is quite divergent because here the word this is the demonstrative pronoun, and that this is yaha, a, and ha, occupies the first position in Hindi, Bengali, and Marathi, but goes to the second position, kampar asi, blanket this. So also bahut naram, that is very soft, that intensifier is obtained in Manipuri by reduplication. Mon is soft. So this is depicted by this picture here. Hindi is very close to Marathi, somewhat distant from Bengali, quite distant from Manipuri, and really very, very distant from English in terms of language behavior. So there is language divergence or a distance between a pair of languages, which machine translation needs to solve. And depending on how close the languages are, this effort becomes enhanced or reduced. Now, this map of India shows the different language families, and Hindi and Marathi are Indo-Aryan group of languages. Bengali is Indo-Aryan, but with influence of Tibeto-Burman. Marathi has influence of Dravidian, and English is Indo-European. Now, this kind of language divergence was studied in 1968 by a physicist called Vauquois, a French physicist, but who worked on machine translation, interestingly. And he gave this Vauquois triangle, which is a classic depiction of language divergence and their translation solution. Now, the left side of this Vauquois triangle is the analysis axis. The right side is the generation axis. Now, depending on how close the languages are, we can operate at the bottom of the pyramid, or we have to go higher up in the pyramid. Now, one of the dreams of machine translation community has been to go to the tip of the pyramid where everything is disambiguated. Okay, word sense, structural disambiguity, ambiguity, everything is disambiguated. And we have a language independent representation from which the target language is generated. So the simplified Vauquois diagram says that the source language is analyzed, and then from the analyzed representation, we do a transfer to the target side, and we generate the target language sentence. So this analysis transfer generation is the ruling paradigm of machine translation, independent of whether the approach is knowledge-based or data-based, whether it is neural or statistical or rule-based. Now, rule-based machine translation is very analysis intensive, as I said. So you take the source sentence, go through the whole NLP pipeline, then do a transfer to the target side, and then begin to generate the words and the syntactic structure of the language. This is the classic rule-based machine translation. Now, if the languages are close to each other, then this analysis becomes less and less important. Okay, you can almost do one-to-one correspondence-based transfer from one language to another. Now, all this work on machine translation we have been doing is in the context of our lab at IIT Bombay, Center for Indian Language Technology. This has been in existence since 2000, and we address, I think, all areas of machine translation. And I also was responsible for setting up a lab in IIT Patna in 2015. And there are also lots of activities in natural language processing go on, including machine translation. Now, since we are discussing low resource machine translation, Indian languages are low resource. We do not have huge amount of parallel corpus and huge amount of other natural language processing resources. So it is also important to understand what kind of challenges face us when we deal with Indian language processing. First is the scale and diversity. There are 22 major languages in the country, written in 13 different scripts with over 720 dialects. So that's a huge amount of language data. Code mixing happens all the time. People typically mix 2 languages and often 3. So, kyun ye hesitation? Why this hesitation? So, kyun ye is in Hindi, hesitation is English. A very interesting fact is this: Gadi chalawing. Gadi chalawing means I am driving a car. Chalawing, gadi is Hindi, chala na is Hindi. Ing, that suffix of present progressive tense, is borrowed from English and attached to a Hindi verb. So these are very interesting and difficult phenomena. They are challenging, but they are realities. You cannot wish them away. The There is absence of basic NLP tools and resources. There is absence of linguistic tradition for many languages. The linguistic foundational work has not been done. And the script complexity and non-standard input mechanism, we normally use in script on the keyboards, but that's non-optimal. The finger movement is not really optimized. The QWERTY keyboard, which is used for English, is optimized for English. Now, the transliteration also is non-standard. Mango, Mango is written as AM, AAM, and capital AM. There are proprietary fonts, and typically for newspapers. There are challenging language phenomena like compound verbs. Has pada means started laughing. Morphological stacking, ghara samor chani, which happens in Marathi. And there is, of course, resource scarcity. So Indian language is heavily diverse, has many complexities in the whole NLP stack. And in addition to all this, there is this resource scarcity. So we have to find ways of doing Indian language, natural language processing. With my concentration, of course, is on machine translation for this talk. This applies to sentiment analysis, question answering everywhere. Now, back in 2014, we decided to depart from rule-based approach to Indian language processing, and whatever parallel corpus was available, we created a statistical machine translation system. So there were these Indo-European and North Indian languages of Hindi, Urdu, Punjabi, Bengali, Gujarati, Marathi, and Konkani, and South Indian languages of Tamil, Telugu, and Malayalam, and English also was a language. So we created this matrix of blue scores, and you can see that languages which are close to each other show huge values of blue score, and the quality of translation is also very high. So Hindi and Urdu are almost sister languages. Hindi uses Sanskrit words, Urdu uses Arabic. So you see the high blue score there, it is 61.28. Hindi Punjabi is also quite close to each other, and the blue score there is 68.21. When we come to Dravidian languages, there is a lot of agglutination. The words are joined together, morphemes are stacked. So there in general, we find much lower blue scores. And in particular, when we go from Dravidian to Dravidian, the blue scores are still lower. And for English, it has respectable blue scores for North Indian languages, but for Dravidian, the blue scores are much lower. So this told us that we have to either get huge amount of data to get appreciable blue scores, or we have to apply some kind of creative idea, some ingenuity to solve this problem. So this resource mitigation problem, we addressed with a lot of focus. And we found three ways. We artificially boost the resource. That means we do subword-based natural language processing. Instead of working with the tokens, which are words, we work with characters, syllables, orthographic syllables, byte pair encodings, and so on. Why is it beneficial? It is beneficial because we can stack suffixes and stack lemma and suffixes together to generate new strings. So if we have khaunga, which is will eat, and ja raha, who is going, we can synthesize kha raha hai. Okay, so where the training data did not have eating and present progressive tense combination. Okay, but it can be synthesized if we break the word into its parts and take the parts and join them together. So this is artificially boosting the resource based on subwords. Then we can take help from another language. This is called cooperative natural language processing, in particular pivoting. And we use higher level language properties like part of speech, sense ID, etc. By the way, these three resource constraint NLP, these three ideas for resource constraint NLP, they do not apply only to machine translation. They apply to all areas of natural language processing, including sentiment, question answering, text inferencing, and so on and so forth. Now, but there is a pitfall. This is the NLP's law of trade-off. We have to balance the precision versus recall questions, sparsity versus ambiguity, information injection versus topic drift. Now, when we do word level based translation, we do get blue scores. This is on a different corpora. Now, when we use subword based machine translation, where subwords are characters, morphemes, syllables, orthographic syllables, and byte pair encoding. Byte pair encoding, by the way, is the modus operandi for neural machine translation. There we find that if we do morphology-based machine translation, that means do not deal with words but break the words into its morphemes, then we get 2% improvement for Punjabi Hindi, and for Hindi to Gujarati, for example, Hindi to Gujarati, there is a 10% improvement. Okay, when we come to Dravidian languages, which are really challenging, there we find that for Telugu to Hindi, we have 10% improvement. Tamil to Gujarati, 14% improvement. Okay, then Tamil to Telugu, 7.56% improvement. So there was improvement for all pairs of languages when we did morphology-based machine translation. And when we did byte pair encoding-based machine translation, then the BLEU scores improved much more, and the improvement in BLEU score was really spectacular, especially in the Dravidian group of languages. For example, Telugu to Gujarati, the improvement was 25% BLEU score improvement. Now that was an evidence of how subword-based machine translation can really help and improve the BLEU score. But we had other approaches also to solving the resource constraint problem. Back in 2009, we did factor-based statistical machine translation, where the data is embellished with linguistic information. So I ate mangoes. This is the raw corpus. Now I is the agent. Ate is eat in past tense. Mangoes is the object of eating, and it is also plural. So these linguistic information are padded onto the raw corpus, which is the parallel corpus, and these linguistic embellishments happen on this parallel corpus. So when we do so, we have to make use of what is called factor-based machine translation. Here we don't have only word-to-word and phrase-to-phrase tables, but we also have morpheme-to-morpheme tables, suffix-to-suffix tables, and so on, and also factor-to-factor tables. So semantic roles are mapped to semantic roles. Okay, suffixes are mapped to suffixes. So when we do this kind of linguistically embellished parallel corpus-based statistical machine translation, we do find that the BLEU score improves from baseline value of 24.32 to 28.21 when the dependency parsing information is also added to the parallel corpus. So this was back in 2009, and then we moved on to see if other ideas also can be used. So that was pivot-based machine translation. So pivot-based machine translation, we did this work in 2015, where we made use of the idea of triangulation. The intuition is simple. Suppose we have the word pani in Hindi, and the Bengali translation should be jal. But we do not have a parallel corpus where this pani to jal correspondence is present. We do not have this evidence in the training data. So what do? We go via media English. So we have pani to water and then water to jal, and then we can synthesize this alignment of pani to jal by making use of this intermediate translation to water. And there the theory is also worked out. This theory is essentially based on marginalization, where any number of pivot languages can be brought into the argmax expression by means of marginalization. So what was the result? The result was that we first undertook a simpler task, which is Mauritian Creole to French machine translation. For Mauritian Creole to English machine translation, I had a postdoctoral fellow coming from Mauritius, whose requirement, the government had given him that requirement to create a Mauritian Creole to English machine translation system. So since that data was small in amount, we decided to use French as the pivoting language. Why French? Because Mauritian Creole is very close to French, linguistically speaking, and French English is hugely resource rich. There is huge amount of French English parallel corpora. So when we made use of that, we could, with small amount of data, that is English and Creole of about 25,000 word sentences only, which was very small, but embellished with this kind of pivoting corpora, which is English, French, about 2 million sentences parallel corpus. So with that, we could achieve BLEU score improvement on the baseline. Okay, so in the baseline, we had the basic Creole English system, which is statistical machine translation on only 25,000 sentences, but embellished with the pivoting corpora of English French, we could reach a blue score of about 25 from close to 20. Okay, so this was interesting, and then we moved to English Hindi machine translation, and there we could see that if we bring in pivot other Indian languages for pivoting, then the accuracy improvement is quite significant. So for example, if I have parallel corpus of, let's say, 7K, then with the basic system is this English Hindi machine translation. But if we bring in Bengali, Gujarati, Marathi, Punjabi, etc., the accuracy goes on improving. So if I draw a vertical line from 7K with the influence of pivoting languages, the accuracy goes on improving. Okay, and we studied this extensively for many Indian languages. So this was another method of reducing the criticality of resource. Now, today's paradigm is neural machine translation, which is extremely data hungry. And there we have to make use of many of these ideas like pivoting, subwording, phrase table injection, and so on. So we did extensive study with Indian languages and European languages. Now, the neural encoder-decoder model has this basic encoder and a decoder, where the encoded output from encoder goes into the decoder and the translation is produced. This is absolutely the basic encoder-decoder model. And this is embellished with attention so that long-distance dependencies are captured and the output comes out properly. So this was the status of in various Indian language neural machine translation. We also contributed a lot to this. Hindi Marathi, for example, shows 31 blue score, Hindi Punjabi 63, Punjabi Hindi 68, Hindi Gujarati 49. These are excellent blue scores, but they're in highly constrained domain. So the ultimate of completely resource constrained neural machine translation is unsupervised neural machine translation, where there is no parallel corpus. All you can make use of is the monolingual, huge amount of monolingual corpus. So this work was done in 2019, and as is usual in unsupervised neural machine translation, there is one shared encoder and multiple decoders. There are fixed cross-lingual embeddings at the encoder side. Denoising happens where the permutation of sentences are given and the output is insisted to be correct syntactic order. So if we train the machine with denoising, then the decoder learns the syntax of the language. And the back translation also is a critical step. So what is the foundation for unsupervised neural machine translation? This denoising and back translation based machine translation. The foundation is geometric structure of words, also called isometricity. So we see that dog, tiger, cat, these are words and their embeddings are clustered. This is in the English space. In Hindi also, we find that bag, billi, and all the animal words are hanging together. So if we take them to a cross-lingual space, then we find that tiger in English and bag in Hindi and bag in Bengali and the Tamil bag and French bag, all of them hang together because of isometricity. So we do this multilingual embedding in our work. We take L2, L3, L1, etc. to the English space. English is L1. So when we do this through denoising and back translation, we have these shared encoder and many decoders of multiple languages. And our results are on News Test 2013 and News Test 2014 data. And there we find that the French English machine translation system gives an increase of 0.78. English French in another setting gives plus 0.12. German English plus 0.73. English German plus 0.53. Okay, so this kind of neural machine translation through back translation and denoising applied to this benchmark data set did show improvement in blue scores. And we have done some extensive case study on output of French English, German English, Spanish English. And we also studied this in completely zero-shot setting where French to German, English to French, Spanish to French, this train system did not exist. They were tested on NMT systems, which are trained on English, German, English, French, and so on. And there also we got respectable blue scores. So this was reported in 2019. And this year in Calling, which is going on now, 2020 Calling, here we have enriched our unsupervised neural machine translation with further ideas. So that idea is filtering on back translation. So the idea is as follows. The central idea is to filter the back translated data by giving more weight to good pseudo-parallel sentence pairs. So we artificially generate parallel corpus in unsupervised machine translation through what is called back translation. So the back translation idea is this: we give an English sentence and we get the output on the Hindi decoder side for this English sentence. So that Hindi output is likely to be noisy. So we feed back Hindi output, this Hindi output, to the shared encoder. And now we take the output from the English side. So when you are taking the output from the English side, we expect that the initial English sentence would come back, but that doesn't happen. So the English output which is obtained is compared with the initial English output, and that is compared with blue score. So this blue score gives us a mechanism of assessing the quality of back translation. Now, when we generate parallel sentences through back translation, this back translated data is filtered based on their round trip back translation score. So this is the related work. We compared our system with Junsees and Doman 2018, Doe et al. 2020, and Lampel and Connew 2019. So our contribution is this. There is this cross entropy loss, okay, for training the system. And in the cross entropy loss, we also have a weight factor, WB. So this weight is a weight for assessing the quality of the back translation. So we take the artificially generated synthesized parallel corpus through back translation and filter out bad quality translations. What do you mean by bad quality? The bad quality is indicated by round trip blue score. English sentence, Hindi output, back translated English sentence, compare initial English sentence and the back translated English sentence. If the blue score is low, then discard that English Hindi parallel sentence. So when we applied this idea, the training data was about 5 million sentences from English, French, English, German, and English, Romanian. This is the WMT news crawl. And the test data was again new test 2013 and 16 and 14. So when we did that, we compared our work with the state of the art, and we found that compared to Song et al., we are able to get higher values in many of the pairs. And compared to Lampel and Connew, the statistical test also showed that the differences are significant. Though not much, you can see that with filtering and without filtering, the curves are close, but this is an indication that filtering based on round trip blue score is possibly an idea which can be exploited and investigated further. Finally, I would end with this module. We have investigated a lot the neural Indian language machine translation systems. And there we have used the idea of phrase table injection, word as features, morphologically segmented words, and we have worked on 56 systems. And the number of systems is large because we have many Indian languages involved: Hindi, Punjabi, Bengali, Gujarati, Marathi, Tamil, Telugu, and Malayalam. Here, of course, I'll report mainly performance of Hindi, Marathi, and English Marathi. That is because of a large government-funded project on speech-to-speech machine translation. This is a national project, and our part is English, Marathi, Hindi, Marathi, and also northeastern languages of the country. So we initially worked on some domain-specific corpora. The training set had about 46,000 sentences, tune set 2,000, and test set is 500. So when we applied the basic byte pair encoding-based neural machine translation, we got this blue score. Let's concentrate on English Marathi. The blue score was 10.79. Okay. And then when we used more corpus. When we use more corpus, this is Prime Minister's speech from India. And there, using more corpus, we could improve the blue score from 10 to 14. I'm talking about English to Marathi. Of course, there are other languages blue scores also, as you can see. Marathi, English, Hindi, Hindi, Marathi, and so on. When we made use of byte pair encoding of different size, then the blue score further improved to 14.63. And with back translation, with neural machine translation based on byte pair encoding, we could reach a blue score of 16.73 for English Marathi, and 16.47 when we had forward translation also. And when we introduced phrase tables, phrase table entries, that is, we combine statistical machine translations phrase table with the neural machine translation. We add the phrase table entries to the parallel corpus, then we could achieve a blue score of 21. And this is a consolidated table of English, Hindi, Marathi blue scores, where we have multilingual embedding-based training, phrase table injection, enhancement with morphology, BART augmented neural machine translation, pre-trained embeddings on byte pair encoded segments, and so on. So a very exhaustive set of experiments. And the highest blue score we could achieve was about 22 for English Marathi. Now, there are some sample outputs also. We have always compared our output with Google machine translation or Bing machine translation. So if the English source sentences, I do know some young persons who are active in such campaigns. So the Marathi reference gives Yuvak for young persons. Our output was Tarun, which is synonymous with Yuvak. Google translation produced Tarun Vyakti, and Bing produced only Tarun. Okay, and a complex verb structure is this Mohim Chalavtat, which is campaigning. Okay, campaigning as a verb. So Mohim Chalavtat is a complex predicate in the Marathi language, and we could output it correctly. Google output Mohima Madhya Sakriya Ahet is okay, but not fully idiomatic, and Bing did not produce it correctly. Similarly, for Hindi Marathi, we took sentences from the health domain. So Hindi यदि श्वास प्रणालिका में सूजन आ जाए तब भी रक्त मुंह से रास्ते बाहर आने लगता है. So reference Marathi is this. In our output, we could achieve Tari Dekhil, which is very idiomatic in Marathi, and Google's output was not really completely appropriate. So extensive experiments have been done. We did from COVID domain. We took experiments, sentences also from programming domain, because one of the goals of this national project is large-scale machine translation for lectures. So lectures are delivered in English for higher education in India, but there is need for getting them translated into local languages. So we also took data from programming domain and other lectures, and we could study their quality also. And an important module of the work here is disfluency correction, because this is speech-to-speech machine translation. Live lectures or lectures with video will have to be translated into local languages. So this required speech-to-speech machine translation, and that requires disfluency correction. So when a speaker speaks, the spoken utterances are often disfluent. There is this hesitation, then repetition of words. So we are working on disfluency correction, which is important for speech-to-speech translation. So in supervised system, we could get about 90 blue score, and that's expected because disfluent sentences and fluent sentences are both in the same language. But when we do completely unsupervised setting, the accuracy falls quite a lot, goes to 50 and 60 range, and that is what we are trying to improve now. So there are these case studies also. For example, so been a different turn. So fluent output is been a different turn. Okay, so this kind of this disfluency removal to an extent we have been able to achieve. Now I'll summarize my talk. We have discussed MT paradigms, data-driven machine translation is statistical machine translation and neural machine translation. Neural machine translation is extremely data hungry, so we need tricks for resource mitigation. And unsupervised neural machine translation is a crying need of the hour. So we have extensive experience of working on Indian language neural machine translation and also European neural machine translation. And all these have been reported in quite a few top venue conferences. The summary on resource mitigation is important to look at again. We have explored several techniques and demonstrated their efficiency. Phrase table injection. This has a great potential to boost the BLUE score, particularly when Dravidian languages are involved. Dravidian languages are very agglutinative, just like Hungarian, Turkish, Arabic, and so on. Harnessing monolingual data with back translation, forward translation is also advantageous. And there we have showed that back translation with filtering can be effective. And morphology and word feature injection to raw corpus has been proven to be effective by many people, including us. And this is important for Indian languages. We draw some conclusions. The data needed for quick system development and robustness. This is the theme of neural machine translation. We need data for quick system development and creating a robust system. Linguistic insight is also needed. We cannot really discard linguistic insight. This is needed for data curation and annotation and insightful error analysis. Now, when the neural net machine translation produces output, we have to analyze where is the weakness of the system, where is the strength of the system. This really requires insight into both languages, their linguistics, and the translation process. Neural machine translation ensures fluency, and syntactically the output is quite good. But many times semantically very strange things happen. The names get substituted, the tense changes. So these kind of things happen, but the output is quite fluent. So there is no way out for neural machine translation than tricks of ameliorating data hunger. And our future really lies in cross-lingual, multilingual word embeddings, where intense amount of work is going on. So cross-lingual, multilingual NLP itself is a very hot area. And I think the whole effort is being led by machine translation. Now, I would like to leave a final message. We have understood many times through this resource content constraint NLP that NLP is really a task and trade-off. If we have too much of enhancement of extra linguistic information, the information beyond training data, if you have too much of such information, then there can be inadvertent insertion of ambiguity. And if the embellishment is too little, then we face the problem of sparsity. So we have to tread a middle ground, which was actually propagated by Lord Buddha some 2000 years back, that the middle path is the golden one. Now, everything I have said is linked from my homepage through publications, and our lab, Center for Indian Language Technology in Bombay, and now the NLP lab in Patna, they are contributing a lot of resources, especially for Indian language, which are publicly used. Thank you very much for your attention.
Wow, that's a great talk, Prof. I mean, wonderful. So we have questions. Question from the audience. Question from Dipanay Khosal. Is NMT considered solved for resource-rich languages? Is there any research on unsupervised machine translation for low-resource languages? There has been some development in this area for resource-rich languages such as English, Spanish in the last few years. So I guess for the point two, Prof has already explained in his lecture. So I would seek your answer for the first question. Then we will move to the second question.
For the first question was what? Sorry,
is NMT considered solved for resource-rich languages, like for English, Spanish? Yeah.
Well, I think good question. So not really, because a very important landscape is still unexplored. That landscape is the landscape of fixed expressions, collocations, idioms, and proverbs, and also metaphors. So So to give an example, the donkey praises its own tail. This is for persons who praise themselves. Okay, so the corresponding Hindi is apne muh apne muh miya mithu. Yeah. So so if somebody is saying that his own mouth is very sweet. Okay, and the corresponding Bengali is nije dhol nije bajano. So that is beating one's own drum. Okay, so as languages become divergent, the proverb translation becomes more and more challenging. Okay, a bad workman quarrels with his tools is translated to a bad rider quarrels with his camel in Arabic language. So proverbs are very culture specific, and this kind of translation is still a far cry. Similarly for metaphors are very language specific, and collocations and fixed expressions. Okay, for example, Hindi says hasparna, laugh and fall. Bengali says heshe ota, laugh and rise. Okay, so this landscape is yet to be explored.
Yeah, just to add one point here. I mean, do you think that like even for the resource-rich languages, when we have informal text, when we have conversation, dialogues, I mean, still very difficult to capture the pragmatics and context and the reply considering that. So that's a still relevant topic and unsolved, I guess. I mean, not well researched.
We are absolutely right. Yes.
Okay, so the next question from Gopa Sen. She's saying, thanks for a very interesting talk on extensive multilingual MT work. Given that Sanskrit is the root languages for many of the Indian languages, was Sanskrit been used at any stage in MT, say for pivoting of different Indian languages?
Okay, so hello Gopa. Nice to meet you after such a long time. Gopa was my student in IIT Bombay. Okay, so okay now so Sanskrit as an interlingua has been investigated quite a lot since 1980s. There was a seminal paper by Professor Biggs, and in Bangalore there was a conference in Sankarmat where this was discussed quite a lot. Now the problem is that though Sanskrit words are heavily shared across languages, so there is a lot of vocabulary overlap, but Sanskrit also uses tremendous amount of sandhi samas. So the modern languages typically reduce sandhi and samas, and also morphological complexity. Okay, so and also the other problem is that the interlingua is expected to be completely disambiguated, but Sanskrit also has its own ambiguity, both at lexical level and at the structural level. So Vriddhasya Mitrasya Griham, for example, Vriddhasya Mitrasya Griham. This may mean old man's house, old friend's house, or old man's friend's house. Okay, so the ambiguity is still there, even if we use Sanskrit. So the advantage of using Sanskrit as an interlingua would be there is a lot of vocabulary overlap, but we still have to solve the problem of sandhi, samas, agglutination, morphology stacking to be used as interlingua.
Okay. Okay, great. Yeah, I think that's all. Thank you very much for that great talk. Yeah, it was great attending the talk. Yeah, thank you so much. Yeah.
Thank you very much. Thank you. Thank you.
I will now. I will now let Gangesh sir. Yeah, to continue. Okay. Thank you. Bye.
Thank you, Professor Pushpak. That was a fantastic talk. Thank you, Saujanya, for hosting it. I think this concludes our morning session, and we will be back at 3 p.m. for the afternoon session. And let's 3 p.m. in Singapore time, and which is GMT +8. So see you all soon there. This link will be live. You can still join through the same link, and also YouTube as well will have the same link, YouTube Live. So see you all here. Thank you. Bye-bye.
Hi everyone. Hi Nancy. Hey.
Hi Lidong. Hi.
Hey, nice to meet you. Nice to meet you again.
Hi everyone. Nice to meet you all. Oh, hi Dad.
Hi everybody.
Hi.
Nice to meet you.
Nice to meet you.
Hello everyone, this is Yang Jun, Bill.
Hi Bill. I guess we're all here. Should we wait a couple more minutes or does everyone's video work? Hi Bill. Atapol, can you hear us?
Yes, I can, yeah. And you can call me Tay. That's what I go by.
Okay, great.
Hi, Nancy. Hi, everyone.
Hi.
Hello.
I think we wait for a couple of more minutes. So,
sorry, everyone's video work? I cannot hear. Atapol, can you hear us?
Yes, I can, yeah. And you can call me Tay. That's what I go by.
Okay, great.
all right. How about we wait for a couple of more minutes?
Yeah, we can wait a couple more minutes.
Yes, let's let everyone know. I think we wait for a couple of more minutes. So,
sorry, everyone's video work? I cannot hear.
I guess there's some sort of echo, so
Yeah. Is
we
everyone
might just mute if
okay, maybe
we
we
are
mute
not.
first.
Hi, Lidong, where are you now?
I'm in the office. I guess we should come together.
Okay.
So they will find out that we are in the same building.
Yeah.
Background.
okay, we have a lot of people joining in now.
Can you guys still hear me?
Yes, can.
Okay.
Yes, we can.
Okay.
All right, I think we can start, Nancy.
Okay. Hello, everyone. Good afternoon, good morning, and good evening. Welcome to the panel discussion for Low Resource NLP for Southeast Asian Languages. I'm Nancy Chen from the Institute for Infocom Research, A*STAR, Singapore, and I'll be facilitating this panel discussion. We're very honored to have 5 panelists from both industry and academia with expertise spanning from linguistics to language technology from different Southeast Asian countries. I'd first like to ask our panelists to introduce themselves. And so let's go by alphabetical order of the surnames. Monojit, do you want to go first?
Sure. Hello, everybody. I'm Monojit. First of all, thank you to the SSNLP organizer for inviting me for this. And also a big thanks for choosing this as the topic of panel discussion, which is very close to my heart and I think is very, very important. So I'm a researcher at Microsoft Research Lab India. And I have been working on mostly various topics in NLP. Of late, I have been focusing on low resource languages and code switching and code mixing. Yeah, other than that, I'm personally pretty passionate about languages and linguistics. So I also drive the Linguistics Olympiad in India, and also the Asia Pacific Linguistics Olympiad, which is awareness of linguistics for school children. Thank you.
I see. Thank you. Lee Dong, you want to go next?
Yeah, sure. So my name's Lee Dong Bing, and now I'm working with the Alibaba Damo Academy, and based in the Singapore office. And my team and I are working on a lot of practical low resource problems to support the Alibaba's globalization effort in Southeast Asia as well as the worldwide. And yeah, it's very happy to be here. Thanks for the organizers. Thank you.
Okay, thank you. Bill, you want to go next?
Okay, so thank you, Leslie. I'm Bill Lang. Yeah, so now I am working in Lazada, Southeast Asia company. So our company are doing a lot of e-commerce business in whole Southeast Asia. To language processing, yeah, we are doing a lot of things for Thai language and Vietnamese language and Bahasa and English to cover all of our business countries. Yeah. So to this topic, yeah, we are doing a lot of effort for Southeast Asia language processing, such as tokenization and lambda entity recognition and classification and topic detection, and something related to business part by address processing and product title processing and a lot of things. Yeah, we are very honored to have this discussion with everybody today. Thank you.
Thank you. Dat, you want to go next?
Yes, hi everyone. I'm Dat Quốc Nguyễn. I'm a researcher at VNAI Research, Vietnam. So today we'll be very honored to be here to discuss with you guys about low resource language processing. In particular, I'm doing research, doing application of machine learning to natural language processing tasks like tagging, parsing, information extraction, knowledge graph, embeddings. I'm also very keen to explore these kind of technologies for the Vietnamese language. Yeah.
Thank you very much. Atapol, you want to go next? I don't see him.
Yes. Okay. Hi. So I'm Tay Rutherford. I'm assistant professor at Chulalongkorn University at the Department of Linguistics. I recently joined the faculty a couple of years ago after my PhD in the States at Brandeis University. Now, my research interest involves around building Thai language, natural language processing infrastructure. So like my previous work since I joined here includes word segmentation, making parallel corpora for Thai English machine translation and part of speech tagging as well.
Okay, thank you very much. So I compiled some questions from the audience and organizers, and I'll use that as an anchoring point to seed the discussions, but feel free to counter-propose topics that you think are interesting to you. So there were a lot of responses related to pre-trained language models since it's pretty hot. So I was wondering if the panelists could share from your experience how do the different languages that you've been working on behave differently when you leverage these pre-trained language models, and what are some suggestions you have for making the design and training evaluation more fair for low resource languages. Does anyone want to go first?
I guess I could. So like recently, like pre-trained language model is like the hottest thing for NLP at the moment, right? And Thai is one of the low-ish resource language. We do have some stuff, but like not a lot. So I try using that with part speech tagging, which is it doesn't seem to be quite compatible with the BERT style kind of BPE kind of subword unit, right? So that makes it a little more difficult. But what BERT makes it a little easier is that we don't have to deal with word segmentation anymore, and we don't have to deal with the ambiguity around like morphological parsing of the word, because sometimes we don't know whether it should be treated as compound word or it should be treated as two different words. And BPE just eliminate all that ambiguity by training the tokenizer on the large corpora, and actually the results still hold. We have to do some trick so that one word with different BPEs will have the same parse speech tag. So we could get around that, but the results still hold pretty well, pretty impressively for Thai parse speech tagging. That's what we have experimented with so far.
See, thank you. Anyone else that want to chime in?
I guess I could. So generally, to be honest, I'm just working on language modelings for Vietnamese. So in general, I find using pre-trained language models might be result in similar behaviors for different languages, like Mono just mentioned. Just mentioned it can help to improving parse-speech tagging for Thai language. So in other words, they all help to improve the state-of-the-art performance for many NLP tasks. So the difference here is, I think, when using pre-trained language models, I find higher performance improvement for low resource testing than compared to the richer resource testing. For example, for Vietnamese dependency parsings, a pre-trained language model can help to improve like 4% absolute improvement to a strong baseline. While for English pantry banks, I only find like around 0.5% improvement to when using a pre-trained language model. So that's the difference I find when I exploring the pre-trained language model for different languages. Also the question about designing, training, evaluation, the pre-trained language model, right? For low resource languages, I think we probably can create standard measures for different modeling perspective. For example, the model size, the pre-training data size, or computational resources. Because when we mention about low resource languages, it also means that a minimum access to the GPU resources. So, for example, in Vietnam, not so many people can access to the GPU computations. So I think that's to have a design, training, evaluation of the pre-trained models, we might have some regulation on top of model size and the training data size.
I see. Thank you.
So maybe I can pick on your point on fairness, because I think that's very important. And very recently, it's not yet public, but accepted for AAAI 2021, we did a work where we asked this question that, when do you call a pre-trained model to be fair? And we looked at a host of papers which try to do this kind of modeling. And what we found is almost everywhere, people at the end decide which is a better model based on average accuracy across languages. So, and that's very weird, right? You are training it for 100 languages, testing it for, let's say, 15 or 20 languages, and you are just reporting average on those 20 languages. So we looked at a lot of studies to see, and as well as literature in economics, to see what could be a fairer model or fairer way of deciding. It turns out one of the ways to do it is what is called Rawlsian fairness, or in short, you try to choose that model that maximizes the accuracy, which is minimum for a language. So let's say I have Thai as the hardest language to process. So I choose the model which has highest accuracy for Thai. That's typically fair. Now, would it reduce performance for English and other high resource languages? Turns out most of the time that reduction is too small, whereas the gain for the other language is much, much more. So, of course, I mean, we are not proposing that as the only solution. There are more details to it. But the point I wanted to bring up is fairness is an extremely important question here, which people don't seem to think a lot when they choose models. They even don't discuss these issues and just assume that average is the good way to go. So that's one point. Another quick point is, often we are hung onto zero shot, but most of the time we can build some resources, some labeled data across languages, so-called few shot. And few shot models are often much, much better than zero shot. And that's, I think, one concrete way to go for all low resource languages. Just don't rely on zero shot. I'm sure for Thai and Vietnamese, you would have resources to do some label training. But even for other, I mean, much lower resource language, at least even 100 data points could be created. That goes a long way.
Thank you. How about our friends from Alibaba?
Yes.
Comment on the pre-training.
Yeah, I may want to echo one point about the and the low resource setting. In fact, in the industry, we don't really solve the problem with the zero shot setting. Normally, we will have our resource to label some data. I can give one example is for the low resource language name entity recognition from the product titles. What we did here is we will label 10K or 20K product titles and then train a supervised model to do name entity recognition. And we did try to use the pre-trained language model. And on top of the pre-trained language model, the performance for each individual language we are interested in does have improvement. For example, for Vietnamese, Thai, Indonesian, the improvement can be 3 to 4%. I've found. But the problem is in real applications, this big pre-trained language model-based architecture is not efficient enough. And then we need to think about how to deploy a more efficient version. And we use the knowledge distillation. And after that, we will find that the performance drop compared with the full pre-trained language model, drop 2 or 3%. That means this distillation model has advantage over the pure supervised method. The LSTM-CRF method is about 1%, which is not that impressive already. So this is something we need to tackle in the real industry application. You use the full pre-trained language model, it's good, but it's not efficient. If you use knowledge distillation, and its advantage becomes small. Yeah, this is the real case we're facing in the real industry problems.
Thanks for sharing.
Okay, so let me share something from Lazada. Actually, same as Li Dong, yeah, we are doing a lot of collaboration from each other. To Lazada part, we have the most population from our Bahasa language relations from Indonesia and Malay. Actually, to Lazada, we have the most product from the two ventures. Yeah, but to Vietnam, Thai and Philippines, and even Singapore, yeah, their product is not so many like our Indonesia here. So to Indonesia and to English, we already have a lot of resources here, but to Thai, to Vietnam language, the two parts, yeah, we have very low resources here. To us, we already found, yeah, if we have a very good pre-trained model, even a good language model, we can easily transfer our English and the Bahasa's models to other languages. Yeah, this has been verified from our product title processing and product image processing, and it's also have been found and verified in our users' entries classification part. Yeah, it's very interesting. In future, we do hope we can do more such kind of study from our Thai language and the Vietnamese language processing. Then actually with this kind of effort improvement, it will improve our user experience in e-commerce a lot. Yeah, we do looking forward to collaborate with everybody. Thank you.
Okay, thank you for sharing. Does anyone want to elaborate more on the fairness aspect or your experience in which language that you found surprisingly easy or difficult in your work, whether it's in research or applications?
So maybe I can add one thing, which is this is a very recent discovery that we made, and not about an Asian language, but nevertheless a low resource language, which is Swahili. And we were looking at natural language inferencing and category-wise zero-shot performance, like certain inferencing requires logical deduction, some inferencing might require syntactic deductions, and so on. So we separated the data by categories and tried looking at zero-shot transfer for each category. And surprisingly, Swahili had a very low zero-shot performance for negation. Whenever somebody, so contradiction is often expressed as negation in these data sets. So there was very low accuracy there. And when we looked at it, it was very interesting to see that unlike all the other languages in the data set where there were words for negation like not or no, or whatever that word is in nahi in Hindi and so on, in Swahili, there was prefixes which are used with the verb for negation. And these prefixes actually differ by pronoun. So I did not do will have a different prefix, and you did not do will have a different prefix, and so on. So it was very interesting revelation to us that typology of languages matter so much, and we really don't. We haven't looked at our massive pre-trained models that deeper to understand well that what they can handle and what they cannot. So there are, I'm sure there will be a lot of research in that direction, but that was a surprising discovery, I would say.
Okay, that's very interesting. Anyone else have any examples that you want to share? Okay, so there are other questions related to linguistic theory, since a lot of NLP work is grounded in this. From your experience, do you think there are certain linguistic theories that might deserve more attention, especially for the success in low resource NLP, since now a lot of the theories might be based on more mainstream languages that are Indo-European? Does anyone want to share some thoughts or elaborate on this?
Hey, Nancy.
Hi.
Yeah, I think I can share some of my ideas. In last year, we have a discussion with a linguistic professor from NTU, and we do mention that in this DNN time, we can use this architecture for pre-training language models, and which can perform good adaptation performance for low resource language. But we do think that from both our industry view and also from the linguistic view, we do think that one result that is pretty important for low resource language, even with the powerful pre-trained language model, that is the word net. And I know that some efforts are in Japan and Singapore, and some team are working on this low resource word net. And now they do have some good progress for some of the local language in our region, like Vietnamese, like Indonesian. But we know that worldwide, there are a few thousand of languages are using by a not very small number of population. So I do hope that for these NLP researchers, particularly from these low resource language speaking countries, we can spend some effort to build up this word net, because this is sort of one-time effort and can be very beneficial to a lot of downstream tasks. Yes, this is my idea.
So, yeah, thanks for sharing. So do other people want to chime in on this, on WordNet or other linguistic theories or resources that might be worth investing in?
I agree with you that WordNet or like semantic theory or lexical semantics in general is it's generally useful because it's not so overfit to certain languages, right? But I think we can agree that syntactic theories, on the other hand, are geared more toward more like European languages that has like more morphology, more like verb agreement, like the main syntactic phenomena that we spend a lot of time on when we learn syntax in university level, right? But when what I found is that even for dependency syntax, when we try to parse it in Thai, there are a lot of relations that we think should be there, but it's not even included in universal dependency. So it makes it very awkward and make it very inconsistent when we try to create a tree bank. And that leads to like another question, like altogether, like should we, like how important is that how important it is to have a syntactic parser in general when we have something that's like more computation heavy, like like BERT, when we try to we can like skip a lot of these like altogether when you try to do, say, any text classification task. We don't quite use syntactic parser. Maybe we use syntactic parser for more like relation extraction or name entity recognition kind of task. So like I feel like that's usually a big like investment in terms of like the theory that we have to develop in order to adapt the syntactic framework that we minimalism or HPSG or whatever theory, LFG, whatever we have from that side of the world to Asian languages. I still found that quite difficult to adapt and try to make tree bank consistently.
Thank you. Anyone else want to add on this point?
This is Bill. So just now, yeah, we have discussed about the syntactic pattern for Southeast Asia languages. So to me, I think in the whole world, from main language, the syntactic research part, we already found to some end-to-end applications, just like machine translation and summarization, things like that. The syntactic pattern technology sometimes is less and less important for that kind of application there. But to my best knowledge in Southeast Asia language, especially to our low resources situation here, I do believe syntactic parsing also have its important role. For example, for the language starting, for language usage correctness, and for our general information extraction, also from the unsupervised learning in our Southeast Asia language processing part, I do believe syntactic parsing is also very, very useful. Yeah, especially to such kind of languages, we have very low resource here. But how to do that? Maybe we should consider how to set up a light standard. Is different from Pentry Bank or from other kind of syntactic parsing in English. Yeah. So how to define such kind of light standard, I think should be discussed a lot with a lot of linguistic person and experts together. Yeah, this is my general understanding. In Lazada, we also are exploring how to use syntactic parsing in our e-commerce text processing. Yeah, so to English, I think sometimes it's useless, but to other languages, they are useful. Yeah, we also would like to collaborate to consider how to have more linguistic syntactic parsers in Southeast Asia languages to our business here.
Thanks for sharing. Anyone want to elaborate on this discussion between syntactic parse trees versus pre-trained language models or your observations or experience on what you think might be beneficial for the field or some future trends?
I guess if you ask me to whether we should build syntactic dependency as syntactic tree banks, I guess we can just go with the phrase structure tree banks, because at the end you can convert from the phrase structure tree bank into the dependency tree. So I think it's really necessary to build a syntactic parser for the Southeast Asian languages. Like you guys have mentioned, a lot of NLP tasks rely on the output of the syntactic parser like information extraction, especially in open information extraction where we want to build a knowledge graph of entities. We still need the output of a dependency tree, a dependency parser to capture the relationship head relation and modifier triple in a sentence, like automatically discovery the relation type between entities in a sentence. So I think it should be very important, especially for low resource languages where the knowledge graph is not available. I mean, it's not much available at the moment. Like in Vietnamese, we even do not have a VerbNet, as Lee Jong just mentioned. So I think it should be very important step for building a syntactic parser.
I see. Thank you.
Can I ask
yes,
a
ahead.
follow-up question? So,
Yes.
do you find the scheme from universal dependency readily applicable to the Vietnamese language? Do you find certain relations don't quite fit well with the grammar in Vietnamese?
So, yes, I found it's quite adaptable to adapt the universal schema into the Vietnamese language. The problem might be on the characteristic of the languages. So Vietnamese is sort of like isolated language and the SVO. So the grammatical structure may be easier than the Thai language, I guess. So we can somehow adapt the universal schema into building a universal tree bank for Vietnamese. But I think Thai language might be more difficult than that. So maybe you might want to develop their own, universal relation type. The relation type, dependency relation type specifically for the Thai language, instead of using the universal ones.
Just now you mentioned that Vietnamese is a more isolated language. Can you elaborate more on what you mean by that? I'm quite curious.
So we don't really have something called rich morphologically rich language. So we are not. So each word type is sort of like have its own meaning. So especially, maybe it's not like that 100%, but for the entity names, the word names, like 40% of Vietnamese people have the same family name, Nguyen. So whenever the word appearing with the syllable Nguyen, so you know that is a family name. So you somehow have such kind of information, but for the non-entities word, so we don't have that kind of information like clear. We don't have that kind of feature in other words. So that's why we still consider Vietnamese an isolated language. And most of the problem when we deal with the tokenization, so normally most of the errors come from the entity names, the word names of the people, where we have the disambiguation between the names and the organization, where it's somehow merged together when it's present next to each other in a sentence.
I see. Do other people want to share some unique challenges for the languages that you've worked on before?
Yeah, so I would like to so if we take that question you just asked, what kind of linguistic theories are important and why are they important, sort of thing, right? So if we look at the spectrum of low resource languages, we would see languages like Thai, which is not really low resource, you just said now, but compared to English, it's much more low resourced. And then we have the other end of spectrum where we have absolutely nothing. So a language like in India, we would have languages like Gondi or Santali, which has millions of speakers, but absolutely no digital resources. So if you look at this entire spectrum, so this is a very interesting question, because in India also this question is being asked by the at a level of the government, that if we were to provide NLP support for all Indian languages and build a stack, NLP stack, so to say, should we go with morphology, syntax, and that kind of an approach, or should we go with deep models? And to me, it seems like both are important depending on which part of the spectrum you are operating on. So a language like Hindi, which is almost like Thai, fairly high resourced, deep learning works pretty well there. Whereas if you go to the lower end of the spectrum, I think more linguistically oriented language resource based models work better. So that would be one part of my answer. The second part is, if you look at the high resource languages, the other side of the spectrum, there too, linguistics become important when you want other kind of guarantees. Like, can you explain why you said this? Can you explain why the sentiment was classified positively or negatively? So explainable NLP. Then if you are talking of more like, pragmatics, so then, or even Li Dong mentioned that knowledge bases are very important. So when you are trying to integrate knowledge bases, then it's an interesting interplay of both symbolic reasoning and neural methods. And at that time, maybe linguistic theories are again important, but it might be a slightly different kind of linguistic theories, which might be interesting to look at. And the last point I would like to make is, again, about typology. So even in the neural space, when we are talking of pre-trained model, people have already observed that if you put all languages together, that may not be always the best solution. So you might want to, build smaller models where you put closely related languages together, where one or two of those are high resource and the others are low resource, and then you get better benefit. So to give an example, if I put, let's say, Hindi and Marathi and Bengali and all those languages in a single model, I might get better benefit than if I put all these languages with all the other languages of the world, let's say 100 such languages in BERT. And it's primarily because the code space of subwords and all get reduced per language if you put a lot more languages. So there, I think it's again pointing to a new kind of linguistic analysis, which probably is required to understand what works best for these neural models and which languages can help which languages better. So language family and typology are certainly good cues, give good clues or starting points, but there might be more to it which we can discover as we go on.
Thank you for sharing. I'm going to switch gears a bit. Some of the questions were related to COVID. So like the pandemic has definitely changed how we live and interact with each other. So do any of you want to elaborate on how the pandemic has shaped recent developments in your work? This can be on the research front or from the commercial front, that the market needs are becoming more different. Bill, do you want to give it a go?
I'm sorry, I haven't followed your question. Can you repeat?
Oh, so my question is, with the COVID pandemic, how might that have changed, your business model or how you train models, or because there are different market needs now?
Okay, yeah, it is a very good question. So in this COVID situation, I do believe all kinds of business have been have been affected. Some kind of business have a big jump into a new stage, but some business have been damaged a lot. yeah, especially for some offline e-commerce areas. To offline e-commerce, to online e-commerce like Lazada and other e-commerce companies in Southeast Asia, yeah, they have get a lot of increasement, yeah, during COVID situation. Why? Because during COVID, yeah, a lot of person cannot easily go out to buy something, but in our online platform, it's very easy, and a lot of FMCG and fashion product, yeah, have been sold very, very have been sold out in different kind of sellers. Yeah. So to this part, I think to e-commerce, this is a very good opportunity, yeah, for our business growth. Yeah. But to other offline shops or a lot of malls, yeah, they have been affected a lot. To us, yeah, I think we do have much more customers, and their requirement have been centralized into a lot of categories, as I mentioned there. But to our yeah, today we are discussing about language processing. So I also I'm trying to find out a relationship. Actually, to us, I think, yeah, to Lazada, yeah, we do have created some effort for the COVID situation. Yeah, to language processing part, I think the greatest effort from us is we have put more linguistic experts to label our data, especially in Indonesia and in Thailand and in Vietnam and in Malay. In Singapore is very, very promising. Yeah. Actually, to read March, we have got 2 or 3 times requests than normal days. Yeah. So I think this time after COVID situation, yeah, the business part in Southeast Asia will be changed. Yeah, to some extent. To us, we do think we are going to put more effort for our language resources labeling, yeah, by tokenization and by named entity recognition and by classification and even by a lot of address tagging here. Yeah, so I think this is also a good news to us. Yeah, but the bad news is we do hope COVID can be passed very soon, but now we are facing new challenges, especially in Singapore and in our whole Southeast Asia. I hope everybody you can keep safe firstly. Yes, thank you.
Thanks for sharing. Li Dong, you want to elaborate if any of the pandemic has changed recent developments in your work at?
Yeah, I think because we at the Dharma Academy, we don't have too much touch on the end business like Bill did. So the largest impact on me is I have to work from home. And it's really tough for me to communicate with the team, and particularly before the paper deadline, because now the Dharma Academy is co-training the PhD students with the Singapore universities, particularly before this year's EMOP deadline. Right in the middle of the circuit breaker of Singapore, it becomes very difficult for me to communicate with the students, and working at home is a big headache because of my little son. That's the interesting experience.
I see. Yeah, I guess this is an ongoing challenge for many of us.
Yes.
I think for COVID, I got like a new research topic from here actually, because we cannot have, I'm a university professor, we could not have final exams or like exam anymore because we cannot have students on campus. So, but we still have to give them exams somehow online. So we have to design something that's like hard to cheat on, has to be like open book-ish kind of stuff. So, and it cannot be multiple choice. Because multiple choice is so easy to to cheat on, right? You can just like send the list of answers over whatever platform while they are taking the exams. So most of the exams have to be short answers that are, harder to grade, and we have to grade it at scale. So I try to come up with some stuff that can do like somewhat few shot, zero shot learning for grading when the questions are not factoid anymore. Because when we talk about Q&A, we talk about factoid, right? You got the Wikipedia article, you highlight a place and then you turn it into a question. But now, what I ask is that why is 4-gram language model can be worse than bigram language model? That would be the kind of question that the student will have to answer. So yeah, so I try to come up with some sort of algorithm. So this is a new project for me actually, so that I can scale grading and hopefully can deploy it for other subjects as well, so that education can go on without resorting to all multiple choice questions, because that's the only way that we can deliver the exams in the scalable way. But yeah, so that's the new research topic that came out of COVID for me in the university setting.
Yeah, yes, a lot of unexpected opportunities. Anyone else want to share your experience?
Yeah, so I probably can say a very short experience. So I think it's I'm still single, so I don't have so I'm happy to work at home. So it's still not really changing my life, because the government have very good control over the COVID. So in Vietnam, we pretty safe at the moment. But it's add into my research topic, where we want to focus on developing high quality annotated resources for Vietnamese. But I now focus on the COVID-19 domain. So so that's like I want to develop some sort of NLP task, but for the healthcare for COVID-19 understanding, instead of a very general NLP data.
Makes sense. It's very meaningful.
Yeah. So for me also, it has been similar to finding new research problems, because what happened is, as soon as COVID started, there was a lot of asks for building chatbots for multiple Indian languages, that we could enough data set for a large number of Indian languages, or systems that could be deployed. So the answer was mostly negative. Sorry, we don't have any resource for this language. We can't help you here, etc. Very disappointing. But then this also gives us an opportunity to be prepared for the next pandemic. So we started working on NLP for healthcare. So thanks to COVID. And of course, I mean, this is an old area. A lot of people have been working on it very actively, but personally, I didn't. So COVID was the push for me to work on NLP for healthcare.
So here, maybe, I'm sorry to interrupt. Actually, to this COVID situation, maybe our one domain in natural language processing should be very hard, is sentiment analysis and sentiment trend tracking. And a lot of governments, they are tracking what kind of sentiment have been caused from their population, and what kind of new topics they would like to discuss, or anything require the government to do something to help their population. I think that may be a new topic, especially on COVID situation.
I see.
In Singapore, I think the government have done a lot of effort. Yeah, all kinds of information, they are transparent to everybody. Yeah, and we have a lot of discussion in some forum and topics there, and I think this is very useful for COVID, even for healthcare. Yeah. Okay. Thank you.
Yeah. So yeah, I guess someone from the audience is asking, how can NLP help with the COVID pandemic, which I think is partially addressed a bit, but does anyone want to elaborate more? So if not, there's another question from the audience. So this is related to machine translation, saying that so from this person's observation, when you're translating from a low resource language to English, the translation is often better than the other way, where it's from English to the low resource language, even though the training data might be the same. So I guess this person wants to pick on the brains of the panelists if you have any insights or sharing of how to address this issue.
Maybe I can take this question. So yes, you are right. And if you look at the older systems, right, statistical machine translation system, it was much more obvious. And the reason is when you translate, let's say, from a low resource language to English, what remains same is the parallel data. But and the parallel data is used to learn the transfer model, so to say. But you know, at the end, you use something called a language model at the target language side to rank your translation. So you know, let's say I have 20 different possible English sentences that my decoder gave as output. So by the way, this is true for also neural decoders, not statistical decoders. But statistical decoders, it's easy to understand because it happens very explicitly. So when the decoder gives me, let's say, 20 or 2000 sentences, I choose the best output based on my language model. So the better the language model, the better the output of the translator. And therefore, you know, the fluency of the translated output is much better in a high resource language than a low resource language, even though the amount of parallel data is same. For neural, you can imagine that, you know, the encoder and decoder are there, and the encoder's efficiency depends on how good is the data in the source language, both pre-trained and as well as the parallel data. And similarly for decoding, it's how good the data is for the target language. So when the target language is English, so it's always more fluent output in that language. Does that answer your question? Or if any one of you want to add anything to that?
Yeah, so thanks a lot. I think if there are other follow-up questions, maybe we can take it offline. So yeah, so there are a couple more votes on asking how NLP can help healthcare and the pandemic. Does anyone want to elaborate more on this before we move on to some other topics? Okay, so yeah, so some other question. Please,
sorry.
go ahead.
Yes. Nancy, you just mentioned healthcare and COVID. You know, in natural language processing, there is an old area is bioinformatics. To that part, there are a lot of experts and researchers have spent some time on the biodomains lambda entity recognition and even some tokenization and language relationships between all kinds of entities. Actually, I think that is very useful for our healthcare. During COVID, I don't know whether any expert have spent some effort on this new arrow to combine COVID and bioinformatics arrows together. Maybe I think maybe it's a potential opportunity for us. Another way is to COVID. Just now I mentioned some topic is sentiment analysis and sentiment tracking and topic tracking, things like that. And to COVID, yeah, now a lot of persons they also have a lot of panic, about when we can finish the COVID. Yeah, so to that part, maybe we can consider some multi-document summarization to this kind of topics. Yeah, is also maybe something related. Yeah, now I think everybody needs information from COVID, from government, from the whole society, even from other countries in whole Southeast Asia. It's quite related to everybody's daily life. Yeah, thank you.
Thank you. Okay, so I guess we're coming to the end. So looking towards the future, since all of you are leading figures in low resource NLP and especially in Southeast Asian languages. What do you think we can do to raise global awareness so that research and applications in Southeast Asian languages can thrive and attract more support? Any thoughts that you want to share or propose, or for the rich companies you want to help out a bit, help out the academics?
I'm sorry, I need to speak something here. Firstly, because I ever worked for SQR with Nancy. Yeah, so we are colleagues before. So during the period, I found in Southeast Asia, yeah, we already have some language resources union, yeah, from maybe around 7 or 8 countries together. So that day, our goal was to create some parallel data for machine translation. But nowadays, I don't know the new situation. But to me, I still believe if we can share more resources to link different languages together, it will be a good opportunity for our machine translation. And to our some monolingual languages processing, yeah, I do believe the fundamental part is also we need to label more data. If we can have more data from different aspects, we can have better future. Nowadays, a lot of low resources research solution is based on unsupervised learning. Yeah, but I think nowadays manpower is very, very expensive to do this kind of labeling. But to Lazada, we do believe we should spend more money to do this kind of effort. In future, we do hope we can contribute and share some resources to everybody. Thank you.
It's very good to know. Thank you. Anyone else that want to share your thoughts on how we can raise global awareness and get more resource and support?
Yeah. So at Alibaba Dharma Academy, we also preparing some low resource language data set, and we're about to share with the community. And I think beside the data, another point we can work together is should we set up sort of a conference that specifically focusing on the low resource language processing. Maybe it can be a small, cohesive, small scale and cohesive conference or forum that specifically for low resource language processing. And no doubt it can draw attention from the communities in both Europe and the US, because there are also many researchers working on the low resource setting. But anyway, in such a conference or forum, we will come together and have more brainstorm, and then to come up with more advanced techniques to process these low resource languages.
Yeah, I have to agree with that, because I work on Thai mostly for the past few years, and like the comment that I fretted the most to get back from the reviewer is that how is it different from English, right? Although like everything is different. The answer is always everything is different, but the feedback from the community always like, well, we know this already. It works with English, it has to work with this language too. It's not always the case, right? But so I feel that it's more like a complaint than a solution, I guess. So I guess like I agree that we should have at least some sort of venue that that focus on low resource languages, because sometimes like your work is mostly create a corpus and recreate what we have for English, because if we don't have it, then we cannot do anything else. When I got back here from the States, I have to start from word segmentation, from the very ground up, right? Because there's no real benchmark, there's no real corpus that you can always rely on. So that's part of it. So I feel like research in other languages other than English is is often marginalized, which you cannot all blame it on the community alone, right? Because they might not be interested in other languages, which is a fair point. But yeah, I think we should have the stages where this line of research is actually important for the industry and for the development of technology within the region as well.
Yeah, I think having a conference can also help educate the other people. Yeah, in addition to provide a venue for researchers to interact. Anyone else want to add on to this?
So I would just say, tell Tay that, and everybody here, not only in the panel, but everybody in the room, next time you review a paper and it's working only for English or some high resource language, ask this question: are you sure it's going to work for Thai? It's going to work for Vietnamese? If not, I'm not going to accept your paper. I mean, you have to explain. Yeah, but jokes apart, yes, I do agree that it's very, very marginalized, and that's the first thing that we should do. So in our this year's ACL paper on this linguistic diversity and inclusion, we proposed that there should be a DNI clause, that every paper that is submitted to the conference at least gets to answer this question: that are you aware that, I mean, are you aware which languages your system is going to work on? Yes or no? And which is it promoting linguistic inclusion and diversity in technology? Of course, your answers can be no and paper can still get accepted, but it's a way to make sure that everybody is aware of these issues.
Okay, to future, another suggestion is maybe we can consider to co-organize some low resources language processing related tasks, like a competition. Then we can draw more attention from other researchers. Then it will be very good for our language processing progress.
That makes sense. That and Lidong, you want to elaborate a bit more on this? Like it could be a wish list that what you would like to see in our field.
Yeah, I think another random idea I just mentioned to my colleague in the strategic collaboration department of Alibaba is it seems now we don't have a unified organization working, or even a virtual organization working on the low resource languages. Say in Southeast Asia, it seems in Singapore we don't have such an institute to working on these local languages. Maybe as more and more Chinese companies came to do their business in this region, and we know that ByteDance and Tencent, Alibaba put their overseas office in Singapore. Maybe it's the right time for us to think about set up such an institute that working on this low resource language from both industry side and the university side, because on one hand, these low resource problems are very challenging for the real business. And meanwhile, this problem setting is also very interesting for the academia researchers. Yeah, just my random idea discussed with my colleague within the company.
Okay, thank you very much. Anyone want to make one last comment before we wrap up and move to the next session?
Today's session, I think, is very impressive. Yeah, I do hope this is a new opportunity and a starting point for our future, especially to Southeast Asia language processing. I do hope we can meet again for some general topics. Thank you.
Yeah, I think the feeling should be mutual. It's an important area that many are interested in, but maybe under discussed. So this is a good starting point to work together for the community. Okay, so I think if there are other questions, we'll take it offline. So you can contact the panelists through email or on the Slack channel. And so thank you very much for sparing your time for attending this panel discussion to share your insights with everyone. And thank you, the audience, for all the questions and participation. So hope to see you soon.
Thank you, Nancy.
Thank you, Nancy.
Thank you.
Thank you, everybody.
Thank you.
Bye-bye.
Thank you, Nancy, and everybody. Bye-bye.
All right, thank you. Um, Hi, Jing.
Hi.
Hi, yes, the floor is yours.
All right. Okay. Okay, so we are starting the, I guess, the last session of today's program. So yeah, I'm very happy to be here to introduce our last speaker for today, Professor Yulan He. So I believe Professor He is no stranger to many of us here. In fact, Professor He obtained her bachelor's degree from Nanyang Technological University. And then she went on to get her PhD from University of Cambridge. So currently, Professor He is at the University of Warwick, UK. She's also the Director of Research at the Department of Computer Science at the university. I've known her for a long time, largely because I think we share a lot of common research interests. So her research lie mostly in the integration of machine learning and natural language processing for text analytics. She has published over 170 papers on various topics, including sentiment analysis, topic analysis, event extraction, clinical text mining, recommender systems, and spoken dialogue systems. And as many of us know, she was one of the program chairs for this year's EMNLP. She's also currently holding the Turing AI Fellowship. All right, so without further ado, let's welcome Professor He for her talk.
Okay. So I think I should share my screen. Right?
Let's share your screen. I think.
Okay, yeah. Thanks, Jing, for the nice introduction, and it's my great honor to join this symposium. So I suppose you can see my screen now.
Yes.
Right. Okay. Good. Yeah. Right. So in today's talk, I'm going to share with you some of our recent work on analyzing product reviews. Basically, people express their subjective experience and feelings towards products and services. So that's what you can typically see from Amazon review website. We have recently developed a series of models for analyzing product reviews. This include a neurogenerative model for joint learning topics and topic-specific word embeddings from review text, a question answering model for generating answers given queries and their associated reviews. And more recently, we have been developing this so-called brand topic detection model, which aims to detect brand associated polarity-bearing topics from product reviews. Now, different from existing models for sentiment topic extraction, which assume topics are grouped into discrete sentiment categories, such as positive, negative, and neutral, this model is able to automatically infer real-valued brand associated sentiment scores and generate fine-grained sentiment topics in which we can observe continuous change of words under a certain topic, while its associated sentiment gradually varies from negative to positive, as what you can see from this figure. And at the last model we developed here is this so-called joint sentiment classification and aspect abstraction model, which does not require aspect level annotations. The only supervision information needed for model learning is document level sentiment labels. And the model can automatically separate positive and negative aspects despite not requiring aspect level annotations for model learning. But in today's talk, I will focus on the first two work we have been developing for analyzing product reviews. Right, so the first model we have developed is to join learn topics and topic-specific word embeddings from review text. And this is our tackle paper appear in this year. Right, so before delving into the details of our model, I would just first give you some overview of this classic word embedding learning. So in classic word embedding learning, as you can see from here, this shows the word embeddings learned by GloVe. We can see that the classic word embedding learning methods will map each individual word into a single vector representation. And in this figure, it actually shows some underlying concepts that distinguish between, for example, waiter from waitress by sex or gender. And this can be equivalent specified by various other word pairs, such as actor and actress. Now, more recently, we have seen a range of different contextualized word embedding learning methods. So that would include ELMO, which calculates the weighted sum of different layers of multi-layer by a directional LSTM-based language model. And also BIRD, which was proposed to apply the bidirectional training of transformers to mask language models. Now, in this contextualized word embeddings, each word would be mapped to a separate word vector depending on the context it occurred with. So we can see here there is essentially the extremes of two opposite ends. So in the classic word embedding, it learns a mapping function to project a word to a single vector in an embedding space. And you can imagine that because a word could have multiple meanings depending on its context. So classic word embedding learning methods cannot deal with this polysemy phenomenon. On the other hand, these contextualized word embeddings, they generate different word vector for each occurrence of a word depending on its context. Now, we actually argue that the word meaning can be inferred from a word associated topics. For example, the word patient has two different meanings. And this meaning would depend on its associated topics. So when analyzing reviews about restaurants and health services, we can somehow infer the underlying semantic meaning of patient, depending on its topic. And that's why we propose this topic-specific word embedding learning methods, which sits in between the classic word embedding learning and contextualized word embedding learning. So to learn this, to learn these topics and topic-specific word embedding representations, what we assume here is we could learn a topic model which generates both the target word, or sometimes we call it pivot word, and context words. Now, this target word is generated by some hidden semantic vector which encode a local context. And this hidden semantic vector can also be transformed into some topic distribution, which would enable the generation of context words. So so basically, like, we can infer this hidden semantic representation of the word through some inference network, given the pivot word and its context window. Now, this process essentially would enable us to quickly gain some understanding of the underlying word semantics through the topical distribution, and also enable us to learn the latent topics from the corpus. So our rationale here is context words can be generated by the hidden semantics of pivot words together with some global topic matrix, and which capture the notion that the word could have multiple meanings that are shared across the corpus. So our assumption is that each word basically embodies a finite set of meanings that can be interpreted as topics. And each word representation can be transformed to distributions over topics. And context words would then be generated by first selecting a topic and then sample according to some to the corresponding multinomial distribution. And in fact, we can use this graphic illustration to show this generative process. Here, what we could do is, if you are familiar with this, like LDA latent Dirichlet allocation generative process, then this will follow a similar route here. So for each word position in a text, we first draw some hidden semantic representation for the target word from a uniform distribution. And afterwards, we could choose a pivot word, basically that's generated dependent on this hidden semantic representation. And then we can transform this hidden semantic representation of the target word into topic distribution by some deterministic transformation here. And then for each context word position, we first need to choose a topic sample from this categorical distribution given by this zeta. And then we can choose a context word, which would be determined by this global topic matrix beta, and then chosen by the specific topic index. And in reality, we would actually marginalize out this topic indicator. So this is a kind of a joint topic learning and also topic specific word embedding learning method, in which we distinguish the word meanings by its topics rather than the context. And this figure shows the overall architecture in which it consists of two main components. One is this encoder, the other one is this decoder. Now this encoder would actually, so we can ignore this encoder part and we look into the decoder part. The decoder part is exactly the same as I just described the generative process for generating the target word as well as the context words in text. So here you can see that we first would have this hidden semantics, which is represented by Z here, generate both the target word X and also its context words represented by this plate diagram, which contains of a capital C number of context words here. So we can see that this hidden semantics would directly generate this target word, but it would be transformed into some topic distribution to generate the context words. So the learning of this model, essentially what we want to do here is given the observed variables, the target word X and its context words W, basically that might be consist of a range of context words depending on the size of the context window. Now the objective here is to infer the posterior of the latent variable Z here, given the observed variable X and W. Now this is intractable, so that's why we resort to this variational autoencoder framework, which aim to minimize the KL divergence between this true posterior, the probability of a Z given the observed variable X and W, and also this variational distribution. So we use the VAE to learn the parameter. And this can be achieved by minimizing, by optimizing the evidence lower bound. So in the evidence lower bound, now we have two options here. We can either represent this input, the target word and the context words by the backward words representation, in which we ignore the word order. Now in this case, we can actually write down this generative probability of generating the target word and context words given the hidden semantic representation of the word, and proportional to this equation. So essentially, this is a kind of a simulated multinomial distribution of generating the words given the topics. Now there is another option here in which if our input is no longer this backward words representation, however, we actually use those contextualized word representation as the input, such as the contextualized word embeddings generated by either Elmo or by Bird. Then in this case, we need to modify the way we generate the target word and context words. Now here we use this particular use this kind of a particular equation. This is because essentially, what our training objectives becomes to make the reconstructed the word representations X and also the W as close as possible to their original input word embeddings. And the difference here can be measured by the angle between the input and output vectors. So essentially, this normalized the Elmo and Bert vectors, which, if we use those contextualized word embedding as the input to the model, they can be transformed into some polar coordinate system with these trigonometric functions, which will form the probability distribution by integrate from 0 degrees to 180 degrees. And then in that sense, this kind of representation can actually use to simulate this probability density function. Right, so that's just like a two prospect kind of input setup. So we can either have this backward words representation as the input, or we can have this pre-trained contextualized word embedding as input. Now, in terms of experiments, we collect the review data from Yelp reviews, and Yelp reviews consist of a range of different business categories. We choose the top 5 business categories, which is listed here, and we balance the data set by sampling roughly the equal number of reviews from each category. And we also show this rating distribution of each business of reviews in each category here. And we can see that the data set we have, it has this imbalanced rating distribution. So most of the reviews, they have this positive or 5-star rating, and then followed by this very negative kind of ratings scores. And the reviews with ratings between 2-star to 4 stars, basically they are less compared to the reviews in other rating categories. So in terms of a baseline model, we compare with this Bayesian skip-gram model. And in fact, our model is inspired by this Bayesian skip-gram model. Now, this figure shows the generative process of a Bayesian skip-gram model. Now, in BSG, the latent embedding, there is also some latent embedding for the target word, and also draw from the Gaussian prior. However, the context words are generated directly from this latent embedding, as opposed to via some mixture model as in our proposed approach. And for this reason, our model is able to group semantically similar words into topics, which is not the case in the BSG. Now, the next baseline model we compare against is this CVMF. Now, it's rewrote this glove objective function as some cumulative product of normal distributions, in which each factor is multiplied by these von Mises feature distributions, in the hoping that based on these VMF distributions, the context words can be clustered together because this VMF density retains this cosine similarity between the word vectors. And another baseline model we consider is this so-called skip-gram topic word embedding model, and in which it adapts this skip-gram model by associate 2 matrices with each word. So one matrix will be used when the word is a pivot word, and another will be used when the word is context words. And then it just used some expectation maximization to estimate the model parameters. And the last baseline model we compare against is this mixed membership skip-gram model. So it also assumes the topic is drawn for each context, and then word in context draw from some log bilinear model based on the topic embeddings. Now this MMSG is actually trained by alternating between some Gibbs sampling and noisy constructive estimation. So the training process is different from our model, and also this MMSG only models the generation of context words, but not the pivot words. So that's also different from our approach. And among these baseline models, the CVMF and BSG, they only generate the word embeddings, so they don't model the topics explicitly. And both these, the last two models, STE and MMSG, they can learn topics and topic-dependent embedding at the same time. However, in STE, the topic dependency is actually stored in certain rows of the word matrices, and word representation themselves, they are context independent. And this MMSG actually can produce these contextualized word embeddings just by summing up the topic vectors weighted by the posterior topic distribution given context. Right, so in terms of evaluation results, we first compare the results with this different baselines on this benchmarking data set typically used for the evaluation of word embeddings. Now, because these word similarity tasks, they require context-free word representations. So for those models which generate contextualized word embeddings, we aggregate all the occurrences and obtain a universal vector for each word. And then we use the distance between the two word vectors as the similarity score. So the table shows the results of our model, which is this joint topic and word embedding learning model in comparison with all the baseline models. Now our model outperformed the others only on one data set. However, on the other 6 data sets, our model actually performed in the second position on 5 out of 6 data sets. And on average, our model actually outperforms the other models. So the previous word similarity task, they focus more on the general meaning of a word. Things like word pairs are presented without any context. Now the next task we consider here, lexical substitution task, was designed to evaluate the word embedding learning methods regarding their ability to disambiguate word senses. So in this case, the word context will be used. Now, on this particular task, we evaluate our model on the data set from this SEM-eval 2007. And the task here is given this sentence highlighted in blue, and also given the target word match, the model need to identify the alternative word which can be used to replace match here. So you can see that in order to be able to perform this lexical substitution, the word embeddings need to encode the contextual information here. So the results here show that our model basically performs better than the other baseline models. So it essentially shows that the way we model the generation of pivot word as well as the context words, and also the use of the VAE framework for parameter inference is more efficient than, for example, this negative contrastive estimation methods used in the MMSG. And next, because our model can generate the topics as well as these topic-specific word embeddings, so we also compare the topic coherence scores. In this case, we only compare with other models which can also learn the topic at the same time. And by varying the number of topics, we have a different topic coherence score. But generally speaking, our proposed model, which is this JTW, gives the better results compared to the others. And here we show some example topics by listing the top 10 words sorted by their associated likelihood for each topic. And the topic label here are given manually. Here we can easily deduce actually from the top words that the discovered topics represent the food, shopping, beauty, automotive, and also clinical. And in this figure, we actually shows the topic distribution for each word. Now we specifically choose some choose the 3 words plastic, bar, and patient to illustrate the polysemous nature of these words. And we can infer from this overall topic distribution of each word that plastic here, so which is highlighted, by the histogram with this red kind of marks. So this word plastic would associated more with the shopping and also beauty category, as you can imagine that when it's used in shopping, it probably refer to plastic bag, right? And in beauty, it probably refer to plastic surgery. And the meaning of this bar actually would be more prominent in food and also in shopping. Now, patient here is actually, we see it has the highest topic association with clinical, right? So a patient as referred to the patient basically in clinical services, but it also has a certain level of association with the food, right? So sometimes if you say the waiter is very patient in serving the food, right? So in that context, patient actually has another meaning. And in this case, we actually show this visualization of the sentence semantics. We only illustrate 3 example sentences. So when considering the specific context about patient, and we can see that the sentence 1 has its topic distribution. So the sentence 1 is here, right? Has its topic distribution picked at the clinical topic. And sentence 2 also contains the word patient, but it now has a topic distribution over the picked at the food, right? Because this is has another meaning. And finally, for the plastic word plastic, because it's mentioned the plastic bag, so its most prominent topic would be the shopping. Finally, what's more interesting here is we actually, what we can do here is for all the methods which, generate these topics, sometimes render topic and also topic specific embeddings, we could just add an additional by directional LSTM with a softmax layer to perform the sentiment classification. So in this case, we use the data set we constructed. As you have seen in previous slide, each review has a rating score, and we have a total of 5 rating categories. So we performed this 5-class classification, and that's also imbalanced class classification problem. So in terms of this classification results, if we just use the topic-specific embeddings generated by our model, it performs worse than Elmo or BERT. This is somehow expected, right? Because the Elmo or BERT, they capture this contextualized word embeddings better. However, what's interesting here is if we combine this, our proposed model with Elmo or BERT, so in the sense that the input to our model is now the pre-trained Elmo or BERT model, then actually we observe increased classification accuracy. So these results actually show that our proposed model can capture this domain-specific sentiment better compared to directly fine-tuning this pre-trained language model on this particular data set, as we have seen from the results here. So that would summarize the first part of my talk, so in which we propose a new probabilistic generative framework which can learn latent topics and also topic-specific word embedding simultaneously. We have conducted a comprehensive set of experiments to verify the effectiveness of the models. And we have shown that the model can discover the latent topics shared across the documents in the corpus. And we can somehow review this polysemous, kind of a nature of the words by visualizing the word semantics captured by our model. And finally, the model can be easily integrated with existing contextualized word embeddings generated by other large-scale language models to improve the results on sentiment classification. So in terms of a future work, what we could do is we can possibly explore these cross relationships between the neighboring sentences in text in order to model the semantic shift. And the other possible direction here, the model can be extended to track topic dynamics and language semantic change over the time. So for example, if you want to analyze the language change of indicative of mental health problems, so this might be something could be considered in that particular use case. Now, in the second part of my talk, I'm going to share with you our proposed approach on generative review question answering. So in generative review question answering, we are particularly interested in developing a QA system for answering questions from some e-commerce platforms or communities based on the customer reviews. So we have an example here, which extracted from Amazon reviews. So usually, like if you want to buy a product from Amazon website, you will see the reviews from the customers, and sometimes users could post their questions, and they would receive answers to their questions, and those answers would also receive some votes, right? So the other users can vote on its helpfulness of this particular answer to the query. So broadly speaking, there are two types of this review question answering tasks. So the first one is given the question and a set of reviews associated with this question, we can perform this so-called extractive review question answering. And this is closely related to information retrieval or spam-based QA because the answer can be directly extracted from the review text. Another task here is this so-called generative review question answering, in which this is closely related to generative multi-passage QA, because it requires the aggregation of relevant evidence scattered across multiple review documents in order to generate the final answer. So in this case, the answer is actually generated rather than directly extracting from the original review text. Right, so there are a number of challenges so there are a number of challenges which we faced on building this generative QA task. Now, one is for the data set we use here. So our data set built from these Amazon reviews. Now, there are multiple ground truths, right? Because like for any one question here, there are many possible answers to the same question. And so another challenge here is the review text usually is quite long, and also the answer text is also long. Now, the next challenge here is that there's a lack of these explicit relevance annotations, right? So we don't know among all the reviews associated with the particular product, which review would be more relevant to the particular question. So that there's no annotation about this. And finally, there might be some contradictory opinions or contradictory statements from different reviews. Right? So there is basically quite hard to verify which one is factually correct compared to the other. So what we propose here is this so-called hierarchical memory. This hierarchical kind of a memory network for this generative review question answering. And we show this overall kind of process here. So given a question and a range of reviews, now in our data set, each question is paired with 10 reviews. We aim to learn a model which can generate the answer, right? So we can see that in this example, the single question might consist of 2 sub-questions, right? So in this case, users actually ask 2 different questions. One is, can I set it to 30 seconds? Now another question is, can it will automatically reset, right, to the 30 seconds continuous? So there are actually 2 sub-questions in this question. Now, another kind of things is in order to answer this, this question, we need to aggregate the evidence, basically scattered across multiple reviews, and to generate the final answer. So during the training, in fact, essentially like what we are doing is we choose we select the single answer which received the highest helpfulness vote. So in this case, like 100% helpfulness vote as the gold standard answer, and pair with this question and related review text to train the model. And the model will aim to generate the answer. So this is the kind of a high-level description of our model. Now, the model architecture is shown here. So our model is built on XLNet because as has been previously shown in other work, these pre-trained language models, they can be used to implicitly model the knowledge base. So that's why they can usually like we can use them for language generation. So here, because XLNet, it combines the advantage of autoregressive and also autoencoder models for language generation. So we built our model based on this XLNet. Now, this is the model is a so-called cross passage because this model process multiple reviews and gradually combines and also aggregate the evidence from these multiple review passages and use this dual memories. So in this case, it makes use of both the context memory and also the answer memory to simulate the reading comprehension cognitive process. So in this model, the context memory is used to dynamically collect the cross passage evidence, and answer memory will store and continuously refine the answers generated as this models reads this supporting review text in sequential manner. So if we look into this model, in more details, so the first part here is to read the input text. So when reading this particular review case, so denote the case review document, and this review case will be paired with the question and also answer. So that's during the training phase. And we have this associated gold standard answer. Now, the model actually fit into this question review and answer triplet into this XLNet encoder. Now, during this encoder stage, we actually use this XLNet encoder with sequence-to-sequence mask. So essentially, you can imagine that we fit this into this XLNet encoder, and in fact, there is like an encoder-decoder structure, and you will aim to generate the answer. Now, this is only used during the encoding stage in order to enable this XLNet to better capture the hidden representation of the input. So in this case, you can see that the question will be mapped to this hidden state for question and review mapped to this hidden state to review, and so on and so forth. Now, here we actually would treat the input highlighted in red as part 1, And the, you know, right, okay, so and the input highlight in blue. So basically like the input highlight in both red and also yellow as part 1, and the input highlight by in blue as a part 2. So we can see that in this kind of encoding stage, the part 1 would encode would attend to any of the other tokens in part 1. So there's some kind of self attention applied. And in part 2, it will only attend to those previous preceding tokens in part 2, and also any tokens in part 1. Okay, because part 2 actually consists of this generation of the answers in this stage. Now, it's worth noting that, I mean, this is actually only used in the training phase. It's not used in the testing phase. So training this XLNet with this kind of encoder-decoder task can be considered as a fine-tuning this XLNet on our corpus in order to learn a better XLNet encoder. So this is the first step. Now, in the second step, what we are doing here is we use this hidden state of this, this is the part 1, to initialize and update the context memory, and the hidden state in part 2 to update the answer memory. So let's look at the update on the context memory here, right? So this hidden state from this part 1, I mean, from the both question and review, would use as the key and value, and then to update this context memory. So we can see that the previous context memory will use as query, right? And essentially the memory update will be accomplished by taking this weighted aggregation of the previous retained memory and the current hidden states using some forget gate. So the G here denote the forget gate here. And the gate is actually just obtained by using the MLP layer with some memory-specific transformer encoder. So essentially, we can see this, we have this transformer architecture, which takes the context memory of the previous memory as query, and the hidden states of the current context, in this case, the hidden state from the question and also from the current review document as key and value. And then basically like through this kind of transformer architecture, we can update this gate value. And this would determine how much we want to retain from the current context and how much we want to pick from the previous context memory. So that's the first step. In the next step here, in fact, like we use the last SEP token from the part 1 and then put it into the hidden state for the part 2. So we use it as the starting token of the part 2 for language generation purpose. Now with this newly updated memory, so with this newly updated memory, and the model is able to use the hidden state of the answer part to update the answer memory. So the updating process of this answer memory would be similar to the context memory. We use the updated this context memory, the updated context memory. So from the, you know, basically like the content memory has already been updated as key and value, and the hidden state of this part 2 as the query. And then through the same architecture, basically this, and also we can calculate this forget gate to determine how much the answer memory need to be updated in order for the answer generation. So you can imagine that, you know, during the actual training process, no matter how many review articles we have associated with a particular question, we can perform this kind of iterative update continuously, right? So, so that's the kind of overall architecture. And in terms of a setup, we built a data set from this Amazon review QA review data set. We only focus on descriptive questions. We do some kind of filtering based on, you know, based on the answerability. and also filter out those yes/no answers. And in terms of metrics, we use a number of different metrics to measure the lexical similarity and also semantic similarity, and also the evaluation of the both. So in terms of baselines, we compare with this randomly selecting a sentence from reviews, or retrieve the sentence which has the highest cosine similarity with a given question. And we also have a way to basically generate the answer based on the pre-trained BERT or pre-trained XLNet. Now, because our review documents will be much longer, than any of the typical kind of input text can be taken by BERT and XLNet. So we perform the summarization on the review text first before feeding this review context into the BERT and XLNet for generation. And we also compare with another model, XLNet plus this VNet. Now, VNet here is used for the answer post-processing. So after generating multiple answers using XLNet, what we can do is that we can compare the answer similarity among them and then pick the one which has the highest attention score over all the other answers as the final answer. So the main results is shown here. So essentially, we can see the heuristic baseline, they perform worse compared to the neural baselines. And our model is TRIME. It outperforms the other baselines on basically 4 out of 5 metrics. Now here we also have done some ablation study by removing the context memory or removing the answer memory, and we observe the degradation performance. And here we just show some kind of example output here, and we can see that using this random sentence retrieval, or this retrieval based on the sentence similarity with the question, the answer generator is does not directly address the particular question. Now, from this answer generated by BERT, the quality is actually quite poor because it's off the topic and also is grammatically incorrect. And for the XLNet, based on the summary, review summary, or based on post-processing, we can see that able to generate answers better than BERT. However, it mistakenly used 30 minutes to replace the key term 30 seconds, which basically weakens the credibility of the answer. And our model here actually would generate the syntactically well-formed answers and also with better coherence and fluency. We have some way to actually be able to show the intermediate steps of answer generation because we have this iterative update of the answer memory as we go along. And so essentially from this figure, we can see how this answer is refined from different steps. So that will actually conclude my talk. We proposed this TRIME model for generative review question answering, and it can capture this cross-passage contextualized information, and it can use this answer refinement process and gives some level of interpretability. In terms of future work, so there's a range of things we want to do. For example, how to distinguish between factual QA and opinion QA, because in review QA, sometimes people actually ask the answer which would relating to some specific product aspects or description, and sometimes they ask about the people's user experience on that particular products. And the other thing is how to perform this query-driven opinion summarization, because if a user asks the question relating to some specific opinions, they probably want to see not just the most prominent opinion, but then also what's the kind of a range of different opinions expressed by the users, the other users, and how to perform this fact consistency check, and how to deal with these contradictory opinions, and how to develop the QA models, especially we don't have the proper supervised training signals here, and how to do the evaluation better than this lexical and semantic similarity measurement. So that will end my talk. Sorry, it takes that long. And I'm ready to take any questions if you have.
Yes, thanks, Yulan, for this wonderful talk. So there are some questions in this Q&A panel. So let me just take the first question. So there's this question that asks how we could guarantee the quality of the topic obtained from such kinds of short text. By the way, this is regarding the first piece of work you presented. So basically it's asking, product reviews are very short. So how can the model guarantee the quality of the topics?
Right. I mean, essentially, like the input to our model is the context window, right? So that's the typical way, like when people learn this using the skip gram model to learn the word embeddings. The context window size is actually 10 in our experiments. So essentially, like we only consider 10 word subsequence at one time. Now, to guarantee this topic quality, I think the one thing is we actually use this beta matrix. So the beta matrix is the topic matrix. Now, this is the global topic matrix shared across like all the, the whole corpus. So I suppose like, I mean, this is the, kind of like a different from the, the baseline like a Bayesian skip gram model, right? So in which like they don't actually like model the topics. So to ensure the topic quality, I guess, in terms of evaluation, what we can do is perhaps like just to check the topic coherence as what we have done in this, in our experiments. And also, you could somehow like try to visualize the, for example, like the sentence embeddings generated or the this topic specific word embedding generated to see whether they actually correspond to some like a kind of sensible topics. So I guess that's perhaps like the only way we can do.
Okay, thanks. Yeah, we also have another question from Sujanya. This is quite an interesting question. It's actually not specific to the work you presented, but in general about sentiment analysis, as we know you're an expert in this area. So so the question is, in this era of deep neural networks and contextualized pre-training embeddings, we can see the results on the benchmark data sets surpassing 90%. Now, for the newcomers to this field, do you have any recommendations on how should they approach sentiment analysis as a research topic? Because of the super high results obtained by these complex models on the benchmarks, there's probably a general perception that sentiment analysis is a saturated research field. Yeah, so right, so it's I guess it's especially for people who young researchers, PhD students who just entered the field. When they look at sentiment analysis, when they see such high performance obtained by these recent pre-trained models and so on, so what do you think? What should be the interesting part to look at in the sentiment analysis?
I think first, like the sentiment analysis is beyond this sentiment classification, right? So that's like a modern sentiment classification or aspect-based sentiment classification. There are many other tasks that you can explore. So I think in the recent years, there's also like some work been done on this multi-model sentiment classification problem, and also on this emotion cause extraction, right, to finding the reasons behind or triggering factors behind a specific like emotions or sentiment. I think I basically briefly highlighted some of the recent work in our group. So essentially, like what we are currently doing is, not just to do the sentiment classification, but then instead actually try to, delve into the details into those like review documents. So, for example, I think this like broad topic model, which I just mentioned, essentially what we try to do is to understand this kind of broad polarity scores, and also to be able to automatically generate the ranking of bronze, based on the people's reviews. Now, this ranking is not just, it's not just like generated based on the inferred, rating scores of those reviews, but instead it's actually kind of latent variable, which can be inferred directly from the model. And also, I think in that kind of like space, what we have done is to be able to see how this kind of a broad associated polarity topics change over this continuous kind of a polarity score. So essentially, like what we want to understand is for people bearing very strong positive opinion towards certain brand versus like some people like just slightly positive, versus like people like a strongly kind of negative or slightly negative. So in terms of like the topics they are talking about, whether there is any difference in that kind of like more fine grained kind of a separation of the polarity scores. So I guess that's also something people can do. And the other thing I think we have been working on is for example, like for sentiment classification, or sometimes like for this emotion cost detection data set, whether there's actually like any bias on the data set itself in terms of like annotation bias or some other kind of artificial sort of like a bias built into the data set, and then whether there is any like approach which you can propose to address this bias. So I think there's like a range of like different things which can be done in sentiment classifications, and not just kind of restricted to to binary classification kind of a task. And the other thing I think like people have constantly asked is about the interpretability, right? So I mean, if you use this pre-trained large-scale language model, fine-tune on specific task, and then you might be able to get very good results. But then whether the model actually be able to identify the appropriate or the correct signal, which actually gives that level of a sentiment classification accuracy. So I guess that might also be worth to look into. Yeah. So and then also, I mean, of course, this is a review question answering. So I suppose like there's we're starting to see like more and more work in this space, but then this is still very hard problem. So there is still like scope for further development.
Yeah. Thanks. Yeah, I completely agree. Yeah, there are actually a lot of interesting areas to look at. Yes. I think in the interest of time, I guess we will just stop here. Yeah, thanks again, Yolan, for your wonderful talk. I think we all learned a lot from you. Yeah. All right. So I'll hand over back to the program chairs for the closing remarks.
Thanks.
Hello, can you see me? Can you hear me?
Yes, Wenqiang.
Okay, so let me share my screen. So can you see my screen?
Yes, please go ahead. Yes.
Okay, so it's time to have closing remarks. So we've spent the whole day on SSNLP, the 2020 Singapore Symposium on Natural Language Processing. So we have covered a lot today. So we covered a lot of perspectives, such as technical solutions, ethical risks, concerns, impact on health cares. And we also cover a lot of research topics like question answering, pre-trained models, and low resource NLP, as well as data augmentation. So we have a lot of speakers, wonderful invited speeches. So let's have a review of it. So the first session is given by Mohit. He presented his recent works and thoughts about knowledge robustly and modality-grounded NLP. He covered topics like auxiliary skills, robustness, and scalability to missing words, grammatical errors, paraphrase, and sensitivity to negotiations and anonyms. Then it comes to the second speaker, Eric. He presented his recent thoughts on low resource but long-tail spoken dialogue system building. He first introduced his lessons learned through partnerships, which is that different perspective between NLP folks and the domain researchers. Then he come to address the lack of speech data problem and handling the long tail data. And he have done thinking about the new ways to augment data and train models. As for the third speaker, Alessandro, he present he presents some recent advances in question answering research for personal assistance. First, he covered traditional QA architectures can be hardly scalable, and then he presented a modern system based on retrieval engine and neural models for answer sentence selection. He suggested that this can exploit latest technology, but also being efficiency. Okay, so then it comes to our fourth speaker. Different from previous speakers, Emily presents some ideas of the ethical risks in language technology instead of proposing specific models. Right, she covered topics like the stakeholder-centered topology, data statement for NLP, and beyond data statement. He suggests that transparency is a good starting point, such as documentation of data sets, models, and a clear discussion of applications. All these need to be paid attention to in our future studies. Okay, as for our fifth speaker, Prof. Minlie Huang from Tsinghua University shared his recent thoughts about pre-training language models. First, he gives us an idea of what is understanding and what is meaning. He gives his own definitions, and he then analyzed what pre-trained language models learned and not learned from the language. It suggests that existing pre-trained language model has a long way to go to encode the knowledges. Then he presented his recent works and how to better do with knowledge. For example, knowledge injection, post-training with knowledge, and explicit control of knowledge use. Okay, so our morning session ends with our sixth speaker, who is Push Park. He recently his focusing on his research focus is low resource machine translation. He first covers the essential elements of MT paradigms, which are analysis, alignment, energy, and attention. Then he introduced the challenges of MT, which is language diversity, and then he proposed 3 ways to handle low resource translation. For example, artificially boost the resources and take off from another language. Also use higher level language properties to handle it. As for the afternoon session, we have 2 parts. First is a panel discussion. Well, this is actually the new feature which is added this year. In previous SSNLP, we don't have a panel discussion. Okay, so this year the panel discussion covers low resource language processing or Southeast Asia language processing. So you know Singapore is in Southeast Asia. So Southeast Asia has a lot of countries, right? Aside from Singapore, we have Thailand, we have Vietnam, we have a lot of other countries. So the biggest problem that we are faced with is the low resource language. So different from the Chinese and the English, which we call rich resource language. So the local languages like Malaysian and Thailand and Indonesian and Vietnam, all these language does not have enough annotated resources. So how to solve low resource language processing problem is how to say, is a hot research topic these days. So to have more discussion on this, we invited 5 panelists to give their thoughts. For example, we invited Li Dongbing from Damo Academy Singapore and Bio Junlang from Lazada Singapore. So all these two are expert. These two are expert in local Singapore. And we also have invited some other speakers, panelists from other countries in Southeast Asia. For example, Dat from Vietnam and Temple from Thailand. And so we also have Monojit from India. So we covered we covered topics like linguistic resources and theories, and the computational models, COVID-19 issues, and the commercial applications. Yeah, they are very nice and very fruitful. To conclude SSNLP, we invited Professor Yulan He to give a presentation on his recent works on understanding product reviews, topic-specific word embedding learning, and question answering. She introduced a lot of works, a lot of interesting works, such as understanding product reviews, contextualize word embeddings, and learn topics, as well as topic-specific word embeddings, as well as joint topic word embedding models. Also, he covered his, she covers her recent works on Q&A models. This is actually the last page, but I don't want it to be the end of the story. So by having SSNLP, we do want to cohere our Singapore NLP community. We do want to facilitate the discussion, the communication, and collaborations. So please do continue and extend our discussions today. So we hope it can be more fruitful in the future. So we would thank our co-organizers, actually a lot of Singapore local PIs on NLP made a great efforts on SSNLP. Here we listed their names, and especially we would thank Gang Shuo, another program co-chair that's who spent a lot of time on logistics, and we will also thank Jin Jiang as our general chair. She also helped us a lot. Okay, this is this is a QR code for the feedback collection. So we would be grateful for your feedback. So if you have any comments, ideas, and feedbacks, or if you want to extend the potential collaborations, please scan the QR code and let us know. So now I want to pass the time to Gang Shuo. Hello, Gang Shuo.
Hi, Wenxiang.
Okay,
Hi.
yeah.
Thanks. I think you have concluded very well, and you have spoken for me as well. It's been a great session today, and I hope to see everyone back next year. And we would like to improve every year, right? And this is a very young conference, and we'd like to see it go more global in the upcoming years. So we really like your feedback on how this session was the whole day, and we'd like to see you next year. Thank you very much, everyone.
Okay, thank you very much.
Thank you.
Hi, Jin. Do you want to say something?
Sure. Yeah. Thanks, everyone. Yeah, especially those who stayed until the end of the event. Yeah. So, I hope, I think next year we will have it again, although we don't know yet whether it can become a physical, a real, event. But hope to see everyone again next year. And meanwhile, stay safe.
Thank you.
Thank you.
Bye-bye.
Bye.
Bye. Bye. Bye. Bye. Bye.